spin it.
Okay, all right. I hope you can hear me. Good morning, everybody. My name's Martin Still. I'm from the NSF in the United States. I'll be the chair for the first session today. Today is full of an action-packed agenda, similar to the last few days. We're going to move topics in the morning, and we're going to talk about time domain astronomy, which, of course, is incredibly important to many of us. With the onset of new detection abilities with multi-messenger astronomy, with gravitational waves, with neutrino detection, and all of the support that we can provide with the electromagnetic observations. So for the first session, we have 4 speakers. The first speaker, I'd like to introduce Monica Saraisam from Gemini Noir Lab, and she's going to talk about a panoramic view of the time domain landscape at Noir Lab. And this is a 15-minute talk. And so I'll give you a 5-minute warning and then a 0-minute warning and start honing in. Okay. Over to you, Monica.
Thanks, Martin. So in this talk, I'll be describing the various resources being developed by Noir Lab and Gemini in particular to enable time domain astronomy, which is being shaped by a surge in data rates and data volumes from modern surveys. An important source of the data surge in the immediate future is going to be Rubin Observatory's Legacy Survey of Space and Time, or LSST. And there you can see the expected numbers for its data. So we'll be seeing several hundred petabytes of imaging data over its 10 years of operation. We're expecting up to 10 million alerts every single night. And of these, just a handful of sources can be followed up on any given night. So to do time-critical science with this barrage of data, specialized software infrastructure along with efficient data mining algorithms are a necessity. So for present and upcoming large-scale surveys, this ecosystem will be the paradigm for doing real-time science. So apart from the Rubin facility, the encircle components that you see there are resources from Noir Lab, thus highlighting its capabilities to provide end-to-end support for time domain astronomy. So we'll have millions of alerts generated by these surveys, which will then be distributed near real time to what we call as event brokers. Antares is one such broker developed by the CSDC program of Noir Lab. These events or alerts will be processed by various science filters running on Antares to find the most interesting transient events. The science filters, in turn, can be readily developed on the Noir Lab Astrodata Lab science platform. Then there's a few tens of the most exciting events flagged by Antares will be followed up using a rapid response coordinated network of facilities, that is AON. And within the AON network, Gemini will provide the largest class. We'll hear more about AON from Brian Miller in the next session. Then once the data are gathered, they will be automatically reduced by modern data reduction tools, notably Gemini's Dragon software that we heard about from Kathleen this Tuesday. Dragons will generate rapid turnaround, quick look data in order to help the user assess requirements for further time critical follow-up observations. Finally, using the data reduction package, the user can also generate science-ready data products to make discoveries, perform characterization, and use the results to feedback to the brokers to improve the filter, or they may decide to trigger further follow-up observations to trace the late time evolution of the transient. In the next few slides, I'll focus on the Antares alert broker. So Antares has been processing the alert data from the Zwicky ongoing Zwicky transient facility. The ZTF alerts are generated at IPAC and are distributed via a server hosted at the University of Washington. These ZTF alerts are then processed by Antares using multi-level filters. And in the processing, the broker Antares adds values to the raw data of the alert. An example being, cross-matching the alerts with various legacy catalogs in different weblinks. This will help to identify the high priority events. The filtered events are then delivered to the community via multiple services. So we've got Slack, then there is a Python client library, then we've got a toolkit for exploring the value-added Antares database. This toolkit can also be used to develop filters on the Astro Data Lab platform. And finally, there's a web portal that you can access at www.antares.noalab.edu. Okay, I'm going to skip this slide to save some time. Next, I'll highlight Gemini's specific resources, which will cement its leadership for time domain follow-up in the Rubin era. So the plot on the left-hand side is the distribution of the optical peak magnitudes of extragalactic alerts from ZTF. So these alerts comprise various types of supernovae. And as you can see from the plot, more than half of the sources, they have their peaks fainter than around 18 Mach. So for one-time follow-up, the arrows indicate rough aperture requirement. But the problem is this is just the peak of the transient. And what we want to do is to trace the evolution of the event in different wetlands for us to investigate the underlying physics. So to monitor rare and exciting events like fast blue optical transients or F-boats that we'll hear more about in the next session, facilities capable of rapid response are a necessity. So there you can see two example light curves of F-boats to highlight the rapid decay. So they decline by like 1 magnitude in a single day. So to capture these events, rapid response facilities, they are a requirement. Now, to specifically focus on Gemini for time domain alerts, it's not just the aperture size it offers, but a whole suite of instruments ranging from the optical to the near IR that we heard about in this meeting. Then, of course, there is Scorpio under development, which will simultaneously cover both visible and near IR, and it will be used for dedicated LSST follow-up. So Scorpio, combined with Gemini's capability for queue scheduling, will make this facility unmatched and a game changer for in the follow-up ecosystem. Now, for real-time applications, the turnaround time from observations to reduce data is also important. And on that front, of course, we have Dragon's program in place. And Dragons will play a critical role in closing the time domain follow-up loop. Okay, so in the remaining time, I will demo how the various Gemini and NOAA Lab state-of-the-art services are enabling end-to-end automation of the time domain astronomy process. So I'm gonna change my screen to a notebook, and I'll be executing this in this demo. I'll run this block by block so people can follow. So here it goes. The purpose of this notebook is to demonstrate the integration of these three key services for time domain observations. So we'll have Antares for the target selection. Then we'll trigger follow-up observation on Gemini using the Target and Observation Manager or TOM toolkit. So this is a web application framework developed by the Las Cumbres Observatory to enable triggering observations on facilities within the AON network programmatically. Then we'll retrieve and reduce the observed data using dragons. Okay, so let's start with Antares for the target selection. So here I'm importing the client library of Antares. And this is the target I have selected for this demo. This was flagged by a filter I wrote called Novatest. This finds explosive transients. It's a pretty stable filter, but I didn't get a chance to rename it. Okay, so this event occurred in this blue spiral galaxy, largely likely a star-forming galaxy. Fortunately, the galaxy was observed by SDSS, so we have spectroscopic redshift for it. And here's the ZTO flight curve of this event retrieved using the Antares client. So as you can see, there are two outbursts separated by almost a year. And if I apply the redshift of the apparent host, then these peaks are brighter than an absolute magnitude of -19, which makes it pretty interesting. We discovered this event around the second burst, and we were scrambling to get a spectrum for it. Fortunately, around this epoch, we got GMOS spectroscopy time with Gemini. So in this demo, I'm going to replicate the Gemini observation, but now using the TOM toolkit for triggering the follow-up. So Gemini is now TOM enabled thanks to a software plugin written by our own Brian Miller. And to use the API, I need to import these libraries. Then I create this target object, which will be loaded with the properties of the transient selected from Antares. And then triggering a Gemini is relatively straightforward. So we submit, we create this form where we specify the constraints for the observing parameters. And then in a single line of code, we submit this form. So basically we trigger the observation. One can also use a locally deployed web application to manage these observations. And here is the user interface that is running locally at the background for me, built using the TOM toolkit library. And for the purpose of this demo, I just wanted to highlight how the record of this trigger looks like within that interface. So I made a test trigger December last year. And oops. Okay, let's hope it works. This is a live demo, so things like that happens. All right. Okay. Anyways, you can I can show this offline, but it does work, and you would see a record of this event. Okay, let's proceed. This is anyway. So the trigger is done. The data is gathered. It will be ingested in the Gemini Observatory archive within minutes, and so we can now proceed with the reduction. The first step here is to locate the data in the archive, and we'll do this programmatically using the archive API. But first, I'm going to use the thank you, the Gemini Astro Query module to gather information about this target. So, for example, the observation ID. This is integral to download the data with the API, and then I make this. I do the download in this 4 blocks of code. So data is now in my local file system, and I can proceed with the Dragons reduction. I'm going to use the API for this process. It's now importing the Dragons libraries. And if you attended the workshop, Dragons workshop on Monday by Kathleen, how the reduction proceeds is we first systematically create file lists, and then we process the calibration frames, and finally reduce the science data. So let's go ahead and make the file list. So here's the bias file list, the science target file list. for the flats, the arcs, and the standard star. And now we can proceed with processing the calibration frames. So in this block of code, the master bias is generated. And then here we process the flat frames. And one thing I want to highlight here is for this demo, I'm using the 3.1 version of Dragons, which we expect to release early next year. And that version will come with enhanced capabilities, one of which are these powerful interactive tools that the user can, that will help the user to optimize the data reduction process. So as an example, for the flat processing step, one will be able to interactively fit the wetland structure of the flat fill using this tool. And then I'm determining the wetland solution here. And for this step as well, one will be able to interactively find the arc lines, interactively perform the fit. And now releasing the standard star, which will be used for the flux calibration. And for this step as well, we should be able to fit the sensitivity curve there. And finally, going to the science target. Fortunately, we had a clear trace in 3 exposures for this transient. And using those process calibration frames, I'm reducing the science exposures in this block of code. And for this step as well, one will be able to use this tool to interactively find the aperture. Okay. As well as interactively trace the aperture. And finally, this is the Dragons generated wetland and flux calibrated spectrum of this transient. So this Gemini observation, it helped us to classify that the target as a type 1a supernova. And the story is those 2 outbursts were actually 1a siblings that occurred in the same galaxy. So they were pretty close by, separated about 1 kiloparsec or so. But anyways, as I showed in this demo, we can perform this whole process of time domain astronomy, target selection, triggering observation, data reduction, all within this single notebook. And that is thanks to the services developed by Gemini and other programs of NOAA Lab. And I'll end my talk with this slide as a short promo. It is contingent upon funding from the NSF, but if we do get it, then we plan to develop this interface called GOATS, which stands for Gemini Observation and Analysis of Target System. And GOATS will provide a seamless integration between these various services so that you don't need to learn 3 or 4 different APIs to interact with the different services individually. I'll be happy to take questions. Thank you.
Thank you, Monica. That's an excellent summary. So now we can take some questions from the room and from online. Clara is managing the online contributions. Nothing so far, but we'll give them some time to type. Are there any questions in the room anybody would? I encourage everybody to stand up, and there's no such thing as a stupid question, as you'll find out if you force me to ask them. So don't do that, and come forward yourself and do the same. So while you're thinking, Monica, so this afternoon session after the time domain session is all about adaptive optics. And I noticed in your list of facility capabilities, in the south, you have GEMS in your list, and in the north, Gemini is working on GNAO, which will be replacing the Altair system. Is there anything that you can talk to which will describe the unique contributions that users will have using these 2 Gemini systems that will help us in time domain astronomy?
Oh, with adaptive optics, oh my gosh, yeah, you can do lots of things. I can talk about my own personal program. I'm pretty interested in variables in clusters, stellar clusters. So for example, Andromeda, clusters in Andromeda. And of course, we do not, the only facility that's capable of resolving these clusters is HST. And if, with all these AO facilities coming live for Gemini, there is enormous scope to study these sources in crowded fields. So much to be learned from these variables from clusters. You can leverage properties of the clusters in order to, study the driving mechanism of these variables. Then, of course, I think it's not my field of expertise, but for the supermassive black hole binaries, adaptive optics a big deal. Like I know that there are groups who are vying for AO time to actually, resolve the binaries if possible. I think Shin Li's group from University of Illinois, that's one group. They have a program using Gaia data where they use the astrometric, I think it's called very Stromy, or I'm blanking out on that, but they use changes in the centroid of the Gaia observation in order to find possible targets, and then those selected targets will be followed up with AO system. So there are lots of things to be done. So.
Yes, very exciting. Can't wait for this to happen in the north, especially. Yes.
There is a question on Slack.
Great. Let's do Zach first and then
Okay.
go on to online.
Hey, Monica, great talk. So, I mean, this demo was really nice in the sense that you showed off, okay, already we can get Gemini data and have it reduced already with the alert system. How is GOATS going to dramatically improve that?
Right. What I can tell you is there's the entry barrier is pretty high, because you realize that I actually have 3 software installations to kind of like interface these services. Like Antares, there's a different interface, API that I have to install. There's the archive, Gemini Observatory archive. It's fabulous, but these services, they aren't really talking to each other. It requires the user to make the connection. Now, in order to reduce that entry barrier, imagine this interface where all of these things are abstracted, right? Like as a user, I don't want to spend time, trying to figure out how to do the installation and then learning how to use the API. What I want to do is to focus, on interpreting my science results. So that's basically what GOATS will achieve. And of course, it will have like added functionalities on Dragons that will add the analysis part to it, where you can do things like splot, the RF standard splot, where you can find line profiles, properties, equivalent widths, do redshift scaling, and all these things. That me as a time-domain astronomer, I would have to go to a transient name server. This is another service, and upload my spectrum, try to do the line list analysis, or do it on a notebook separately. So I want to do away with that and have everything on one platform. So that's basically the plan.
Thank you.
Okay, let's go over to Clara online.
Okay. Joel Rodiger is asking, once the observation form is submitted by a user, does Gemini receive a treat the request like a RTO trigger?
I totally believe so, because that was the test trigger, and Brian is the guy here who made that possible. So so Brian, myself, and I guess there is a test mailing list that when I make the trigger, Brian receives the email as an RTO, a test RTO, as well as myself. So I know that has happened.
Sorry, the specific answer to that question is it depends. It can be either rapid or standard depending on what template you've used for the trigger.
Thank you.
Okay, thank you, everybody. Thank you, Monica. Let's thank Monica one more time. Let's move now to Jillian Rastinajat from Sierra and Northwestern University. And Jillian, once this is set up, and I'll say this title slowly, exploring the diversity of short gamma ray burst counterparts with the Gemini Observatory, of course.
Okay. Okay. Okay, hello. My name is Jillian Rastinajad. I'm a PhD student at Northwestern. And today we're going to be talking about short gamma ray burst counterparts with the Gemini Observatory. So what are the systems that we're actually talking about? So thanks to the amazing event GW 170817, we know that 2 neutron stars emit gravitational waves that we can observe with our current gravitational wave observatories. When they merge, they emit these waves. They also emit jets along the poles. In addition to that, you have a short gamma ray burst with a duration approximately less than 2 seconds that's launched. And so we've been detecting these short gamma ray bursts for years, and they're another signature of these compact object mergers. So the jet eventually slams into the ambient medium, producing broadband synchrotron afterglow. And in addition, we have this kilonova counterpart. So these kilonovae are thermal transients powered by the radioactive decay of heavy R process elements synthesized in the neutron-rich ejecta. And so we know about all these counterparts because we observed them with GW 170817. So we observed them and we obtained these beautiful light curves. Seemingly every telescope in the world turned to look at this event. And we have a really rich data set that we can study and look for those heavy element signatures. So a key signature of a kilonova is this fast fading optical counterpart. Here you can see in the G band. Whereas we have this longer lasting emission in the near infrared, which is a signature of the heavy lanthanide elements and their filled valence shells that increase the opacity of the ejecta. So why, a lot of you here don't study kilonovae, why should you care about them? Well, they're the only known source of heavy R process elements in the universe. So R process elements, I think someone showed the periodic table the other day. You can see that the majority of the heavier elements were produced in these neutron star mergers. In addition, this R process enrichment affects the environment and the chemical evolutions of the galaxies in which they live. And finally, these kilonovae can actually offer clues to the maximum mass of a neutron star, being one of the few electromagnetic clues that we can get to the equation of state of these unique objects. So 170817 happened. We have this one really well-studied kilonova. And so now there's been a lot of theoretical work looking at what the diversity of these objects might be. So we think that not only binary neutron stars, but neutron star black holes can create kilonovae. We also think there's some diversity in what the remnant could be. So we could have a prompt collapse to a black hole, or a neutron star that exists that's rotationally supported for a few milliseconds before collapsing, or even a light enough neutron star that exists infinitely. So all of these different scenarios leave imprints on the kilonovae, and from theoretical simulations, we have different ideas of what those light curves might look like. So here are just some model light curves along with 170817. And you can see that all of them are fast fading, but they all span about 2 orders of magnitude and even fade at different rates. So all these light curves give us something that we want to study. We only have this one really well-studied kilonova, but we want to understand what the range of diversity is when we look at observations. So the Gemini Observatory is uniquely poised to observe these short GRB counterparts and can do a lot to help us when we want to look at this diversity. So the first way in which this helps is that gamma ray bursts can go off anywhere. Fermi and Swift find them all across the sky, as this map is showing. And so by having 2 sites in the north and the south, we're able to study these bursts no matter where, well, almost no matter where they go off. In addition, and this is something that Monica brought up too, having the rapid TRO capability and the diverse suite of instruments is really key to doing our science. So here on the right, I'm showing a plot of the afterglows that Gemini has discovered over the years. Approximately a third of the observed short GRB afterglows were found with Gemini. And indeed, you can see that these are really fast fading. The majority of them disappear within a day of the actual burst. On the left, I'm highlighting the Gemini spectra of 170817's kilonova. You can see that from the spectra, we were really able to match it to models, figure out how much of this R process ejecta was created. and the composition of it. And in addition to this, this event happened very quickly. We were able to get both spectra and imaging with GMOs and flamingos. So having these instruments available was really key to extracting the maximum amount of information from this event. And looking towards the future with instruments like Scorpio and our programs on JWST, these will continue to enhance each other. So the rapid TRO response is not something that James Webb has the capability to do, but Scorpio will do, and will study these beautiful broadband light curves. And then James Webb, our programs to study both gravitational wave and short gamma ray burst kilonovae at late times and obtain their spectra. In addition, short gamma ray bursts occur across a huge redshift range. And so not only are these things fast fading, but you want to be able to observe them and extract the maximum amount of information from them. So we need Gemini sensitivity and its ability to go deep in both the optical and near infrared. And so here I'm showing an image by our collaborators where they detected the optical afterglow and then the host galaxy spectrum of a short gamma ray burst at a redshift of 1.75. This is the second most far away short GRB that we've found. And NORLab did a wonderful press release about this for us. So you can learn a lot from these host galaxies. It's not what I study, but I want to highlight Anya Nugent has a poster that is going more into these, and we can learn a lot about the neutron star systems from their stellar population properties. So now we know everything Gemini can do, but here are some questions that lead into the research that we're studying. So how can we constrain the diversity of kilonovae with existing observations from Gemini and other large aperture telescopes? Is AT 2017 GFO a representative kilonova? And then how can we leverage Gemini's TRO capabilities to observe future counterparts to neutron star mergers? So I'm going to go over two different studies that we've done. One is a catalog and the other is a really exciting event. So, as I said earlier, SWIFT, the Neil Gehrels Swift Observatory, continues to localize short GRBs at a few arc-second precision. The GMOS imager and all of Gemini's imagers, are well equipped to follow up, unlike gravitational wave localizations. And so the detection of the short GRB is actually unique in that it allows us to explore kilonova diversity at a fixed viewing angle. So we think that the viewing angle can also affect what the emission looks like, but by studying these at a fixed viewing angle, we're observing the intrinsic diversity of the kilonova itself. So what we did is we built a short GRB kilonova catalog, and this is comprised of optical and near-infrared observations of 85 short GRBs over the last 15 years. So we get our data from unpublished observations, including a good amount from the Gemini telescopes. We get data from the gamma ray circular notices, which are real-time notices to the community of follow-up. And then we go through the literature. And so actually in our catalog are detections of kilonova candidates. So these are bursts where there has been photometric evidence for kilonovae following the gamma ray burst itself. And indeed, GRB 130603b is the first example of this. We have a very well-studied afterglow, and we see a nice near-infrared emission after it. In addition, what our paper contributes is a number of deep upper limits, which allow us to constrain the diversity of the kilonovae, even though we're not actually seeing it. And so together, this includes over 250 observations that span a wide range of time and the bands that we expect the kilonova to be observable in. And of course, Gemini played a huge role in this. A quarter of the host galaxy redshifts that we use in our sample are from the Gemini telescopes, and then a huge fraction of the most sensitive observations were obtained by Gemini using our rapid TRO proposals. So I'll go through some of our sample trends and the diversity that we were able to uncover. This plot, let me explain it. So on the x-axis, we are showing just time. All of the points on here are color-coded by the rest frame band. Our y-axis is the luminosity ratio, so the ratio of the observation to the ratio of the kilonova AT 2017 GFO, matched in rest frame time and band. And so things that fall along the 1-to-1 ratio here are basically tracing AT 2017 GFO. And so, highlighting some pieces of this. So the kilonova candidates, which are labeled in stars here, we see that the majority of them are detected at least in bluer bands, and they are more luminous than 17 GFO. We also see that there are a number of bursts which have deep upper limits that probe lower luminosities than 17 GFO. And overall, this shows significant diversity in the short GRB kilonova population compared to 17 GFO. So this is about a range of a factor of 2 in terms of luminosity. And again, this is not something that we're able to do currently with the GW observations that are out there. So just want to say that we do a couple other things with this huge catalog in our paper, but I don't have time to talk about them because I'll be talking about the really exciting recent discovery of the second closest kilonova to date that is actually following a long gamma ray burst 211211A. So I've been talking about short gamma ray bursts, and indeed this clear-cut picture of short gamma ray bursts and neutron star mergers is something that this event appears to revise. So this event has a duration of about 50 seconds, well outside that 2-second range of short GRBs that I discussed before. However, we obtained follow-up imaging with the Gemini telescope after hearing from colleagues that this event was happening very close to a galaxy at only 350 megaparsecs, which is one of the closest gamma ray bursts across both short and long categories. And so Gemini NIRI followed up this event at about 4 days, and we obtained this really nice K-band detection. And this was surprising because this does not, the optical afterglow was well faded at this point. And so we're seeing this near infrared excess that doesn't fit with what you expect the synchrotron afterglow to do. We continue to observe with Gemini. Unfortunately, there was bad weather. Luckily, our friend MMT was able to come online and help us observe. And then this really exciting event actually motivated mid-cycle HST follow-up. So we were able to get this nice HST image in the background. And what that confirmed for us is that this was by and large the most likely host galaxy. And this event, the luminosities that we were calculating from this transient were very close to what we expect for a kilonova. So next, showing the light curve of our event. So the points here are actually afterglow subtracted. So we fit an afterglow model to the early data as well as the X-ray and radio data, and then we subtract that off. And then when we do that, these are our points here. The dashed line here is the kilonova that I've been talking about all along, but we just put it at the redshift of our event. And then the lines here are the model that we fit to it. And you can see just how similar, especially in K-band, this looks to 17 GFO. And I was showing the 17 GFO light curves earlier. You can see that we're not, we didn't get as many observations, but I can tell you as far as GRB kilonovae go, this is very well sampled. So so many amazing implications come out of this event. But as I said, this looks like a kilonova, and we tried a bunch of other things to try and fit the data. Also, this has huge implications in the fact that this is a long gamma ray burst, implying that at least some fraction of long GRBs are created by neutron star mergers. And then also, really excitingly, some of our friends at LIGO calculated that this would have been detectable in 04. And so we're working with NORAD and NASA on a press release for this event, hopefully to be released soon. So I'll leave with my conclusions up here, but I do just want to say a big thank you to a large team of collaborators, and then our contact scientists, Kristen and Jen Andrews, who I know is not here, having a rapid TOO proposal. They are super useful and can always answer all the questions that I have. So thank you all.
Thank you, Julian. It's a beautiful talk. So let's see if there are questions online and in the room, please.
Okay, thank you. Great presentation, Julia. And I have a question that what makes GLB 121A has the long duration in gamma ray? Because it looks like originated from the binary neutron merger. So
Yeah, that's a great question. So we don't explore that in our paper. It's a great question. We do bring up two possibilities. So one is that this actually comes from a neutron star black hole merger. And so the tidal disruption of the neutron star produces that longer lived emission. The other possibility is that you have a magnetar remnant. And so that magnetar, Brian Metzger has a 2008 paper that says maybe this is possible. But yeah, I would encourage you to look at those. There's also been a number of papers on the archive about this event now. So people have a lot of different theories about what could have caused it.
okay, so next question is quite tricky, but I just wonder how can we discriminate those possibilities with the observational data? Is there any opinions or comments?
Yeah, so Ben Gompertz, he did a really detailed study of the high energy emission for this event. And so he set up this framework that can potentially work for these extended emission short GRBs. And so, you know, we don't, because most of these GRBs aren't happening as close as this one is. It's harder to get those time resolved X-ray spectra that he does. The other thing that I'll add is that you can detect supernovae out to farther redshifts than you can kilonovae. You can detect them with a telescope like Gemini out to like a redshift 0.5. And so I should have mentioned earlier, we don't see a supernovae for this. We did follow it up with the Nordic optical telescope. We have deep limits on that. And so you can constrain the massive star scenario by limiting the supernova.
Okay, great. Thank you.
Thank you for your question.
Anything online, Clara?
Nothing.
Nothing online so far. Anything else on the room? I'll ask a quick, more basic question to form. My understanding from years ago was that long gamma ray bursts gave us a very wide cosmological window. You could see all the way back to the epoch of reionization. What's our window, our redshift window for short gamma ray bursts and kilonova?
Yeah, thank you for that question. So long gamma ray bursts, because they come from massive stars, they trace cosmic star formation. So they peak at about cosmic high noon. And so again, want to point to Anya's poster because they make this huge compilation of short GRB host redshifts, and it peaks at about a redshift of 0.5. So there's these all depend right on the delay time distribution for the neutron stars to merge, and for those massive stars to evolve through and eventually produce the short gamma ray burst. So that peak is at about 0.5, which delayed from cosmic star formation can tell you a little bit about the delay time distribution.
Great, thank you. All right, let's thank Jillian again for a fantastic talk. So next talk in our series this morning is online. We have Cal Tinyanont, who's from Santa Cruz. I don't know if we have to set anything up or whether Cal is ready to go. I have a short delay while we set this up. But the title or the topic is a local analog of a local analog of the death of the first stars. And when we're ready to go, we'll let you know, Cal. And I think Clara's in charge of giving you a star with a 5-minute to go sign.
Yep.
Okay. How are you? It's all you. You can go now.
I think we cannot hear him.
Hello, can you hear me?
Yes.
Okay. Awesome. Well, thank you very much for the introduction and for giving me the opportunity to give this talk. Again, my name is Gao Samaphon Tinyanon. I'm a postdoc at UC Santa Cruz. And I'm super excited today to tell you about this mysterious supernova called 2020 WNT. And hopefully it will serve as a reminder why finding out and following up on good old supernovae is still an exciting science. So first of all, let me introduce you to some generic properties of supernovae. So here I'm showing you a collection of like just an average light curve of 3 different types of supernovae. Up here, the peak, the brightest one here I have on here are type 1a supernovae, which come from explosions of white dwarfs. Unfortunately, I don't get to talk about these guys today. These two, a little bit less fainter lines are from core collapse supernovae. So these are death of massive stars. The yellow line here represents the type 2 supernovae. These are supernovae that explode with most, if not all, of the massive hydrogen envelope intact around the progenitor star. And as a result, you see this plateau in the luminosity light curve from the recombination of the hydrogen envelope. If this hydrogen envelope is removed somehow from the progenitor star prior to the explosion, you get a strip envelope supernovae or type 1 BC supernovae shown here. For these explosions, you notice that all the tail, the decline rate are quite similar, and that's because these explosions are powered by radioactive decays. So now in the past 10 to 15 years, we have started to use these untargeted wide field all sky surveys to search for transient instead of using galaxy targeted observations. And as a result, we have been reviewing and finding out about all these different types of rare, weird, odd transients that we did not know before. And one of those peculiar transients are called superluminous supernovae. These are death of massive stars that somehow manage to get extremely luminous. And with a luminosity increase of a factor of 100 to 1,000 over a typical core collapse supernovae, the evolutionary timescale of these explosions are typically quite a bit longer than normal supernovae as well. Superluminous supernovae also come in 2 flavors, type 1 with no hydrogen and type 2 with hydrogen. Today, I will only be talking about type 1, superluminous supernovae with no hydrogen. So how do you get this huge boost in luminosity in these events? So first of all, when you think about radioactive decay, you might think, well, if you need more luminosity, you can just increase more radioactive material. So let's see how this would work, right? So in this scenario, if you boost the amount of nickel that you produce in the explosion, then as a result, you would get higher peak luminosity. Great. The problem here is that the rise time of the transient is also set by the total mass that you have in the ejector, because more mass that you have, it takes longer for the light to diffuse out. And this presents a problem for most superluminous supernovae. When we try to fit the light curve of these events using a radioactive decay model, what you find is that you need more mass in nickel than you have in ejector mass. So for example, from the rise time, you might get ejector mass of about 10 solar masses, but from the peak luminosity, you might need 11 solar masses of nickel, and that is not physical. And with this being the case for most superluminous supernovae, you need some extra source of luminosity. One of the most simple and successful models to explain behavior of superluminous supernovae are magnetar models. So in these models, you assume that the neutron star that is born in the core collapse is highly magnetized and is spinning really, really rapidly. And this magnetar is somehow coupled to the ejector and is spinning down via dipole radiation, depositing this energy into the ejector. In this model, the spectroscopic imprints are quite clear. You get blue continuum and a series of absorption from ionized oxygen because of this very energetic source of energy in the middle of your ejector. So that's one way. Another way that we can explain the evolution of these superluminous supernovae is by having some circumstellar medium interaction. So in this scenario, the progenitor star lose some mass before its death, and then the resulting supernova shock wave crash into these CSM, producing extra light. These models are particularly good at explaining bumpy light curves that are not just a smooth evolution. And they also have their own very clear spectroscopic imprints, which are these narrow spectrum lines that you get from ionized but slowly moving circumstellar mediums. For the population of superluminous supernovae that we have observed, the magnetar models work really, really well. So this is a collection of MOSFET fits from Nichols et al. 2021, showing your favorite superluminous supernovae that are very well observed with a lot of data. And these are the magnetar model fit to these data, just to try to convince you that this works quite well. So let's switch to our protagonist of the story, supernova 2020 WNT. So 2020 WNT got discovered on October 14, 2020 by CTF. And here I'm showing a detection stamp from CTF on the left three panels. You get the new image, the reference, and then there's subtraction showing the detection of the supernova. And then on the right here, I'm just showing the false color image of the supernova at peak. And you can see that it's much brighter than the small little host galaxy. About a month after the first detection, we went and finally got a spectrum of this supernova. And from here, you can see that there's no hydrogen and no helium. So at first we thought, okay, another type 1c supernova. I also have beautiful HFC images here of the host galaxy with the supernova location here. We can take more look at it later. But what makes this supernova super exciting is that after we got that first spectrum, the light curve, so the first spectrum is here, notated by this black line. The light curve continues to rise and rise and rise and rise. And it took in total about 70 days for the supernova from the explosion to its peak. So this is extremely long for a normal type 1c supernova, which usually only rise on a matter of a few days, and the longest is maybe a week or two. And the peak luminosity of this event is also really high at almost -21. So this is getting it close to this population of superluminous supernova that I'm showing here. So in comparison, most of these different lines are from other superluminous supernovae in the literature. And here I'm showing a typical normal strip envelope type 1c supernova here, 07GR, already shifted up by 1.5 magnitude. So you can see what kind of difference in luminosity that we have here. So now, there's a problem with this light curve, however. So we try to fit this light curve with a magnetar model because we think, it's the best one for other superluminous supernovae. And we had some problems. First of all, the rise time, we just really couldn't get the rise time to fit the data very well in order to get to this peak luminosity. And secondly, there is this very sharp knee in the light curve. This is more pronounced in the photometry rather than the bolometric luminosity, but there's a really clear knee here that the magnetar model just cannot fit very well. And the reason is because for these magnetar models, the essential assumption is that the diffusion timescale in the ejecta of these superluminous supernovae have to be on the same order of magnitude as the energy injection timescale. And this is simply to allow for the magnetar to really power that very luminous curve. If the diffusion timescale is much longer than the large luminosity coming in from the magnetar needs too much time to diffuse out, and the resulting transient will not be as bright at peak. So because of that assumption, we just cannot get this long rise in the light curve to match. Another problem is that when we take a look at the spectra, as a reminder, the first spectrum we have looks like a normal 1C. So we keep getting the spectrum of this event. And I'm showing here 20 WNT is in this red line, 07GR, the normal 1C is down here. And up here, I'm showing samples of superluminous supernovae. And you can see that the spectroscopic imprints of the magnetar that I mentioned, the blue continuum, the oxygen to absorptions, 2020 WNT didn't have any of that. And this is also true all the way from before peak to through peak and also after peak. So from here, we concluded that the spectroscopically 20 WNT looks more like a normal 1C than a superluminous supernova. But when we wait long enough at late time, this is a nebula spectrum of 20 WNT. It's now starting to look like a superluminous supernova. So here, 20 WNT is shown in red. I have like a mean spectrum of type 1C down here and a superluminous spectrum at late time up here. So you can see that 20 WNT have kind of this transition from a 1C like to a superluminous like at late time. And we'll talk more a little bit of what we think is happening and why it's having this behavior. So Gemini comes in here because we got some fast turnaround time to observe this supernova in the near infrared to complement our data from the optical. So the first G-near spectrum that we got was from about 81 days post-peak. It shows all these rich spectroscopic features in the near infrared that we didn't get in the optical. And after that, we thought, okay, maybe it will fade and get too faint for another epoch of spectroscopy. So after the supernova went behind the sun, came back, we got another epoch of near-infrared observation, this time just the photometry from IRTF specs. And we started to see this like really red color in the near-infrared bands. So we went back and asked for another epoch of Gemini observations, and we ended up getting both NIRI imaging and G-near spectrum at this late time. And what these observations really showed us is that there is some dust and carbon monoxide getting formed in the ejecta of this supernova, which is extremely exciting. For a context, for superluminous supernovae, there has been only one detection of dust formation, and there have never been any sign of carbon monoxide formation at all. And this is mostly because most superluminous supernovae are too far away, so that this CO feature in the K band get redshifted out of the near infrared band that we can see from the ground. So this is a super exciting observation for us. Another thing that we are able to do with this late time spectrum is that we are able to try to fit it with some nebula model. This one is from Under Yerkstrand 2017, and this allows us to put a further constraint on the ejecta configuration of this supernova. If you have more time, you can ask me about this, how this modeling is done. So if you don't think that the magnetar contributes to the power of the supernova at peak, then what else can it be? So we considered a few different radioactivity models. First one of all, of course, we have a long-lived supernova. We all want it to be a parent-stability supernova, which is this theorized explosion of extremely massive stars. And so, of course, that's the first model we checked if we have a match. And the unfortunate part is that the rise time and the peak magnitude of this supernova don't match the classical parent-stability models very well. But we are able to fit it much better with just a more simple radioactive decay model. And the conclusion that we get is that this supernova can be explained by about 5.6 solar masses of nickel and 46 solar masses of total ejecta. So in this case, it's about 10% of the ejecta in nickel 56, which is a lot, but not completely unphysical. And so yeah, that's the conclusion for this supernova. The magneton may be there from the nebula spectrum. We see some signs that it looks somewhat like some superluminous supernovae, but we know that it doesn't power the peak based on other observations. We also found that strong CSM interactions are not likely because we don't see any narrow lines, no radio detections. So we think that it's a radioactive, actively powered supernova with about 5 to 6 solar mass of nickel, and the process that create this supernova is still quite an open question. So I will leave you with a summary with this pretty picture, and we'll take any questions. Thank you.
Thank you very much, Carl. That's great talk and that's beautiful data. So are there any questions in the room or online? Please.
Can you hear me? Okay, great talk. I have two questions. I was wondering if you could derive some constraints from the, I think you're seeing the tail of the cooling envelope emission. So can you derive some constraints from that part of the light curve?
This part?
Yes, exactly.
Yeah, thank you for asking that. So that tail is real. It came, we checked the CTF data and Atlas. They all show this brief cooling phase. The best model to explain this kind of behavior is just, as you said, shock cooling in some extended envelope. We try to use Tony Perot, like 2015 or 2021 model to derive some constraint on the envelope mass and size, but we still couldn't get the color to work quite right. But so yeah, essentially we have data from R band and G band, and fitting those two bands separately give a very different answers. So yeah, that's one thing we're still working on. One of the few loose threads of this data set.
I see, thanks. And another question is, in your conclusion, you said that CSM interaction is unlikely, but I was wondering, because we do observe like some supernovae where they likely are powered by CSM interaction, but the signature is hidden. Can that be a possibility?
Yeah, so we did definitely consider that possibility, and especially interactions with hydrogen poor CSM can be relatively easy to hide compared to hydrogen rich CSM, because the lines that you would create are quite a lot fainter. The issues with hidden CSM scenario is that usually, as the supernova expands and cool, you typically reveal the features of CSM interactions at some point. But here we have spectra from, have this plot here that shows epochs that we have spectra up here. So we sampled this thing, throughout the peak, and also very well on the tail. And at none of these epochs, we see any narrow emissions at all. And in addition, we also have some radio observations that didn't produce any detection, but we are still working on that to convert it to a constraint on the CSM density.
I see, thank you. This is awesome.
Thank you.
Question from Janice.
Hi, great talk. So what is the range of masses of the progenitor star?
That is definitely something I have to look up and work on. But yeah, if it's a single star, then it must be, in 100 solar masses range to have this much ejecta mass. And binary models are possible as well. Another thing I should mention is that this the mass number that we get from fitting the light curve shape depends quite strongly on the opacity that we assume. So if the ejector has higher opacity, then this total ejector mass can come down quite a bit.
So the context of the question is I work on massive star formation, so I'm interested, I'm not sure you can answer this, but I'm interested in the upper part of the stellar initial mass function. And I'm wondering whether or not what you see in superluminous supernovae are consistent with what we expect from a normal IMF.
Right. You mean in terms of rate of these events?
Yes, in terms of rate, exactly. Yeah.
Yeah, that is definitely not my area of expertise, but I believe that the general numbers are consistent with superluminous supernovae coming from the very, very massive star. I believe the rate is about like 0.1% of all core collapse supernovae are superluminous. But yeah, this connection between massive star population and the supernovae that we see is definitely some something that we are all working hard on, because even for a normal core collapse supernovae type, normal type 2 supernovae that we know for a fact come from red supergiants, there's still a lot of open questions on whether or not there's an upper limit on the mass of red supergiant that would explode as a type 2 supernova. So yeah.
Thank you, Cal. We don't have any questions online. For the sake of time, we'll move on to the next talk. Thank you again. Let's thank Cal.
Thank you so much.
Now, this next talk, oh, sorry, I did see them. So sorry. For this next talk, it's going to be something slightly different. Mansi Kaslowal from Caltech will be talking about the growth program, but she's currently in the air. So she's recorded the presentation for us, and that will make the Q&A afterwards really interesting. But she has asked if you have questions to put them into Slack, and she will respond to them once she has signal.
So I think my mouse is still controlling your screen.
A very good morning to all of you. First of all, my sincere apologies for not being able to do this talk live. When you see this talk, I will actually be on a flight dealing with a family emergency. And I'm very grateful to the SOC for inviting me and allowing me to participate despite the circumstances. So today, what I'd love to share with you is results with Gemini from the growth collaboration. And I begin every talk I give with pictures of the most important contributors to the talk, which is my students and postdocs. And these students and postdocs are really the powerhouse behind the growth collaboration. And students and postdocs are part of the growth collaboration, and growth stands for the global relay of observatories watching transients happen. And the concept behind this National Science Foundation partnership in international research and education is that we begin discovery on one mountaintop, but very quickly we need to actually go around the globe for follow-up to try and understand and characterize fast evolving transients, very young supernovae, fast moving asteroids, all in a timely manner. So growth is an international collaboration, and it's as much a network of people as of telescopes. There are no new telescopes in this collaboration. It's all existing telescopes, existing infrastructure, and the people really bring it together. And here are the key players in growth. You see the various co-PIs from the different countries here. And the most amazing thing here is, thanks to jet lags and time zone differences, the team never sleeps. And that's not even a joke, because the team has so much energy that it has been a real pleasure to work with. The way we organize ourselves in growth, given the large number of scientists, not just peers, but also all the students and postdocs in the collaboration, the large number of telescopes, the large number of alerts, all this needs to be coordinated. And we do that dynamically through the growth follow-up Marshall. In fact, this picture is now a bit outdated because in collaboration with Josh Bloom at UC Berkeley, the next generation of the growth follow-up Marshall, which is now the open source Fritz Marshall that any of you can download and use for your own purposes from GitHub, is now live and has been running for a while now. Over the 5 years that we were formally funded by the National Science Foundation between 2015 and 2020, we wrote 182 papers, and it was a lot of fun, well cited, and all that good stuff. So the discovery engines, the main discovery engines in the growth collaboration are at Palomar Observatory. In the optical, it's this Wiki Transient Facility. In the infrared, Palomar Gattini IR. And very soon, actually, we are going to be deploying the Winter Telescope at Palomar, which will be a new 1 meter, 1 square degree sensitive near-infrared imager at Palomar, which I'm very excited about. This will happen next month. And critical to the spectroscopic follow-up has been Gemini's rapid response capability. I don't need to preach to the choir here, but the queue scheduling facilities really enable Gemini North and Gemini South to respond within minutes. And this is unique to Gemini. And both North and South is just anywhere in the sky, anytime. It's a great hedge against weather. And GMOS, which has been the primary workhorse here, is an instrument that's available without any lunation constraints. Everywhere else, with Keck, with Palomar, with any large aperture telescopes, we struggle with the bright moon time when you just don't have an optical spectrograph mounted on the telescope. So initially with Gemini, we had some fun with the LLP program with a large number of rapid TOs. And since then, we've had many different programs led by many different PIs actually in the growth collaboration. Not just me, there's a program led by Anna Ho, one by Adam Miller, one by Robert Stein, one by Thomas Omuda, one by Leo Singer. And through this wide variety of smaller programs that we've been proposing for in various semesters, Gemini has continued to play a critical role in the scientific aspirations of the growth collaboration. So now I'm going to give you a taste of the collaboration science results. And I've broken this up into 4 sections, and I'll just spend a few minutes on each of these 4 sections to give you a flavor of the science. So let me begin with young supernovae. And the concept of supernovae evolve on luxuriously long time scales, right? We have days, weeks, in some cases months to study supernovae. But where growth really focuses energies from day one is hours after explosion. We really wanted to understand co-collapse supernovae in their infancy, within that first day after they were born. And Kawai Avishai Galyam led this effort from Weizmann Institute of Science. And what we were finding, what we were motivated by, were these very, very high ionization lines, like carbon-4, nitrogen-3, nitrogen-4, which disappear if you wait a day or 2 days, or depending on the amount of circumstellar material around the supernova. This flash in the pan that gives you these very high ionization lines just disappear. And so several students working with Avishai have actually written PhD theses trying to understand, when does a core collapse supernova show these flash ionization features? What does a population look like? When does it not show any flash ionization lines? When you just see a featureless blue continuum? How quickly do these lines disappear? So on and so forth. And really try to understand the type of progenitor, connect the type of progenitor star to the type of core collapse. And I'd say, one of the biggest surprises just which we published just this year in this motivated by the science case, was a discovery of an infant type 1CN supernova. So again, I'm showing you 2 Gemini spectra, barely 2 days apart. And in one, you see this rich suite of lines, right? Neon 3, neon 4, carbon 4, carbon 5, oxygen 5. Really, really spectacular spectrum on the top there. It's gone in 2 days. And the supernova, instead of almost all of the flash ionizers before this one, evolved to show hydrogen in the spectrum, and so they were in the type 2 category. This one, oddly enough, never showed any hydrogen. It had no hydrogen and in fact no helium either in the photospheric phase. So this was what we call a 1C supernova because of the lack of hydrogen and helium. And Avishai in this paper presents a case for why this is a new class, a new window into our understanding of core collapse. And he dubs these as 1C N for the narrow line supernova spectral features that we see. Another example that again caught us completely by surprise was an infant ultra-stripped supernova, where we see the flash ionized helium-2 4686 line that you see over here, and we see it disappear in about 33 hours. The spectrum 33 hours after explosion, you don't see that line anymore. And this thing, if you look after the shock cooling dip, you actually look at the second part, the second peak in the spectrum, and you fit that and you try to compute how much ejector there is, it's really tiny. So it's not just a stripped envelope supernova, but an ultra stripped supernova. And it is so extremely stripped that if you work through the numbers, the only way to strip such a supernova is through a compact companion. So this is what Thomas Torres and others have theoretically postulated as a class of ultra stripped supernovae, which are sort of the penultimate step towards forming a compact neutron star binary. So you already have something that is stealing all the material. It could be a white dwarf, a neutron star, or black hole, and you just formed another neutron star at the end of this explosion. So this binary, if it remains intact, could actually be compact enough to then merge in less than a Hubble time. So seeing some direct evidence of a system like this being born in action in real time was a really fun result that a growth student, Kishore Loide, wrote, and encourage you to read his paper. Now I'd like to move on, in the interest of time, to section 2, which is on relativistic explosions. And here I'd like you to speed up time scales, right? I mean, supernovae, as I said, tens of days. They live on the, if you plot peak luminosity versus characteristic time scale, then a decade ago, we were getting very excited about novae, supernovae, finding transients in the gap between novae and supernovae. In the past decade, this diagram has gotten squished, and we've been pushing to sub-day time scales. So what sort of optical transients actually evolve and explode on sub-day time scales? And the well-known piece of the relativistic explosions categories is, of course, gamma ray bursts. There's decades of gamma ray burst science with Gemini. There's no way I'm doing justice to any of that in this short talk. And what's new is that initially Gemini would go and observe gamma ray bursts that were discovered by, say, the Swift satellite, that was well localized. Now it's also been trying to find the afterglows of gamma ray bursts that are coarsely localized by the Fermi satellite, or not even that, but gamma ray bursts that are discovered first in the optical. So here are a couple of examples of things that look exactly like a gamma ray burst afterglow, but they're not triggered by a gamma ray satellite. They're discovered in the optical. And in some cases, we just missed the gamma ray emission because the satellite was looking in the wrong place. In the other cases, it could be an untriggered GRB afterglow. And we have dozens of examples of this now. We're finding more and more, as we understand the gamma ray burst population more, we are finding more and more exceptions to the rule of the sort of two categories, right? Where broadly speaking, you have the short duration gamma ray bursts that come from neutron star mergers, and the long duration gamma ray bursts that come from collapsed stars, which are deaths of massive stars. In this paper, a graduate student at University of Maryland working with Leo Singer, Thomas Amuda, and the growth collaboration discovered an extremely short duration collapsar. So the shortest duration collapsar. So if you just look at the duration, it should be a short GRP, and that's what he was actually looking to find the afterglow of. But if you look at some Gemini photometry in this case, you see this inset here. The light curve deviates from an afterglow model and shows a bump that is consistent with coming from a supernova, from a collapsar in this case. So this is the shortest duration collapsar that we have discovered to date, and encourage you to read the master's paper for more details. So that's it. I'd now like to switch gears again for the third time to fast blue optical transients. And at this point, you might realize that I have another topic to cover. And a Caltech graduate student, Anna Ho, actually comes to the rescue here. She's a Caltech graduate student until a couple of years ago, and she's now Miller Fellow at UC Berkeley. And she's also going to be giving a talk at this meeting. So I was going to tell you about her discoveries of the koala and the camel and all the fun with fast blue optical transients, but I'll leave all of that to Anna's talk and skip right ahead to section 4. And section 4 is on multi-messenger astrophysics. This is the science topic that is actually sizzling with excitement in this decade. There have been massive breakthroughs in understanding cosmic explosions through multiple messengers. So not just photons and light, but also gravitational waves or also high energy neutrinos. And on the right, I show you a picture of the ice cube high energy neutrino detector on the South Pole. And it's spectacular because just in the last few years, there have been at least 4 events, 1 blazar and 3 tidal destruction flares, where coincident with the high energy neutrino, we see an electromagnetic counterpart. And 3 times at least was a tidal disruption flare, not even an extremely relativistic or jetted tidal disruption flare, pretty normal looking TDE with a strong dust echo. This Gemini has also been helping with follow-up of these high energy neutrino candidates and helping vet them and understand which ones could be associated, which ones not. And now I'd like to focus on the picture on the left here, which is gravitational wave counterparts and the fun science we've been doing in following up gravitational wave triggers from the LIGO, Virgo, and now soon Kagra is joining this gravitational wave interferometer network. So as far as neutron star mergers go and neutron star black hole mergers go, the key motivation to study these cosmic explosions with multiple messengers is to understand the origins of heavy elements. So everything you see in blue here is synthesized by supernovae of different flavors. Everything you see in yellow here is synthesized by our process nucleosynthesis, which is the rapid capture of free neutrons to make heavier and heavier nuclei. And the best site we have, and the only site with completely direct evidence, arguably, of our process nucleosynthesis is in fact merging neutron stars. And when we encounter the situation of the synthesis of very, very heavy elements, then inherently you're filling out SPDF shells. And inherently you have millions of line transitions, and unavoidably you have very, very high bound opacity. We're talking about 10 centimeters square per gram. And the only way to overcome this bound opacity is sort of to look at the emergent spectrum shift from the optical in the infrared and improve our infrared tools. And the very first time, this majestic event from August 17th, 2017, which was the first binary neutron star merger that was directly detected in gravitational waves, when that trigger was announced at 4 a.m. on this day, the most amazing thing about this was that this lit up the entire electromagnetic spectrum And let me just remind those of you who may not be fully caught up with the story, is that as soon as the Earth rotated and the sun set in Chile, there were 8 telescopes that were observing the afterglow from this event, the electromagnetic counterpart to GW 170817. And Gemini, with the Flamingos 2 camera, took this beautiful picture that you see here in the JHK bands. This was a picture taken by Growth Kawai Leo Singer. And since that first night of confirmation and discovery of that pinpointed location of the electromagnetic counterpart in the galaxy NGC 4993, Gemini got a sequence of infrared spectra and photometry, also with the Flamingos 2 camera, till it was almost impossible to observe because the target just got too close to the sun and faded very quickly. But you could see these beautiful spectra with spectacularly broad lines, which shockingly matched predictions from many years ago, theoretical predictions from many years ago, by just overplotting some models from the grid onto the data, not even trying to fit it, just overplotting, which is so you can compare data in gray and smoothed in black to the red line here. And this was by far the most sort of vivid evidence. Infrared spectroscopy was the most vivid evidence that we have of the synthesis of our process elements in a binary neutron star merger. There is just no way any supernova, any transient of any other sort could produce the lines that we see here. And these are not single individual lines, but all blended together, many, many different lines with very, very high velocities as well. And then since then, we have made a lot of progress and tried to discover even more the electromagnetic counterparts to gravitational waves. There was an entire observing run, the 3rd gravitational wave observing run, where there were many triggers for binary neutron star mergers and neutron star black hole mergers, a total of 13 triggers. But the median distances were really high, and the median localizations was over 4,480 square degrees. Our tools were sharper. We had this wiki transient facility with the 47 square degree field of view, and you can see how quickly we could map these ginormous areas within a few hours after merger, and less than 4 hours after merger. But the challenge was all in the follow-up, right? Inside those 13 gravitational wave event localizations, there were 2.1 million candidates. And it took multi-step machine learning, all kinds of photometric and spectroscopic follow-up of all of these candidates to bring down that funnel to conclude that with all the follow-up data in hand, without which we would be able to say nothing, with all the follow-up data in hand, none of those triggers or none of the data associated with those 13 gravitational wave triggers in the 3rd run were consistent with physically being associated with those neutron star mergers. So there was 0 kilonovae after all of this. Gemini played a key role in this follow-up game here. And so what we were able to conclude was that perhaps GW 170817 was not the norm. Perhaps the luminosity function is skewed towards a significant fraction of kilonovae or electromagnetic counterparts to neutron star mergers being fainter than GW 170817. So there's some constraints you can derive even from the non-detections in the 3rd run to learn about what the underlying luminosity function would be. Furthermore, you can constrain the rate. I mean, it's been 5 years since the discovery of GW 170817, and so you can ask the question if there were more, how common these events are, by looking for these events completely serendipitously. It has nothing to do with actually the gravitational wave rates. I mean, you can see the gravitational wave constraints in light blue here, but independent of that, you can now use just the wide field optical surveys, many different ones, to try and constrain the rates of these events. And the rate has to be less than something like 900 per gigaparsec cube per year if GW 170817 was a fair example of the luminosity function of such events. And this pipeline that we are using to search for kilonovae serendipitously is called ZTF REST, just for fun, for real-time searching and triggering. It's a pun on the word rest, right? Because it's really not really resting, but searching all day, all night, every night, even when the interferometer is offline. And the idea is that we look at the fastest feeding events, and we try and understand them in real time by getting prompt follow-up and seeing if any of them are consistent with kilonova. And we found many a gem in this data, many gems of different types even, but none of them are actually consistent with the kilonova. So they strongly constrain the rate of kilonovae by doing this serendipitous search. In just the last couple of minutes here, I'd like to conclude with some thoughts looking ahead. And I'd say in the coming few years, let's just say the coming 5 years, one of the things I'm most excited about is neutron star black hole mergers and finding the electromagnetic counterpart to a neutron star black hole mergers. We know they are no figment of a theorist's imagination. In the third observing run of LIGO Virgo, they found these events. They found a couple of these events with some with pretty extreme mass ratios. So where the neutron star is probably swallowed whole by the black hole. Some with more tantalizing mass ratios where maybe there was possibly some ejector, right? The localizations were much too coarse. So in the coming observing run, the fourth gravitational wave observing run that should start in March 2023, I think we have a real shot at understanding and discovering the electromagnetic counterpart to neutron star black hole mergers. And of course, at the very end of this fourth gravitational wave observing run, we'll have a new giant in optical time domain astronomy in the room, which is the Rupin Observatory. And this will be so incredibly powerful that it will do tremendous amounts of science, not just in the multi-messenger arena, but in all types of time domain astronomy, in all aspects of astronomy, in fact. And I'm hoping that many of the students and postdocs trained by the Growth Collaboration in the last few years will be leaders in the Rupin time domain science world. And Gemini has been thinking ahead and is building this amazing new spectrograph called Scorpio. And I'm sure it's going to do fantastic follow-up. And we'll have a real treat of spectra and science that will be enabled by this instrument. And with that, I'd like to thank you again for your time and patience with this recorded talk. And I'd be very happy to answer questions as soon as I'm able to get internet again when the flight lands. Please put your questions in Slack and I'll be sure to answer them. Thank you so much and hope you enjoyed the Gemini Science meeting.
At this time, it's important that you understand I am the replacement chair for this session. Young Shin In also has a family issue. And so unfortunately, they had to go home for that. So please join me in sending both Mansi and Young Shin our thoughts and warm wishes. So now is the last part of the session. We have 12 individuals coming up front for poster flash talks. And I have no idea how to organize this. So somebody needs to take the mic from me. Yeah, so line them up, key things to say who's next.
You can, okay, yeah, we'll pass it around, but actually we like to use it. Oh, okay, so this is you. So yeah. Just nod over to me and I will change slides if that's fine.
Just one.
Okay.
Yeah.
There you go.
Good morning. I'm Gu Lim, and I recently passed a PhD defense a month ago at Seoul National University. So I'm mainly interested in the project system of the Taiwanese supernovae. So it is largely known that their project system is the white dwarf in the closed binary system. So there is no consensus of the companion star. So I'm mainly studying to find evidence of their project system. So there can be a non-degenerate system such as the main sequence star or the red giant star or another white dwarf in double degenerate system. My poster is on the late time spectroscopy, the study of the Taiwanese supernovae to detect the H alpha emission predicted in the late time phase. So this emission is originated from the stripped matter of the companion star, which is revealed 200 days since after the explosion. So I think I am in the future I am preparing the Gemini spectroscopy observation of the Taiwanese supernovae, especially with the early bumpy feature in the early light curve. So the plus other transients and the robotic system for the observation is another my interest. Thank you.
I'll wipe it off then. Just figure, be safe, yeah. Okay, so make sure you just into it and then nod if you need to change.
Okay. Hi, everyone. My name is Anya Nugent, and my poster presentation is on a short GRB host catalog of observations and stellar population properties, which Jillian Ristinajad mentioned earlier in her talk today. So short GRB hosts are incredibly important for telling the story of these transients because they are what sets the redshift for these events, so we can understand their energy scales. And also we can make a lot of inferences about their formation channels or the formation channels and timescales of their neutron star merger progenitor systems. So in that vein, we have collected a lot of data on short GRBs, especially using our Gemini rapid TOO follow-up program, which we can use to locate the afterglows of short GRBs, and that helps us determine what their hosts are. Furthermore, we've collected a lot of photometric data on each of these host galaxies and spectroscopic data to determine their redshifts. So out of the 149 short GRBs that have been detected with SWIFT, we have been able to make 84 host associations, which is the largest sample of short GRB hosts to date. So out of these 84 host associations, we have enough data to do stellar population modeling fits for about 68 of them. And from that, we can get photometric redshifts for the ones that we don't have spectroscopic redshifts for. And we can determine things like star formation rate and stellar mass and their star formation classifications. So in total, this helps us understand the delay times of these events and their full delay time distribution, as well as how connected to star formation their progenitors are. And this even has implications for how we should do follow-up methods in LIGO Virgo 04. And I also want to mention that all of this data on the observations and the stellar population properties is publicly available, which you can find through this QR code. It's bright.sierra.northwestern.edu. So I hope to talk to you all more. Thank you.
Hello, everyone. I'm Yasna Ordenes Briceño. I'm a postdoctoral fellow of Catholic University of Chile. And my poster is about the next generation Fortnite survey. That is, well, the aim is to do a census of baryonic structures in the Fortnite cluster, galaxy cluster. So here I show in the first plot the sky, the coverage area of the survey. And we are covering the Fortnite cluster up to the virial sphere. So we have 19 decantades in UGI, in the optical, and we are detecting the low surface brightness dwarf galaxies. So we have candidates, and we are have a preliminary number of 800 dwarfs in the area. And summing up the bright galaxies, we have around 1,000 galaxies to study in detail. So we can study morphologies, projected surface density distribution, structural parameters, color analysis, and scaling relations. So a lot of things to do. And can you change? So we want to use the Gemini facilities to have a better understanding of the dwarf galaxy. We would like to have radial velocity, but also we need to understand the scale, well, the time formation scales of the nuclei, the nucleated dwarf galaxy and the non-nucleated. So here we test the dragons in some of the dwarfs that we have already. So we have a lot of things to do, and stay tuned because of papers are coming out soon. Thank you.
Hi, in this poster is presented the results of the PhD thesis of a student of mine. He couldn't attend to the meeting, so I present in the poster. He studied the chemical evolution of the main body of the SMC using star clusters as tracers and using also calcium triplet metallicities. I will not give more details about the poster because a video recorded by him will be played in the afternoon poster session, but you can contact me if you have any questions. Thank you.
Hello, everyone. I'm Yeonseok from Kasi in Korea. Oh, yeah, I heard my poster keeps falling from the board, and I think it's suspect. I suspect it's because it deals with the heavy elements. My poster presents a preliminary result of the one of the youngest and nearest galactic supernova remnants, Cassiopeia A. Cassia provides a unique opportunity to study circumstellar knots, material ejected before the supernova explosion. We obtain beautiful GMOS spectra of 24 circumstellar knots, so-called quasi-stationary floculi. Next slide, please. So you can see a beautiful spectra of 2 examples. And then based on that, we could derive the visual extinction directly, which is very important to do for the further analysis. And we did some shock analysis from them. And if you are interested in what we found, please come to see my poster and be careful, it can fall down again. Thank you.
Hello, I'm Clara Martinez Vázquez. I am Science Fellow at Gemini Observatory in Hawaii. And here, next slide, please. In my poster, I am presenting the deeper look into the main sequence blue struggles stellar pulsators in a extragalactic system. We studied 2 clusters with GMOS. And thanks to the deep photometry of Gemini GMOS, we could reach the main sequence and far beyond. So we detect a lot of Delta Scuti stars. Especially for the first time, we detect a lot of stars, Delta Scuti stars in the small Magellanic clouds. and the very largest detection of the stars, Scuti stars in one intermediate age cluster of the LMC. And you can see in my poster that, well, thanks to this, we could infer that the age of the cluster in the Small Magellanic Clouds, which is NGC 419, is smaller and than expected. So this cluster is younger than previously thought. And if you want to know more about this, you can check my poster. It's very, in 1 minute, I cannot explain all of this. But another thing I wanted to mention, we are going to publish a paper because we detect a very peculiar periluminosity relation in the Delta Scuti stars in extragalactic system, and we don't observe this in the Milky Way. So yeah, if you have any question, I'm here, or please ask me on Slack. Thank you.
Hi, my name is Jen Miller. I'm a science operations specialist at Gemini North. My poster discusses the preliminary work and results, ongoing work of the Gemini North infrared detector controller upgrade, the IRDC. And in the IRDC, the purpose is obsolescence mitigation, and we will be replacing the GNAT controllers, the original GNAT controllers in GNears and NEARI with new generation 3R controllers. These new controllers will help us provide support into the future, as well as eliminating some issues that we have with the GNAT controllers. If you would like to ask any questions, please Slack me or stop by the poster. Also, I just want to mention that data obtained with these controllers will be backwards compatible with Gemini IRAF package. So thanks to everyone who has done work on this, everyone listed, and thanks Janice and the LLC.
Oh, hello, everyone. I'm Romelista Castillo, a PhD student at Seoul National University, and I'm here to talk about my poster. Recently, we conducted a study of dust destruction and survival in supernova remnant in the LMC using P2 and iron 2 narrowband image, and as part of my thesis. Among all the supernova remnant that we study, these 3 supernova remnant show P iron abundance ratio comparable or even larger than those of general ISM. And normally we expect the opposite. So these supernova remnants have different environments, ages, so the situation can be different target to target. So possible origin for this high P iron abundance ratio can be related to supernova ejecta as Ca, and also circumstellar medium or interstellar medium, or contamination from near resources. So to find an answer, we are using optical spectra obtained with Due South to analyze different line ratios, and also compare the observed emission lines to shock model to obtain their shock velocities. So if you are interested in our preliminary result, please visit our poster in the poster area, or the PDF version. And also, if you have any comments or questions, please contact me. Thank you.
Yeah, okay. Hi, everybody. My name is Mark Rawlings. I'm an associate scientist at Gemini North. I do a bunch of stuff. One of the things is I'm an instrument scientist for NEARI. So thank you to all the wonderful people who've shown lovely science from NEARI so far. But I'm also the instrument scientist for GPOL, which you won't have used yet because it hasn't been commissioned. But that's what my poster's about. GPOL is a polarimetry module that fits inside the acquisition and guidance system, actually on the telescope, and allows polarization of the signal to come down to instruments on the bottom port. It's basically like a toaster with bits that pop up, each of which has a rotatable wave plate in it. It's currently fitted for a half wave plates to do linear polarization. And I guess there's some numbers on here about what it's going to be able to do in terms of wavelengths. So basically anything you can do with the facility instruments. Initially, we're commissioning it with NIRI to demonstrate that it works, which is one of the reasons why I volunteered to take over the role. The synergy there. So we're initially hoping to be able to do polarization of point source objects, compact objects, and see how it goes from there. Next slide. Yeah, there's way too many words on here for me to read them all, so I won't. Basically, things are progressing, software's working, new control boards in there. I just got an email today telling me that the unit's shipping. We've actually got the shipping sorted out, so it's going to HAA. They're going to look at it, test it, refurbish it. Hopefully, we're going to get it back before the end of the year. Science, I do that too. Personally, I'm interested in using it for things like dust polarization analyses, grain alignment, that kind of thing. But also, I'm involved in the JCMT large program, which is called Bistro. It's actually a series of large programs which studies molecular clouds, star formation, filaments, all that good stuff. And they've produced some beautiful polarimetry results with the JCMT camera already. And I'd like to do follow-up. Thank you very much.
Hi again. I introduced myself yesterday, so I'm still being Victoria. And I want to show you this time my last poster. This is about our analysis on the star formation history of disturbed early type galaxies. My teammate, Carlos Escudero, early this year found a very young population of globular cluster in NGC 4382. And now we are looking for the fingerprints of that burst of star formation in the galaxy itself. And let me tell you that Carlos Escudero is not only my teammate, he's also a member, sorry, my mask. He's also a member of the Argentinian National Office, our NGO, and I will take this part of my minute to thank to Carlos, Leandro, Luciano, and Gabriel over here, because we all the community of Argentinian users of Gemini are very grateful. I'm proud of them. So, muchas gracias, Gaby. And well, that's all. Thank you very much. And gamsamnida.
Good morning, everyone. My name is Javier Fuentes. I'm an SOS in Gemini South, and my work presented in the poster consists in the study about the temporal variability of the delivered image quality using GMOS imaging data as measured by the quality assessment pipeline over the last 18 years in Gemini South. So we also use dedicated SIM monitors as a differential image motion monitor, DIM, and the multi-aperture scintillation sensor, MAS, to explore the sightseeing and the turbulence parameters. Both instrument, MAS and DIM, are located at Cerro Pachón in Chile. And ultimately, we extracted environmental information from the outside weather station to explore the influence of the weather on the image quality as a function of the telescope position. So the aim of this study is to monitor the image quality as it is an important metric for Q observing and scheduling, especially for adaptive optics instruments. So about my results, the median seen, the median delivered image quality corrected at zenith and at 500 nanometers from long exposure GMOS imaging, it's about 0.75 arc seconds. And DIM and mass data indicate that the median total seen at Cerro Pachón is 0.76 arc seconds and a median free atmosphere seen of 0.46 arc seconds, all layers above 500 meters. This result is better to the median total seen found in Cerro Tolo Inter-American Observatory. And it's in agreement with the previous studies made in the regional area. So mass data indicates that there is a strong annual variation of high altitude turbulence during wintertime and weak turbulence encountered while approaching to southern summer mount. And the ground layer seen contributes typically about 51% to the total integral. And finally, the weather influence on the IQ at Gemini South, we found that the IQ deteriorates when the wind's speed is above 10 meters per second when pointing to the telescope to northern directions, and less impacted when the telescope is pointing in southern direction while winds are ranging between 5 and 10. Thank you very much.
Okay, that is the end of a rich and fascinating session. Blame only your chair for a curtailed tea break, and we'll be back at 11:10. But for now, please applause for the speakers, for our hosts, and our hosts over here, and for everybody in the audience. Thanks very much.
I'm going to leave this. No, thank you. I should have been connected here to put the stars because some of them were like super long. Yeah. Are you going to be the chair of the next? No. No, I think. No, we're feeling. Hello. The next one, but I think. No, I mean the next one after. Thank you.
How many of you did 5? You made it perfect. I went to 85. Oh my God, it's not good. I'm going to want to start a real thought out responses. Like, bring power right now. No. Everything we want. Well, I think one thing was. I'm still a little. Where's the next picture? Oh, And at that level, well, it depends. Sometimes we want to just do it.
So we have to impact statement. Starting from. Yes. Yes. So we have the, well, I make notes as well. So we have, can I take that? I'm yours, right? Well. I didn't have to check anything all with an actual. Yeah, or you can check. I mean, I think I have to check. Let me check one and you can take it if you want. Well, in any case. Yes, oh, yeah. Some don't know what that fraction is, but we. What you talking? Yes.
You know. Guy going, ding, bring out. For like 5 minutes, 0 minutes.
Yes, and it had its own share of. So I. The mantra is. Sorry. That's great. Yeah, there is no.
Want to check. Okay. Let's get started with the second round of this exciting, explosive session. For those of you who do not know me, let me introduce myself again. I'm Monica Saraisam. I'm an associate scientist at Gemini, and I'll be the chair for this session. The virtual chair will be Clara Martinez Vasquez. And just a few notes and reminders before we get going. To the in-person speakers, if you see me raise my hand, so that will be a 5-minute warning. At your 0th minute, I will stand up, so you'll know. Remote speakers, our virtual chair, Clara, will annotate your slide with stars at your 5 and 2-minute warnings. So just keep an eye out on that. Also, remote audience, please post your questions or comments on Slack using the corresponding speakers thread. And to the audience here in the room, if you'd like to ask a question or make a comment, please either come up to the microphone so that everyone can hear you, or if you prefer Slack, you can use that as well. You're welcome to do that. If you're not able to get to your question during the Q&A session, please also post them on Slack. And speakers, do keep an eye on that after your talk. Okay, so let's get going. Our first speaker for this session is Massimo Roberto from Space Telescope Science Institute. And Massimo will be presenting remotely. He will share with us the progress on the Scorpio instrument. Massimo, please take it away.
Thank you. Hope you can hear me well. And good morning, everyone. And my apologies for not being able to be present with you. I really regret missing this opportunity. So this morning, I'm going to give you an update about the status of Scorpio. Scorpio is an acronym for spectrograph and camera for observing rapid phenomena. And the real Scorpio has 8 legs. The instrument has 8 legs, so it's a very appropriate acronym. I think we were pretty lucky with that. How do I move to the next slide here? Sorry, I cannot hear that.
You can use your arrow keys.
Arrow keys. So if I move the arrow, this doesn't move.
Working.
Oh, it's working. Sorry, it's just the delay, I guess.
Yes, there is
Oh
a
my.
little bit.
Fine, sorry. Okay, so this slide shows just a summary of the enormous range of science teams that can be attacked by an instrument like Scorpio. Of course, Scorpio has been designed for being a time domain machine. So you can see here the long list of science observations that can be optimally carried out by Scorpio. And we just heard about kilonova and fascinating stuff like that, but the range really goes from these exotic extragalactic objects or galactic extreme objects, so to speak, to exoplanet transits, for example. On the other hand, when you have 8 channels that can observe in parallel, both in imaging and in spectroscopy as a target with such an efficiency, I'm pretty sure Scorpio will be highly demanded also as a general facility instrument, because you get simply more data at the same time with a nice gain in speed, in observing speed. The main instrument capabilities are summarized here. Scorpio, as I said, is an imaging and spectroscopic mode. In imaging, we have 8 channels, and the channels are basically rigid in some way. The band passes are fixed. You cannot put an H-alpha filter, so to speak. You have the broadband GRIZ and the Y, JH, and K band for the near IR. So you cover for about 4,000 to the K band, 4,000 extern to the K band. And we made an effort to go standard with this band passes, so to get the same type of, almost basically the same type of edges of the LSST band passes, for example. So color corrections when you get the transits with LSST, for example, should be minimal, basically avoided. The field of view in imaging is 3 by 3 arc minutes, so it's pretty large. And it's 180 seconds, and on a 1K by 1K detector or detectors, you get a scale of 0.18 arc second per pixel, which nicely sampled the seeing that has been presented in one of the posters. The spectroscopic channel has, again, 8 channels. The hardware is basically the same, except that instead of filters, now you put VPH gratings and slit on the focal plane, so you get a simultaneous wideband coverage. We push with the spectra a little bit below 4,000, not too much, because we know Gemini has a silver coated mirror. The resolving power is 4,000 when we use the 3 pixel sampling. The 3 pixel wide slit is about half an arc second, but we have a narrower one, a 2 pixel, and then a suite of other wider slits that will give you better throughput, of course, with at the price of the lower resolving power. Interestingly, the slits are as long as the imaging field, 3 arc minutes. 3 arc minutes is very large. If you're familiar with our cousin, which could be X-shooter at ISO, X-shooter is about a dozen of arc second, if I remember well. So with 3 arc minutes, you will always have a chance. You can basically probe almost 6 arc minutes diameter field. So you always have a chance to have a nice a bright comparison star in your slit, which I think is very, very good for monitoring and, to cross-calibrate your source against something, your variable source against something that is not supposed to be variable. Another great advantage is that this instrument is supposed to be, will be reconfigured from imaging to spectroscopy very rapidly. So you can acquire or study your field in imaging and go in spectroscopy. But actually, we try really to push the limit with that and go with the ultra fast target acquisition mode. And this is enabled, as I will show, by having slit viewing camera. So you can put your slit, but you can also see what is around, and therefore you can, if you are off by a little bit, you can just put your source, your target in the slit with a single move, and should be very, very fast. Another nice thing that this instrument has is that the CCDs sort of not conventional. The ones that we use are frame transfer CCDs, and this allows us to drive them very, very rapidly. There is a continuous mode. Of course, the field of view will be smaller, but there is on a small field of view, you can go as fast as 50 milliarc second per frame and do this forever, continuously. Or you can even beat this limit. At some point, you need to take the data out from the CCD, so you need to stop after a while, but you can have bursts of exposures that can be as short as 3 milliseconds. If you have enough photons in 3 milliseconds, that would open a new window in our astrophysical measures. So it's pretty extreme, the range of things that you can do with this machine. Here is a picture. I apologize for the next thing that you are going to see, which is this one. Is how Scorpio is going to see. The perspective is completely wrong, but gives you an idea of the size. It's actually a pretty big instrument. It's 2 tons, the limit, and is divided basically in 2 parts: an optical channel, an optical side, and an infrared side. Here you see better the structure. On top, you can clearly see this half cylinder, which is the cryostat for the infrared channel, and on the bottom, the black side, the black shape, is the visible channel. So they sit one on top of the other, and this has been already shown basically, but this is like zooming in and seeing how this layout is arranged. Let me point your attention to here this green, the green element to the left. This is the first dichroic. The light basically comes from the left through our window in the infrared, but then the visible is immediately splitted by this beam splitter through another window, a secondary window, and goes to the lower floor basically. So it goes in and out from the infrared channel to feed the visible channel. This is another zoom of another view. Basically, I'm opening for you the instrument showing how these channels are arranged. The infrared is on the top, and at the bottom, almost specular, pretty similar concept, is the visible channel. And the way this works is basically through a cascade of dichroics. The beam is splitted and distributed by basically 3 passages to the dichroic. Here in the infrared side, I will show you the light comes from the entry window and then goes to 1, 2, 3, and 4 longer or shorter and shorter channels, depending on the performance of the dichroic. And besides, apart from this beam splitting, the design is pretty conventional. There is the usual collimator camera with a pupil plane, where in this case we put the VPH gratings. These VPH gratings are mounted on these benches, and they can be pulled in and out. And when they are in, you are in spectroscopy mode, and when they are out, the filter is in place, and therefore you are in imaging mode. The same is true for the other side, for the visible side. I guess you can imagine that the show is the same here. The light is reflected and beam splitted and reflected, etc., to feed the four CCDs. So a key requirement, I think is important to reminder, is that during our integration, that is actually in progress right now, we will make sure that all the 8 focal plane are aligned very, very carefully. And the idea is to have an offset of a couple of pixels maximum between them. So the field should be, the 8 fields should be very, very nicely superimposed. Also important, the 8 fields have basically the same scale, 0.18 arc seconds in all channels. There will be some image distortion. There is some optical effect that changed by tiny bit the plate scale. Is not an issue, of course. Even in quick look you can correct for that, but the idea is that you will get the same image each time in parallel in all these canonical wideband filters. This is a zoom into the filters and the capability. Wavelengths go left to right here and shows here the 8 channels, GRIZ. The names are here at the bottom, GRIZ, and then we move in the infrared where we have YJHK. There are gaps, they correspond to the atmospheric opacity, H2O opacity gaps, as it is common in the infrared. Y and J are nearly contiguous. The gap again is designed to avoid the regions of very high opacity in the atmosphere, and also to make these band passes consistent with the standard band passes. Also here the Z band, for example, is short just because it's shorter on LSST. So we really clone what we have. And also in imaging, you see the image start for 400, and in spectroscopy we push below. Again, we want to have band passes, especially in the visible, that replicate the one that are considered to be standard. This is an illustration of how the instrument works. As I said, 3x3 arc minutes, 0.18 arc seconds is 1K by 1K. The detectors are much larger. There is a lot of, so to speak, wasted space, but that's this comes basically for free. These are the detectors, the science-grade detectors, the E2V that we want to use in the visible. In the infrared, we go with 2K by 2K, the Y2RG, and they are 2K by 2K. And again, we need a 3x3. So we will have these fields sitting at the center of our detectors, and they will be limited by a field stop just after the window. We have a selection mechanism that puts the stops. For spectroscopy, it's the same 3 in length, but is sitting here in the middle is our tiny slit. The spectra in this case are extended over as much as possible and as much as space you have on the detector. So with spectroscopy, we really like having 4,000 pixels. In this case, we have 2,000 pixels, and we use all of them. And things are arranged in such a way that you get about 4,000 resolution spectra in both in the visible and in the infrared. And then there is this other mode that I was briefly mentioning before. We can put on the focal plane a narrower slit, and with this narrow slit you can optimize your readout, transferring out the charges at very high rate, and with a couple of clever tweaks you can push your exposure time to the millisecond range, either in continuous mode or in burst mode, depending on your science case. These basically illustrate the main modes. See here. Okay, this is. I apologize because for these parts at this point we start having really a lot of hardware ready, but this is still a PowerPoint slide, but it's pretty clear. And it shows you how in the focal plane, just after the entry window and before the first dichroic that push the light down in this hole to the visible channel, just here in the common focal plane, again, in shooter has different focal plane. We have a single focal plane that serves all the channels. So very immediate target acquisition, everything is on focus here. We can put the slit, we can put the field stop. This is the point on the right where we have our selection of slits and the narrower mask here at the center. And this is another, and I picked up another feature of the instrument. There are many of them, of course, but this is an interesting one. Here on the right, you see through this hole one of the slits. There are reflecting surfaces adjacent to the slit with a tiny tilt. Is an interesting piece of hardware, this one. And they reflect the off-axis field to a reimaging system. So when you put the slit, there is here a CCD on the side that will always be able to give you a narrow field around the slit to make sure that you are perfectly centered, the tracking is okay, the seeing stays whatever it is, and especially when you acquire the source, you can see where the source falls after the telescope move, and if you need, do the last final adjustment for fastest target acquisition without having to go in imaging mode and then back and forth, save time. This is, of course, when you have all this, you have to understand, I mean, I think you understand very perfectly, very clearly the situation here. When you go in the blue and maybe there is no moon, you don't want to read the detector. You want to go faint, you want to have long exposures, and then the shorter the wavelength, the faster the changes in the atmospheric transmission, the OH change, the lines, etc. So the integration times need to be coordinated, because certainly what you don't want to do is to move the telescope for a diddler move or to move your target in the slit when one detector is integrating. So there is a lot of attention that has to be paid to syncing the readout modes. And I can anticipate already that the 4 infrared detectors are basically independently driven by 4 readout modules. So you can clock at different speed this stuff. Not that we may want to do that, but there is a significant independence here, because even Y and K band may have different requirements in terms of length of exposure. Exposure that in this case for Scorpio, I think unlike the majority of instruments, will be done in non-destructive mode with multiple reads of the sample. We do this on the Hubble and on Webb, which is my background, and they are very effective to understand better what is going on if there is any variation. And they are also great to improve your dynamic range. You hardly saturate sources because you start with, you get the entire suite of exposure times. When you saturate from a certain point, you still have the early frames in your ramp that you could count. So this is work that keeps us busy and will keep the telescope operators busy. We don't plan to give you a crazy amount of freedom here, but provide you with optimal combinations, of course, to simplify life. And we're working on them. So the status of the project is, I would say, despite COVID that clearly delayed delivery of parts, the companies, a lot of these parts going cascade, and our lens has to be, you need to procure the glass, you need to polish, you need to coat, comes back. Everything, every lab that stops forces you to a delay. But we made good progress. We are basically at this point, we have delivered almost the
Hi, Roberto.
entirety of
We
the,
need to finish up because it's 1 minute and a half ahead, please, if you can.
Okay, so that's
you.
I can certainly close here. I just want to
Okay,
say
thank
that
you,
the
thank you.
instrument is supposed to deliver in 24.
All right. Questions? First, maybe?
Yes.
Oh,
Hi.
sorry, Ricardo. You'll be next.
Oh, me. Okay. Thank you. So I have a question about this high-speed imaging mode. So you show it's possible in this very narrow rectangle. Is it possible to change the RI of that one somehow? That's the first question. And the second one, is this high-speed imaging available for all 8 channels or only the optical? Thank you.
It's available for all 8 channels. Of course, the readout, so starting from the second question, the readout is different because you have, it's really driven by how fast you can transfer charges out from a CCD. So this is the key that drives. With infrared detectors, things may be a little bit faster. Also because we read the detector with the full 32 channels out, not the 4. So I'm not that concerned about the readout speed in the infrared, but it's really the speed of the CCD and transferring the data out. In principle, be done on larger areas. But we have only one field stop. The trick is that you have to move the charges that have been exposed to a dark region and start to stop exposure because you want to take the next one. So this has to be done on windows that are 100 pixels wide. So we move there in the middle. So 50 up, 50 down. The time that it takes to transfer these charges is basically what drives your readout speed. If you want to have 200 by open windows, you don't have that just because we have this single field stop that down select this opening. And this has been, we thought about the optimization process, what is the seeing, how large can optimally be. And we ended up with the 18 arc second wide region for fast imaging mode is enough to sample bright targets.
Okay, we just take one question, Zach.
Hey, great talk. I also have a question on the fast mode. And principally, so you mentioned, it's being able to run in burst mode. And I was wondering how many frames, like in a set amount of time, you can take before you need to offload the data.
Yeah, I sort of easy the math at this point. First order, forgetting the fact that you are also transferring out, but think about the detector is 4K by 4K, and we have 2K on the top and 2K on the bottom. We use the 50 pixels, and then we have 1950 pixels that are in the dark. So they can store the charge and slowly you put them out. But this means that you have 20 slots on the top and 20 on the bottom. Right? Sorry, 50 2000 is 40. Right, you have 40 frames basically you can store on your chip very rapidly. It takes nothing to transfer this 50 pixels in the dark area. Then you start taking them out. The speed is much slower there, and this buys you only a few frames. So I think we'll be about 43, 44 exposures. I don't remember the exact number at this point because it goes with the decimals, but it's less than 50 frames you can take. So 3 milliseconds, if you really go to the maximum speed by 50 frames, you get your number, right? It's a fraction of a second, 150 milliseconds.
Okay, we have run out of time. I know there is one question on Slack, so Massimo, please take a look at it. Next time, next we'll start with Slack. Jerry, set up for the next speaker. Okay, so our second speaker is Anna Ho. I believe Anna is now an assistant prof at Cornell, right, Anna?
Yes, that's right.
And Anna is also presenting remotely, and she will be telling us about finding relativistic stellar explosions as fast optical transients. Just take it away, Anna.
Okay, great. I don't see the slides just yet. Oh, that seems to be the end. Is there a way to open them at the beginning?
They are fixing it.
Now that the end has been given away. All right, thank you. Okay, great. Hi, everyone. I'd like to thank the organizers for the opportunity to tell you about our efforts in the last few years to find relativistic stellar explosions using optical time domain surveys, and to highlight the role that Gemini rapid TOO spectroscopy has played in our program. So I'll start by providing some very broad context. We have this traditional textbook story that the fate of a star depends primarily on its mass. The story goes that massive stars end their lives by developing an iron core. This collapses, and neutrino irradiation causes the star to explode as a supernova, which has a characteristic kinetic energy release and ejective velocity. The mass also determines the nature of the corpse, the compact object remnant. But recent developments, particularly in observations of the explosions themselves, which I'll generically refer to as transients, are forcing us to confront the fact that the story needs to be rewritten. that the fate of a star depends obviously not just on its mass, but also on a host of parameters and processes that we really don't understand very well. Supernovae themselves can have a huge range of kinetic energies and ejecta velocities. There are growing observational hints that a significant fraction of stars shed a significant fraction of their mass shortly prior to core collapse, and we'd like to know why that is. We'd like to know what parameters determine whether a star will explode at all, whether it will collapse directly and form a black hole, or whether it will explode completely, leaving behind nothing at all. And we'd like to know the relative contribution of different mechanisms for causing the explosion. There's not just neutrino irradiation. There can also be fusion, or what's called a central engine. That means tapping into the rotational spin-down power of a newborn neutron star, or the accretion power onto a newly formed black hole. And finally, we'd like to know why some massive stars do weird things, such as make gamma ray bursts. And answering that ultimately comes back to the basics of stellar evolution. So that brings me to the focus of my talk, which are extreme endpoints of massive star evolution. By far the most famous example are long-duration gamma ray bursts. We've heard a bit about short-duration GRBs, which are thought to come from compact object mergers, but long-duration GRBs are thought to come from the deaths of massive stars. So in the traditional GRB model, the core of the star collapses and forms a compact object. Accretion or rotation powers a relativistic outflow that tunnels through the star, breaks out from the surface as a jet, and escapes into interstellar space. The jet collides with ambient gas and dust, and this produces synchrotron radiation, which we call the afterglow. We can observe the afterglow all across the electromagnetic spectrum, from X-rays to radio waves, and we can detect it out to large angles away from the jet axis. But it's thought that in order to detect the prompt burst of gamma rays itself, the GRB, we have to be looking directly down the barrel of this quite narrow, few degree wide jet. Now, GRBs, as I've just described them, are a very well-established phenomenon. They were first discovered half a century ago, and thousands have been discovered since then by satellites such as Swift and Fermi. But these satellites aren't so good at pinpointing the location of the burst. For that, you need to follow up and detect the afterglow counterpart. And today, that stage is also very routine, thanks in particular to Swift. By measuring the afterglow, you can measure the redshift to the event. We detect these all the way out to the other end of the universe. And you can also study the properties of the environments in which they explode. And at this point, there's a general consensus that long GRBs have a preference for low mass and low metallicity environments. However, there's a long-standing problem in this field that GRB satellites cannot solve, and that is that the exclusive selection of relativistic explosions via gamma rays imposes a very strong selection bias. There are a lot of reasons to think that the observed GRBs are just the tip of the iceberg, and that actually most relativistic explosions are faint in gamma rays and so are missed by GRB satellites. So here are some examples. First, off-axis GRBs must exist if our basic model of GRBs as collimated explosions is correct. Second, a jet with too many baryons, which we could call a dirty fireball, would only be able to attain a moderate Lorentz factor, much lower than a classical GRB, and would therefore not produce luminous gamma rays. And third, a jet that fails to escape the star, a choked jet, would also not produce a luminous GRB. And it's very important to try to find these classes and measure their rate, because ultimately that is how we can answer important questions, such as the contribution of these systems to the heavy elements, particularly our process elements, and to what extent they play a significant role in actually causing these stars to explode as supernovae. And today, we're finally in a position to answer these questions, because within the last few years, it's become routine to discover relativistic explosions outside the gamma ray band, and that is using optical surveys instead of gamma ray satellites. So this plot shows the phase space of optical transients. The x-axis shows the transient duration, and the y-axis shows the peak luminosity. Normal supernovae are down there on the bottom right. And today I'm going to tell you about about two emerging classes: optical afterglows, which are shown at the top, and a mysterious group of objects shown in the middle, whose prototype is this transient AT2018 COW. For both of these classes, rapid TOO spectroscopy with Gemini, which we get often within just a day of the explosion, has been really critical. Okay, so before I tell you about these transient classes in more detail, I want to walk you through the discovery process. So much of the work that I've been doing is with the Zwicky Transient Facility. This is an optical time domain survey run at Palomar Observatory in Southern California. We use a set of 3 telescopes. The smallest one does the all sky survey and is responsible for the transient discoveries. And then the bigger telescopes are used for classification and more detailed characterization. This is 1/64th of a real ZTF image. Its full field of view is 47 square degrees, shown here compared to various other optical facilities. And it's really this large field of view that makes it particularly well suited to the pursuit of these rare and fast evolving events. So in practice, on a given night, ZTF takes images as part of several different surveys down to a certain limiting magnitude. We're currently doing the entire night sky every 2 nights in 2 different filters, and about 10% of the sky multiple times per night. The process of finding transients is fully automated. ZTF takes a new image, subtracts an image of what the sky normally looks like at that location, and every 5 sigma change results in an alert, which is just a packet of code, and we're using the same format that's going to be used by Rubin. This is very fast. So from the close of the shutter following an image to the availability of alerts for that image is just about 8 minutes. Okay, so to make this more concrete, I want to walk you through the alerts from one particularly interesting night in the history of ZTF. On this night, there were about 181,000 alerts. This might sound like a lot, but actually on a really good night, it'll be about 500,000 alerts. These come from about 150,000 unique sources. Applying some basic cuts, I'd estimate that about 76,000 of these are sort of truly astrophysical. And then we typically require that each source have 2 or more detections separated by a minimum baseline of 30 minutes. And that's important to get rid of moving objects such as asteroids. Then zooming in on those, we typically apply some cuts to try to remove as many stellar flares as possible, even though, of course, those are also scientifically interesting in their own right. And then we focus our attention on the newest events. And so by young here, I mean that the transient was detected for the first time this night with a non-detection or upper limit the previous night. And this is a very manageable number for humans to investigate. And on this particular night, there was one transient that looked like an excellent candidate for being an afterglow. So here's the subtraction. There's no known counterpart, optical counterpart at that position, down to a very faint limiting magnitude, which is what you expect for these sort of cosmological events that are occurring in sort of low mass dwarf galaxies. And indeed, this turned out to be what looked very much like an optical GRB afterglow at a redshift of 1.063, except that it had no associated detected GRB. Its nature as a relativistic explosion was really established first by Gemini. We got a spectrum with Gemini South a little under a day after the ZTF discovery through our rapid TOO program and measured the redshift by identifying a set of absorption features in the spectrum, which I'm zooming in on in the figure. And I just want to emphasize that these observations are highly time sensitive. This transient was 19th magnitude at discovery, and every night after that, it faded by about 1 magnitude per night. So now that I've walked you through a sort of concrete example of how this works, I'll just highlight some of the results from this program from the last few years. ZTF has found 11 afterglows in the last few years. The figure on the right shows their optical light curves with time and days on the x-axis and magnitude on the y-axis. The shaded region in the background is a compilation of afterglows that were found in targeted follow-up observations of swift GRBs. And then I'm overplotting just a subset of the individual ZTF events. So you can see these are extremely fast events. To my knowledge, these ZTF afterglows are the fastest optical transients to be discovered first in the optical band. And their discovery represents significant progress. So prior to ZTF, only 1 afterglow had been found with an optical survey and successfully followed up to get a redshift measurement. But with ZTF, we now have 8, of which half had redshifts measured through Gemini TOO observations. This really represents the first afterglow sample that was selected outside the gamma ray band. And so it's surprising, or at least surprising to me, that of the 11, 7 turned out to have a detected GRB counterpart. And what this suggests is that these optical searches we've been doing are finding, at least for now, a very similar population to gamma ray searches. And it also implies that at least sort of fully successful relativistic jets are actually intrinsically quite rare. In addition to afterglows, so it's very exciting to find afterglows, but that is a population that we knew existed and expected to find. There have also been new and unexpected classes of relativistic explosions that have emerged in the last few years. So AT2018 COW, or the COW, was an optical transient discovered by the ATLAS survey in 2018. At 60 megaparsecs, it was by far the nearest example of a mysterious class of objects, which are sometimes referred to in the literature as fast blue optical transients. The big surprise here was that it had radio and X-ray emission that was extremely luminous, rivaled in luminosity only really by gamma ray bursts, relativistic events. And this suggested that it too was similarly powered by compact object activity. So the plot on the right shows the radio light curve, or it's actually the millimeter light curve at 230 gigahertz. And you can see that it's orders of magnitude more luminous than that of regular supernovae and actually comparable to low luminosity gamma ray bursts. Since the discovery of 18 COW, we've been looking for additional similar events in the ZTF data. In the past, before ZTF, most of these objects were identified through archival searches, and that made it impossible to spectroscopically classify them. But today we can discover transients when they're young and follow them up before they fade away, thanks to flexible facilities like Gemini. And through this approach, we've discovered dozens of FBOTs, spectroscopically classified them, and identified 3 new transients with very luminous radio emission, very similar to 18 COW. The light curve of one of those new events, which we've nicknamed the camel, is shown here on the right. The x-axis is in days. It's along the top of the figure there. And you can see these dashed lines, which are a sort of regular supernova in the literature. And so clearly this event is, first of all, way more luminous. It's a lot faster, and it also has very blue colors at peak, which is what gives these objects their name. Now, the origin of these events is still unknown. A number of possibilities have been suggested in the literature, all of which would be extremely interesting. But I'd say we're still at this stage now when we're trying to build up a sample and measure their volumetric rate, which is a very important number for discriminating between some of these different hypotheses. So to summarize, we have sort of populations of distinct optically selected relativistic explosions that are finally within reach. This has been enabled in large part by the power of modern optical time domain surveys combined with rapid turnaround spectroscopy. ZTF's phase 2, the current phase, is scheduled to run through the end of 2023, and we're planning to make full use of this time to continue building up our sample of afterglows, particularly the ones that don't have any detected GRB counterpart, also these sort of cow-like transients, and possibly uncover new surprises. Ultimately, of course, our scientific goal is to determine the physical origin of these new classes and determine their connection to established types of supernovae. And I want to emphasize again that Gemini has been central to this effort. It's essentially unique in having this combination of this large aperture, which is important for faint events, with its rapid response capabilities, which is essential for these transients that fade within just a few days or even a few hours. And its sky coverage, ZTF routinely finds transients down to minus 30 degrees declination. So both Gemini North and Gemini South have been very helpful for us and for the continuous availability of the instruments. And so with that, I want to thank you for your attention and would be happy to take any questions that you have.
Okay, we'll start with questions from, okay, no questions on Slack. While we are taking questions, I would request the next speaker, one second, Gregory, to come up and get set up. Okay, Jen, go ahead.
That was a fantastic talk, Anna. Thanks very much. As
Gemini director looking at this phase space, I'm just wondering how many objects are you expecting to want to follow up within this 1-day timescale once Rubin Observatory starts issuing alerts? Do you have a sense of that?
Right. So with Rubin, it will depend very strongly on what the choice of cadence ends up being. I'll say, I think the nominal Rubin survey is not ideal for these events because you really want multiple observations per night in the same filter, which is not the kind of plan for the full sky survey. So it depends very sensitively on the final survey choices. So I'm not sure I can comment so much on what the rates will be with Rubin. There are definitely plans to have surveys like ZTF also in the Southern Hemisphere, LS4, Black Gem. So they're even just with the shallow high cadence surveys, there will be a big kind of explosion in the facilities available. It won't just be the current ones. With ZTF, we trigger Gemini about probably reliably once a month. So one could imagine that it would at least be double that. So maybe something like once every week or once every couple of weeks.
Okay, thanks. Once a week sounds doable.
Any question on Slack? No? More questions from the room? All right, let's thank Anna once more.
Great, thank you.
All righty, our third speaker is Gregory Pack from Seoul National University. Gregory would tell us about the GECKO program for follow-up of gravitational wave events. Gregory, the stage is yours whenever you're ready.
Great. Thank you, Monica. And allow me to begin my presentation. Hello, my name is Gregory Pack. I'm PhD student in Seoul National University. My supervisor is Professor Myung-Shin Im. Now I'm going to introduce our GECKO project aiming to find the optical counterpart of gravitational wave. And I will briefly discuss about the synergies between our facilities with Gemini. The gravitational wave, the GW, is a ripples of space-time caused by extreme acceleration of the object. One of the main GW source is compact binary collisions. For example, there are binary neutron star merger and black hole neutron star merger and black hole merger. If this system contains more than one neutron star, then we can expect the kilonova explosion powered by radioactive decay of heavy elements. So we can expect not only gravitational wave signal, but also the electromagnetic wave counterparts from binary neutron star merger. GW17817 is the best and the only example. 2017, August 17, the LIGO and Virgo gravitational wave detectors observed the gravitational wave signal by binary neutron star merger. And subsequently, the satellite also detected the short gamma ray burst, and the astronomers all around the world started to find the its EM counterpart. So 11 hours after, they found it in the massive galaxy NGC 4993. After that, various observations, for example, radio observation and polarimetry and spectroscopy are conducted. Then this historical event opened a new way of exploring the universe, namely the GW multi-messenger astronomy. GW counterpart makes us better understand the GW source. The EM counterpart pinpoints the exact position of the GW source, so we can confirm the link between binary neutron star merger, short gamma ray burst, kilonova, and gravitational wave. We can also constrain the lateral kilonova models by comparing with the observational data. We also identify the GW host galaxy, so it means we can study the environment of binary neutron star merger. And I want to address the third one, the GW standard siren, we can measure the Hubble constant by combining GW distance and with the redshift of host galaxy. But here are some problems that there is only one GWEN counterpart, so it is hard to do statistical approach yet. And next one is there is some degeneracy between GW distance and its inclination. But fortunately, the observational data of kilonova and short gamma ray burst can constrain its inclination. The last one is the fastest early detection is still 11 hours after the GW event. According to the theoretical studies about this, the emission, early emission, the early emission has crucial information about its nature, for example, explosion mechanism and the origin of heavy elements. So rapid identification of EM counterpart is the keys to the success of multi-messenger astronomy. But nothing goes easy, and there are two main obstacles for rapid follow observation. The first one is kilonova is really relatively faint event and it decays very fast. As you can see on the left figure, kilonova has dimmer, fainter brightness than supernova, about few magnitudes, and it decays within a few days. The next one is the localization area is really poorly constrained. The GW17 and 17 is kind of a lucky event because it was close to us and its localization area is just a 30 square degree. But as you can see, most other events have the hundreds to thousands square degree. So it's hard to cover whole area within a few days. So to overcome those obstacles, we need the optimal facilities and observing strategies. So now I'm gonna introduce the GECKO project. The network of telescope consists of 1 meter class telescope. And thanks to globally distributed facilities, we can follow up the gravitational wave event anytime and anywhere. And not only that, we have two secret reference. The first one is KMTNet of CASI, and second one is 7-dimensional telescope. The KMTNet is 1.6 meter telescopes and located in 3 sites, South Africa, Chile, and Australia. So there is an advantage to do continuous observation. And the 7DT is also wide field of instrument. 7DT is the biggest scale of multiple telescope system with 20 telescopes. What makes 7DT special is 7DT has the medium band filter system for low resolution spectroscopy. So 7DT is specialized to identify the kilonova. So why the project name is GECKO? My supervisor, Myung-shin, usually explains like this. This is because the GECKO sticky hands never miss their EM counterpart. And it is also a good explanation, but I think, as you know, GECKO has very special eye because GECKO's eye has a wide field of view and GECKO has no eyelids, so they never close eyes before they find the EM counterpart. So GECKO name is really interesting and cute. So please remember our project. Okay. So there are two strategies to find GWEN counterpart. The first one is galaxy targeted observation. First, we prioritize the GW host galaxy candidates. Then we observe them one by one in order with using the rare field of instruments. And next one is tiling observation. Tiling observation just covers the localization area with the wide field of the telescope, for example, 7DT and KMTNet. I want to talk about galaxy targeted observation more. So if we get a GW alert, then we know the progenitor, distance, range, the localization area. So we within this volume, we select the host galaxy candidates from the galaxy catalog. We use the GREAT catalog, contains the information about the 3 million extended source. After selection, the prioritization is really important. So we use 3 factors. The first one is the position of the host galaxy candidates on the localization area. The next one is distance difference between gravitational wave, the gravitational wave, and the host galaxy candidates. The last one is the most important thing. We use the K-band luminosity as a proxy of stellar mass of galaxy. So according to the simulation result, it says stellar mass of host galaxy has tighter correlation with the binary neutron star merger rate than star formation rate. So the brighter K-band luminosity means the more massive host galaxy, and that means the higher binary neutron star merger rate. So using these 3 factors, we prioritize, we score each host galaxy candidates, then we observe them one by one in order. Next, we have to check whether this methodology is good or not in real world. So we apply it to GW17 and 17 case. So as you can see, there are 40 host galaxy candidates within the localization area and distance range. And we score each candidate. Then as you can see, NGC 4993 has the highest score, the answer of the galaxy. The next, if we observe the 14 highest scored host galaxy candidates, then we can get more than 90% of cumulative score. It means we can do efficient follow observation. So we can learn that a prioritization method works well for at least just this event. And we follow up lots of GW events in observing launch 3. And here is one of the results about the GW 19425, the second binary neutron star merger. As you can see, this event was really poorly constrained. It has, because of the duty cycle of gravitational wave detectors, its localization area is about 7,000 square degree. So, but there is a chance to have the EN counterpart. We follow up this event. We started the follow observation 9 minutes after the GW alert. And we covered about 40 square degree, and we covered 600 numbers of galaxies. It's compared to the 10% of the total number of galaxies. But in the view of score, we covered about 27%. So it means we marginally conducted the efficient follow observation. As a result, we found 10 transient candidates, but most of them are supernovae, and including us, nobody found the GWN counterpart. It makes us very sad, but we can constrain the expected kilonova properties with the upper limit, the depths, and we can check our facility power. Here is a brief synergies of Gecko and Gemini. Gecko is kind of a point man to filter and select the transient candidates. After that, Gemini will plays an important role as a confirmation of transient. So we have lots of systems, data reduction pipeline, and the classification of real and bogus signal on the image. In that method, we use the AI technique. And after that, we classify the transient type using the color, brightness, and decay rate. After that, Gemini will confirm its transient type. In the view of rapid follow-up observation, it will confirm and characterize the early light curve of the GWN counterparts. And in the view of long-term follow observation, it will characterize the late phase light curve of kilonova. And it also, after the kilonova is totally disappeared, we can study the host galaxy properties, for example, the star formation rate, stellar mass, and redshift. So the next gravitational wave observing run is March 2023. And here the expected information of the expected GW events. 50% of binary neutron merger events will have the 30 square degree of localization area, and most of them will emerge within the 117 megaparsec. So as we can see in the result of GW19 425, our facility have enough power to cover these events. So we expect more than 2 early kilonova in the first semester in 2023. So here are some take-home messages, and I am Gregory Peg again. I'm the only graduate student who want to looking for the GW counterpart in Korea. So welcome you any comments and blames and questions. Thank you.
Great talk. Questions? On Slack? Okay, I have a question. Can you comment on the advantages and disadvantages of the two strategies, tiling versus
Galaxy
targeted
observation? Great. According to the recent observation, tiling observation really powerful for the fully localized GW event. But we have also the narrow field. We have lots of narrow field of telescopes, so we can leave them. So we have to use all resources. So we adapt both strategy on every GW events. So yeah.
Some questions on Slack. Oh, great.
Is it on? Yes. Okay. When you were doing the rates calculation on the second to last slide,
Great.
the rates,
Great.
the number of kilonovae you might find.
Oh, I see. Yeah.
So I was just wondering, when you calculated that, did you take into account how often all the detectors would be on? So does that number take into account that the detectors are off and they cycle through?
You mean duty cycle, right?
Yeah.
Actually, this number is from the paper of gravitational wave detectors team. I mean LIGO. So I think they consider the duty cycle, but I have to check whether it is right or not. So thank you. Thank you for your comments.
Anything on Slack? Okay, let's give another round of applause for Gregory. All right, so our final speaker for this session is our own Brian Miller. And Brian will be talking about the next generation time domain astronomy at Gemini. Brian, whenever you're ready.
Okay, thank you. So as we've seen from the very interesting talks this morning, due to the dominant Q mode of Gemini, we've always done a substantial amount of time domain astronomy. So historically, as you can see from the plot here, we've typically observed about 15 to 25% of the time observed in band one as TOOs, or targets of opportunity, which are observations where the target is not defined at the time of the proposal. And this leads to max target opportunity rates per night of 1 or 2 events, which is relatively easy to handle, but the process is rather manual. is not as efficient or capable as it could be. And in this new era of time domain astronomy, with all these new large surveys, as we've heard, ZTF, in a couple of years, we ran an LSST in the various MMA facilities. For example, LIGO starting 04 next year. We must be prepared for a higher rate of targeted opportunities. So in this talk, I'm going to give you an update on improvements that are underway so that Gemini can reach a strategic goal of being a premier time domain follow-up facility, as well as protecting and make it easier to do all the non-time domain observing that we need to do. So to put this in context, I want to give another view of the time domain follow-up system the community is putting together. On the left, we have the surveys and facilities that are generating alerts and streaming them over the internet. Those are collected by the brokers, such as Antares that Monica mentioned, which catalog and classify them. Then in the middle are the science teams, which use systems such as these TOMs, the target observation managers, to collect the filtered alerts that they get from the brokers, do prioritization, and then submit observations to the facilities on which they have time and collect back the data for their analysis. And this is where we find the Ion network. So I'm going to be focusing on the middle and right parts of this diagram, extending on what Monica showed. So a little bit about instrumentation. Obviously, the facilities have to have instrumentation that are available conveniently. In this context, I want to emphasize that basically all the Gemini facility instruments can be used for TIOs, also a lot of the, especially the long-term visitor instruments, but it's really the workhorse optical near infrared instrumentation will be the most useful because it's on a telescope most of the time. So this gives a view of the likely instrumentation suite from the mid-2020s. In the north, it'll be mostly still GMOS and GMOS, and in the south, GMOS Flamingos 2, and in a couple of years, hopefully Scorpio, which will do optical and infrared simultaneously. I should also note that it is possible to use the relay systems for TROs, but you need to put the trigger in a few days early so we can go through the laser clearinghouse process. We're going on these target observation managers, or TOMs, which the teams use to match the targets with their telescopes. These are basically interfaces on top of databases, which will store all the targets. As you can see here, you can do queries on brokers, so you can bring in the filtered objects of interest. And then there are interfaces in the GUIs for doing the observation submissions. And these are in use by a lot of teams who study supernovae, exoplanets, solar system objects, and microlensing. But they're also useful for non-time domain projects, anything that has a lot of targets, or you have a lot of team members that you need to manage. And as has been mentioned, Las Cumbres Observatory has made these really easy to put together using this TOM toolkit. You can actually go from nothing to a configured system that you can start to tweak for your project in 15 minutes. I did a workshop at the virtual science meeting last year, which shows how to do that. So please check that out. So once the observations are submitted to the facilities, they need to be scheduled and observed efficiently. And it's easier to do that if you have a network of facilities, especially with different apertures, which is a reason that my lab is collaborating with Las Cumbres Observatory on EON, the Astronomical Event Observatory Network. It's an effort to develop and promote an accessible, dynamically scheduled system of telescopes. So the main projects activities have been to develop the interfaces to do this, both internal and external. We've used SOAR as a pathfinder, which is now running behind the Las Cumbres scheduler, and we do Q observing on dedicated EON nights throughout the semester. We incorporate Gemini. We've investigated and implemented tag processes to enable the use of the network, and we encourage data pipelining and archiving efforts. And we want to be ready to incorporate new facilities as they come online, such as the Rubin in-kind contributions, the Bronco, and others who are interested. So the EON working group and the Gemini board have discussed for several years the tag processes needed for this. And it's very important that we meet the participant requirements for proposal evaluation. If the use of the network will require multiple proposals. Proposals for Gemini time go to the national tax systems, just like we do now. Companion proposals for the non-Gemini time will need to go to those facilities. For example, the facilities allocated by the CSDC NORLab system, you would apply through the NORLab for US time on Las Cumbres and solar, and you can take advantage of the US Open Skies policy. When we were putting this together, we realized that the AM requirements lend themselves really naturally just to general multi-facility proposals. So that's why in the 22B pit, we put a new AM or multi-facility option in the QA classical proposal tab here. So if you are putting in a proposal for multiple facilities for the same projects, you should set that to yes. And then you have the option of popping up this dialog here. You can specify whether a particular instrument that you're requesting is required or absolutely essential for your project. Obviously, everything you're applying for is important for you, and you're justifying that. But certain of these may be more important or essential than others. Such that if you don't get the imaging that you're going to use to actually find the transients, maybe the whole thing won't be valid anymore. The important thing is that we don't show the TAC any of this information. This is used by the staff internally to track what's going on after the TAC process and during the scheduling, just to avoid any bias in the TAC evaluations. So you should also describe and justify the roles of the various facilities in your experimental design and use for their facilities section. So Gemini, as we've seen with Monica's example, currently works within EON via this plugin that we wrote for the TOM toolkit using some APIs we already have. This program provides interface for both manual triggering, as you see here, and automatic triggering, such as Monica showed, using this very basic API, which allows the submission. It works okay, but it's not as capable as we'd like it to be. And I should mention that the Observatory Archive also has APIs which allow taking and downloading of raw data. So I'm going to show a little video here which shows how this works at the moment. Monica showed how you can do this with the Jupyter Notebook, and this is how the interfaces can be used. So I've imported a ZTF target into my TOM, and I'm checking the visibilities on the different facilities. So this looks good. I'm going to submit the Gemini observation. So I pick a standard TRO template. I'm going to make a grouping. I'm going to set the slit along the parallactic angle. So that means a date. Set the brightness. Setting one has constrained types of notes for the observer. And now the TOM's going off and finding a bad star and submitting the observation. That's done. There's the entry in the database that corresponds to it. I go to my observing tool, sync, and there's the observation with all the information from the TOM, including the slit, the guide star. But the real advantage of this is being able to do this automatically. So here I've defined a browser or a broker query, which will trigger automatically anything that meets the criteria that I programmed in there. So let's found two. One rapid one went to Gemini South, so the pop-up appeared for the observer, so they'll react to it quickly. There's all the information, and I'm going to switch authentication to Gemini North and sync, and there's a standard TRO, so no pop-up there with all the information. And back in my TOM, the database has records of all this, so I can track them and download the data later. The Gemini will better support EON via this Gemini program platform and Gemini projects. The GPP is the core of a new observatory control system. It's the high-level software that we use for operations. Designed to be easier to use, it replaces the current phase 1 tool and the observing tool desktop applications you have to download every semester with a set of web applications communicating with the database in the cloud via some interfaces. It will allow Gemini North and South observations in the same program. There's a lot of automation. It has the constraints we need for an automated scheduler and makes the code a lot more maintainable. So we can get some hands-on experience with this at the workshop later this afternoon. So Explorer, which is the main application for doing program and proposal preparations, will also allow you to find the capabilities that you need without having to go through all the instrument web pages like you do at the moment. So here's one part of it. You can specify in spectroscopy and then enter your science requirements like the wavelength, the resolving power, the signal to noise, and then we put a limited selection. These are the things that we have that will do that science. And as soon as you pick one of those, your observation is basically done. The integration time calculator has been run, so we know how long it takes, and the sequence has been generated automatically to meet that signal to noise. So this is a new way of doing future TROs. You don't have to define the template observations, such as I showed in that video with the Tom. And everything that can be done with Explorer UI can be done programmatically. So the full program information can be accessed for scripts. You can add targets and observations, edit them, and remove them if you want. This figure shows Jupyter Notebook I did last week when I created the GPP database for the list of observation of targets in my program. And I use this line, I created a new target, and there you see it shows up in the list. Another run command, I take that target and create an observation with it, which shows up down there. And using the automation that I mentioned before in GPP, automatically selecting an instrument and then creating the sequence, that's basically done and it can be submitted as a trigger. So again, not necessary to prepare these TRO templates in advance, which can be a little limiting. So we expect to start GPP early science and testing phase, which we call XT, in early 2024. The XT1 phase, we'll start with a call for proposals to do GMOS imaging in long slit, hopefully October next year. We'll be requesting about 5% of the telescope time to do the reasonable evaluation of GPP. We're going to request these proposals. Then do the observing of a set of fixed nights with GPP, do a full end-to-end test, plan out the scheduler, and so that we can refine the system as we go. The XT2 begins. So from then on, we're implementing instruments and modes. And after one is done, we want to try it out. So we'll probably be requesting that people convert existing programs into GPP, and we'll try observing with that. Maybe giving a time bonus as a motivation to try this out. And we expect full operations currently in 2025. And we certainly want to have the system sufficiently developed that we can do Scorpio commissioning before then. So as Explorer gets more developed and we implement more features, we are gradually ramping up the community testing. The workshops at this meeting are a first step in that direction. So the testing will be, just driving it, trying to break it, throwing in questionnaires, doing quantitative tests so we can measure this against the previous system. So come to the workshop this afternoon and let us know if you're interested in participating in this. So Gemini is also implementing this real-time schedule that I mentioned and real-time data reduction as part of the NASA-funded Gemini, or Gemini in the Area of Multi-Dimensional Astronomy project. The scheduler passed its final design review last May, so we're under construction right now. It will do updates to the plans in real time as things change, as TROs come in, as the weather changes, adapting to it as it goes. We schedule Gemini North and South together. As a sort of moving network, this figure on the right shows schedules for Gemini North and South with our prototype scheduler that was done in the same scheduler run and in less than 15 seconds to do both of those. The real-time data reduction is done in the Dragon system that you've heard about in talks by Kathleen and Monica. Just to go over it again, it supports GMOS imaging in long slit. There's quick look for quality assessment is working with telescopes now, and the science quality reduction is in progress it will be released next year along with the needed archive updates. So in summary, Gemini is aiming to be the promote class member of a follow-up network that will consist of these various pieces, the brokers, these times, dynamic scheduling, a range of network of telescopes of various apertures with various workhorse instruments and real-time data reduction. And to do this, we are constructing this new observing system, which will support the follow-up that make Gemini easier to use for everybody. So your involvement is really important. So we build the right thing for you. So please get involved in the workshops, and thank you. And I'm willing to take any questions.
Questions? Okay, go ahead, Ricardo.
Thanks, Brian. I have two questions. The first one is very general. So from explosion to spectrum, what do you think is the weakest link so far? And the second is, so with the TOM, you're sending information to the database and the OT, but do you also get some information back? For example, the warnings from the OT, like I cannot find a guide star, things like that. Do you get it back, or you have to check on the OT?
Currently, no, you don't get it back with the API. That's one of the limitations. You would have to check the OT for that. With GPP, you will be able to get all of that information. The weak link on our side, and once we get the trigger, the problem we're just keeping track. No, we can show the observer responding properly, that they can make a proper decision about whether to know when they need to switch to a new target, is it interrupt or not, and then they have to, in their head, basically switch the rest of the schedule around, and that wastes a lot of time. So there's just a lot of extra excessive mental overhead, which we want to get rid of. So we'll get suggestions, like here's a new event, let's either interrupt now or it come in later, and the plan will just automatically refresh. So you can focus on what we're doing and getting the best data for people.
Hey, Brian. So in the era where we're going to have, instead of now, like there's 10 alerts, 100 alerts, and getting RTOs rapidly at Gemini, is there going to be, like, let's say you get 20 RTO requests in a night? I don't know whether that's even possible in the era of LSSD, but maybe. And if that does happen, is there going to be a ranking system built into the software? Or is that going to be reliant on contact scientists and everybody at Gemini to look at it and be like, okay, we need to do these instead of?
We need to build in all of the policies for that. So we have this policy for competitive TOs to handle things that are trying to do the same target or coming at overlapping times. So we'll have to implement all of that. We'll have to keep track of when things came in and do them in the appropriate order based on the ranking bands and all of that, so that people don't have to take up time thinking about it. That was a big problem with the gravitational wave kilonova. Everyone wanted the same targets, and I imagine there was a lot of discussion going on, lots of phone calls to work out what to do.
Okay, so it's going to be built into the.
To build all that in. Yeah.
Julia.
Thank you for all your work that you've done on this. This is exciting. I was wondering, you were talking about kind of the limitations of the TOM right now, and then you talk about how GPP is going to solve all of these, but of course that's coming after 04 happened in March. So are there any things that you're doing to, patch that, make the time work a little bit better until GPP comes on?
Actually, not planning to do much with the current interface. The more you do with the current system, the slower GPP is. Because it's the same people supporting both systems. So we're trying to do absolute minimum, just get by with the current system as much as possible. As much effort into GPP and get it in place as quickly as possible.
Okay, great. Thanks.
Any questions on slide?
No questions.
Okay, I think we can end our session now. Janice, you have
Yeah, let's give a round of applause to all of our morning speakers. Fantastic talks this morning. As usual, please, speakers, if you have a talk this afternoon, come and test before you go over to lunch. And again, a reminder of the fabulous public talk that we have tonight from 7 to 9 by astrophotographer Juan Ocho. Please bring your friends and we'll have plenty of room. It'll be given in Korean, but we have engaged a English translator. So we'll be able to have it hear it both in English and in Korean. Any other announcements from the LOC looking around the room? Okay, have a great lunch. See you back here in about an hour and a half.
Hi. You have to talk with him. I am not doing anything. I finished. Sorry. Some labs are kind of, I don't think that I'm done, but if you also want to do science, it doesn't work that way.
Yeah, it depends. What's the choice?
Yeah, I did. Yeah, we leave right now.
Yeah. Not everyone believes this.
Yeah.
That's gonna be a problem.
Es que me dijo la Jocelyn que quería ir more about the, que bueno, pero como él es vegetariano.
O una alita de...
Me lo compré en Chile.
Ya me di cuenta que tiene acá en...
No, yo ya le pegué una hostia en
Ay, yo ese mierda.
Paul, are you still on?
Yeah, hey, Jerry.
Se salió la.
Hey, so you wanna practice yours really quick? I can.
Yeah.
It's
Yeah.
pretty easy. I just, oh, don't move the mouse yet. Let me
Okay.
get your slides up. I think that's. Oh, nope, nope, nope.
Sí, se lo dije.
Not quite. Just a second.
Close.
Yeah, okay. Let's go.
Slideshow.
No,
Okay, now you should be able to control the slides with your right and left arrow keys.
Oh, yeah, okay. Yeah, that seems like it works. And can I get a sound check? Is my audio pretty good like this?
Yeah, sounds good.
Cool. Yeah, awesome.
And,
Cool.
and
All
I'll
right.
monitor during to see if you sound quiet, I'll just turn you up too.
Okay, cool. I'm on a headset, so it should be good. Yeah.
All right.
Cool. Awesome. Thanks, Jerry.
No problem.
Hi, Jerry. Could I have a quick test too, please?
Oh, shoot. I think I hit the wrong. Did I stop the share? No, I didn't. Good. Yeah, just a second. Just a second. I need to there. All right. All right, so who's this who wants to test?
It's Venu Kalari.
Oh, you're testing for tomorrow. Oh, okay.
Yes, sorry, yeah.
And just a second, I need
Hi,
to give you.
I'm Venu Kalari.
I need to give
and
you
I'm an
slide
assistant scientist
control.
at
All right,
Gemini
now you should be able to use your left and right
And
arrow
before I
keys
begin my
to
talk,
move slides.
I must apologize. Can you pause slightly my video, please? ambiguous images I that wanted I've to. been abstract. Jerry, could you just pause that? I want to check the In my slides. defense, when we submitted
Well, this
abstract,
is your slide
this
deck,
is
right?
we had just taken speculative yeah, that's what I wanted to test it. Yeah, We okay, weren't that's sure fine. if we I've could, got what I wanted to test. Can you reduce pause it and anonymize close them it, in time please? to present them at the GSM, so sort of to hedge our bets. Yeah. We
Oh, just a second.
put a slightly ambiguous. Yeah, sorry, that's just my talk playing. I wanted to test that whether it was playing that or was it not doing it. Yeah, that's
No,
great.
I don't think it was doing something. Just a second. Let me. Okay. Well, it says Venu is supposed to be controlling the screen.
Jerry, I've tested what I wanted to test. It's fine. It's playing my talk with the PowerPoint, and I want to remove that. I just wanted to see that. That's fine.
Okay, I was just trying to see if it was.
Yeah, just please stop it. Please stop it because it's playing the talk right now.
Oh, okay. Okay.
Yeah,
It's playing the
it's fine.
video
Just
part.
stop it. The video is recorded within the PowerPoint. I just wanted to check that or not, so I can delete the
Gotcha.
video. Yeah,
Okay.
sorry, it was just playing my talk.
I
Yeah,
got
that's
you. It's
fine.
embedded. I got you. That's why I was confused because I was seeing you over there, then I was seeing you on this, and that's because it's embedded in. Gotcha.
Yeah, I just wanted to test that. Yeah, that's fine. It was just started to play my
Well,
talk. Yeah.
thank you. Actually, now this test allows me to be prepared when that happens tomorrow.
Yeah, well, thanks, Jay.
Okay.
That's fine. Thank you. Another quick question. The PowerPoint that's being used, is it like PowerPoint 365 or is it just Google Slides?
I mean, actually, this computer does Keynote, PowerPoint, or Google Slides. We have a mix of all of it.
What version of PowerPoint is it?
I don't know. 10 seconds.
Yeah.
Oh, not help. Uh, 16.63.
Perfect. Thanks, Jerry.
Yep. Okay, who's next? Trying to check how long I get for lunch.
I think it's a longer one today, right?
I hope so. Yeah, the first day I got like 10 minutes.
Oh, no.
Yeah.
Yeah, I guess because you do the checks after the talks and the checks before the next round of talks, then.
Yep. And this time I also had to do talks for the public event that's tonight.
Oh, that makes sense.
109 slides.
I hope that man's gonna talk very fast.
We've got 2 hours, so.
Oh, okay, it's not, I'm thinking it's an hour, so I'm in for slide.
109 for 2 hours.
Okay.
Sorry. Oh, one of them has movie in it, so. Yeah. Oh, I tried to make sure the movie played and was doing stuff. So no spoilers, no spoilers. But 2 o'clock. Oh, that's good. Also, I got more than an hour. Oh my gosh. I feel like yeah. Okay.
Yeah.
Thank you very much. Sorry.
Yeah.
That's right.
I would love to, not yet, thank you. Okay. You're ready to go? I'm just, no. Okay, I can, thank you very much.
Thank you.
Good.
Yeah.
Yep.
Yeah.
Yeah. I guess how low should they go on the 3x3 or
Configurable.
yeah.
I guess like the release is not the replacement capacity. That's what it meant. Behind it, one fast don't get off all the chances.
Right. I mean, if we can push it, I mean, if we could be pushed down to like 20 something in terms of large, that would potentially. But in terms of, yeah, in terms of like speckle. But I think in the IR, actually. Oh, okay. I think Julia is taking.
Yeah.
Hay una prueba, no te preguntamos nada. Le dije, ¿vos sabes? Ya. Sí, pero yo creo que
Stefan is here.
entonces le dije, y dijo,
Dale, dale.
Cuenta como robar.
Sí. I have pasta. I have pasta. Ah, there. Oh, we good? Said you went with Jake? Said you went with Jake? No.
Don't worry.
Can I see? This is like for this kind of thing. Yeah, but this is the match. For this another thing, the 380. Okay. So this is the full. I kind of get you, that you know, means for me like. You know, yeah, but did you have a lot of cases when you were trying to say how would you want our yeah, they're lucky, yeah. Because when you or you were in the school you learn more. Oh, okay. Sometimes I'm to raise like Chinese, they are getting right because the bunch of the like
That also turned out. That's it.
I'm not saying all this. Oye, nomás que quiere construir esto,
Give me a second.
44.
Just the size you want to see there. How much of a text? I went through it before lunch. Yeah, ones where guy moves and it's got a big video. Yes. Yep. Just taking the. If you like, I can still show you, but I fully tested 100 and
1 a.m. Yeah, from the end of the night.
I figured I had a pretty long lunch break, so I might as well.
It wasn't in tomorrow. Saturday and Sunday. Just sorrow. Tomorrow.
Oh, I'm sorry. No, so I had to had me break down equipment for the UCG with 4. So
No, this hurts.
yeah.
Do you have a room? Oh. You can talk to Crystal or something. The Crystal makes the. Makes the. Your time? Yeah. So yeah, it's now running bright thing.
Tell me don't ever bring up that. That's what I do.
I like the ghost of Christmas past, present, future, the dinging of the clock.
Oh yeah. I just heard the
Oh yeah, yeah, yeah. I am. So I will keep an eye on that. And if there's any questions. Yep. And then for the virtual talk, I will. Yep. Derek.
I'm sorry. You can do either way.
We could start to take our seats and get ready.
You're live.
Okay, shall we get started? Welcome to the afternoon session here. Today's topic is adaptive optics and all the great things you can do with it. We have a number of exciting talks ahead. We're going to start with Stefan Gileson from ESO and Max Planck Institute, excuse me, who's going to show us what interferometry can do coupled with adaptive optics to probe the center of the galaxy. Take it away.
Yeah, thanks a lot for having me. Thanks a lot for the invitation. I'm actually a user of ESO telescopes. I'm one of the power users, so to say, because I'm traveling roughly like 3 to 5 times a year to Parnell to observe there. So I'm going a bit further north than the Gemini South telescopes. And what we do there is interferometry. Yet I'm here to report also on observations, which we did with Gemini. And you'll see in a second why actually we very much wanted that. It's probably everybody is aware of these beautiful observations, which adaptive optics have given to us from the center of the Milky Way. You can see here a very simple technique, namely you take 16 images each a year apart, you plug them behind each other, and you can see beautifully how the stars are revolving around that red cross, and that red cross, of course, marks the position of Sag A star, the supermassive black hole candidate in the Milky Way. The star, which is labeled S2, is you'll see is the most important one, and everybody knows, of course, that this was given to the led to the Nobel Prize. The experimental part of the 2020 Nobel Prize was given to Andrea Ghez and Reinhard Genzel, and Reinhard Genzel actually pays my salary, so I'm part of his team. So you can see here, I was invited when he was given the medal. It was not in Stockholm, it was in Bavaria, in Munich. The Swedish ambassador spoke on behalf of the king. Nevertheless, we are invited to go to Stockholm end of this year. So let's see if that will happen. So let me start by saying that actually in the galactic center, it's really observationally, it's source confusion, which is the limiting factor. If you don't use adaptive optics, your telescope is as good as lambda divided by the atmospheric coherence turbulence cell size, R naught, the Fried parameter. And this is typically 40 centimeters. So your resolution is even at an 8-meter telescope limited to something like 1 arc second. Doing adaptive optics, you can improve here by a factor around 20 or so, because then you get sharp across the aperture and you get a resolution of around 50 to 60 milli-arc seconds. However, if you are able to do interferometry on parallel, or if you could also do it on Mauna Kea, you have baselines of hundreds of meter, 120 meter in the case of parallel. And you see, you gain another factor of 15 compared to the 8-meter. So this is, of course, a huge, huge factor. So for almost 20 years, we had 2 AO workhorse instruments at the VLT. One was NACO, operating from 2002 to 2019. And one was Symphony, operating from 2003 to 2019. And you can see here the problem. The schedule when to recommission new instruments was not taking into account COVID. And that's why we had a data gap, and that's why we reached out to Gemini, whether we actually could not use their telescopes in 2021. And you'll see how beautifully that has worked. But let me first talk a bit about our interferometric project. So here you can see the mountain parallel. And one way to think of an interferometer is, I mean, okay, we have beautiful 8-meter telescopes, but how beautifully would look that mountain if it were completely covered with a mirror, a 130-meter mirror? And if you have such a mirror, it's obviously you get a very sharp image. And if you now start dropping a bit of black paint onto that mirror, it will not matter, right? A bucket of black paint here and there will just look like a bit of dirt on that mirror. And you can put more and more black paint on the mirror until you have only 4 apertures left. And the only thing which you need to do is you have to combine the light of these 4 apertures in a way as if they were a single mirror. And that's the technique called interferometry. What it gets you is typically fringes, and these are characterized by a phase and the visibility. And these phases and visibilities vary as a function of your baseline length. And the baseline length, again, is also given by not only the baseline, but also the wavelength you're observing. So by observing a different wavelengths, you can also change the wavelength. And you can see here a beautiful example of such a signature. You can see very, very strong signatures, and you can describe actually the signatures you see here with a simple model, with a binary model. And for that, you have source parameters, maybe, for example, a separation vector, a brightness ratio, the source colors, and you need to know a bit about your instrument, so like bandwidth smearing or the injection per telescope, so telescope-dependent parameters. However, if you do that a few times in the night, you get more and more of these things, then you can actually collect enough information that you can do the Fourier inverse transform, and you can reconstruct actually an image. So typically with one night of data, one can reconstruct the image, and here you can see how that model actually looked like. It was the star S2 and the source Sag A star itself. The elongation of the sources is the interferometric beam. This is sort of, say, the price one pays for the fact that our we don't have a full aperture, we don't get a nice beam, we get a dirty beam, so to say. And one really should say that laser guide star adaptive optics is really 15 times less sharp. So it sounds great to do laser guide star adaptive optics, but it's not particularly sharp in that sense. And even if you go to the next generation telescopes, the 30 to 40 meters, they are still a factor 3 to 4 less sharp than what interferometry does now routinely. And you can see here the stellar field as it looks like with adaptive optics on the left. In the middle, you can see a zoom in onto the central region where Sagittarius star is the circle and S2 is the star up. And on the right-hand side, you can see the same field, how it looks with interferometry. And it's obvious that no way that you can distinguish all these individual stars with the adaptive optics. It's maybe also interesting to compare the UV coverage, so how well we actually sample, how well we synthesize a mirror. And we compare it here to the EHT, which of course you have seen the Event Horizon Telescope image. And you can see we have only 6 baselines for telescopes, much less than what the EHT was using, but we are actually using the full K-band. So that is from 2.0 to 2.4 microns. This is a 20% bandwidth, so to say. And this is of course unheard of in radio astronomy. And that's why actually our UV strikes are not only dots, but they're actually really bands, as you can see. And you can imagine that this doesn't give you too bad of a coverage. Here you can see the orbit which we've reconstructed. You can see that we've started in 1992. That was up here. The star went down through pericenter in 2002. Then adaptive optics came along. That was what we traced all the way here. And in 2016, the first interferometric point came, and then 2017, 18, 19, 20. In 2020, we got 1 data point. I recall very vividly that I managed to go home 1 day before actually the lockdown came. My family arrived also the same day from their vacation. We were all back home, next day lockdown. But the most important point was, of course, the data point was there. And you can see that in 2021, then we switched to remote observations. And here you can see also our latest data from 2022. So the star has a period of 16 years, semi-major axis of 125 milliarc seconds and eccentricity of 0.88. And the typical uncertainties are in the 0.2% regime. So if you think of the angular momentum or energy of the star. And we can also precisely say that the pericenter was on the 19th of May in 2018. And here's the radio velocity data for the star. You can see that the dense sampling actually started after the orbit was discovered. And since the discovery of the orbit was right after pericenter, the first 2 data points obtained with the Keck telescopes, they were sort of at random points. But then one realized that it's important to trace this star. You can see how beautifully we were tracking this star. But you can also see that in 2019, the Symphony series ends. And this is, of course, where the Gemini data points come in. And these points, I'll show later a little bit how we obtained those. The 2022 points are now from the successor instrument ARIS, which is being installed right now. So this is commissioning data. S2 is very fruitful. There's a plentitude of stars, but S2 really stands out. S2 is that orbit here. It is the second shortest. It's not the shortest period. The shortest is 12. But it happens to be the brightest star, so it's actually easily accessible. And we've done plenty of things. For example, you get a geometric distance. You can think of it, we measure a proper motion and we measure a radial velocity coupled with a simple geometrical model, namely an orbit. So you get a very direct distance measurement because one is measured in milliarc seconds per year, the other in kilometer per second, and milliarc second to kilometer is the distance. We've measured the relativistic redshift of the light leaving the star. We've seen the precession of the star, the relativistic precession, and we can give limits on the extended mass. On the test of the equivalence principle, I skip for the time reasons. So at closest approach, S2 actually reached 8,000 kilometers per second. Compare that to Earth motion, 30 kilometers per second. And we know that it's mildly relativistic, 2.5% speed of light. But the transverse Doppler effect should show up and the gravitational redshift. Those 2 terms are actually identical in size for a Keplerian orbit. And if I can show you now how the residuals to the Kepler orbit look like. And you can see here beautifully the redshift signature, which showed up as a 200 kilometer signal. And again, you can see why in 2019 we were reaching out to Gemini, because we really wanted to get those data points here on that side. And you can also see that the new instrument ARIS is now starting to deliver, hopefully, data again. The effect is measured with around 25 sigma, and so that looks much more here in this plot, but this is because you can think of finding a different Kepler orbit which mimics a bit that signature. So that was something which was easily realized in 2006. At the time, people proposed either use 2 orbits or use hilarious good astrometry, and we did the second thing. We used simply very good astrometry. Also, the Schwarzschild precession is detected. So this is at 8 sigma. So this is the effect that the orbit is precessing progressively. You can see it in this plot. You just have to zoom in a little bit. And you can see here that the star has changed its orbital trace. And here you can see actually the actual data. You can see that the Kepler orbit by now is largely excluded. And the star has really changed its orbital orientation at pericenter. What is new since 2021 is that actually we're tracing more stars than only S2. So we have actually, you can see here the field in March, May, June, and July observed with gravity, and you can easily draw again like this beautiful orbits through these individual data points. And it happens, of course, that these stars were known to us, so we had previous coverage for those stars, and then you get very quickly beautiful orbits. And you can see here, besides S2, the star S29 seems to be also very interesting. It's also coming close, and it went through pericenter in 2021. And if I show you now the radial velocity curve, you can see here how deeply that star should dive. And it actually did dive very, very deeply. You can see here this -4, -5,000 kilometers per second. And those 2 data points, they are from Gemini. So that was the actual reason why we wanted to be in 2021 at the telescope. So let me just report a little bit on using Genius at Gemini North. So I'm a user of ESO, and I have to say that compared to observing at an ESO telescope, where you have the feeling to be in a factory of science, it was very refreshing, warm, and welcoming to observe with Gemini. I really liked it. Where's Jen? Is she already back from lunch? Very, very nice to do that. Very direct. You just zoom into the observations. You talk to the people. You see everything they also see. Who is observed with ESO telescopes here in the room? You recognize the difference in how things are done at the different telescopes. So I found it very, very nice, and I'd like to say thanks a lot for the hospitality. So here's our slit, which we wanted to put. We wanted, of course, to put it on S29, on S2. And it happens that if you do the slit orientation in that way, you also get a bright star here, which you can use for alignment purposes. And you get a moderately bright star also here, which is a well-known late-type star, for which the radial velocity is very easily measured. So this is the best slit orientation we could think of. Here's then the finding chart. You see that actually there's a very bright star, which you miss with the slit. And then you go to the telescope and hooray, you get your acquisition image. And it looks like just the image before, just rotated by 90 degrees. You have to figure out that. Then comes the through slit image, and you can see here the little dots, which are here in the through slit image. This is S2 and S10, so they are there. Here are then the reduced spectra. So this is the whole stack of a night, which we obtained. And if you zoom in a little bit, you can see here, this is the S10 spectrum, and this is the S2 spectrum. The wavelength calibration, I didn't even know if there was a pipeline. I think I just did it myself. Very linear relation. You get this thing, and then you can check things. For example, on the star S10, it has CO band heads, so at 2.3 microns, you get these sharp features which you can easily identify. Here's all the symphony measurements before, and you can see that grossly things seem to work out for also for that star. Notice the scale here. This is only a 50 kilometer per second difference. So S10, here's the Gemini points. For S2, you can see here the spectrum of S2 also works as expected. You've seen that already. There was another star in the slit, S24, also here, CO band heads. And also that star is interesting. It goes through pericenter next year, and it started already curving its radial velocity in 2021. So it's also important to do. And of course, here you can see the spectrum where the bracket gamma line of S29 is. So you see, it's exactly, we didn't overexpose. You needed that integration that is maybe, I don't know if you would trust the line, but of course we had a strong prior where the line should be. Having several orbits, you can then do, of course, a more involved orbit fit. So you then have 7 parameters for the black hole and 6 for each star. You get a huge parameter space, but in the end, you get very small error bars on the level of 0.5% or so. And this really should be said that it's not only S2, it's also S29, which contributes, because also that went very far away in radial velocity, and this gives you a huge lever arm on this plot. And if you put it into context compared to what was done before, you can see here that, of course, this factor 15 in resolution translates into an accuracy here in this plot. We continue as we speak, so we have more stars. You can see here compilation of 2022 orbital traces. S38 is going through pericenter this year. So this is this guy here. S24 will do so next year. And for example, we can conclude from that 99.9% of the mass of such a star needs to be inside of S29's apocenter, which is 100 AU, so Neptune orbit or something like that, which means there's at most a 4,000 solar masses, which could be in any sort of extended configuration. Think of a sea of neutron stars, think of dark matter or something. So we are really probing the black hole nature here very, very well. How far can we get? Well, if we have a star which would come 10 times closer than S2 over 10, then lens steering precession should be in reach. And this is our medium-term goal. So the spin of such a star, it probably requires ELT spectroscopy. We need the big mirror to go down to these faint levels, and the interferometry, maybe another 2 or 3 magnitudes fainter than what we can do now. We're working on that. Even longer term goal would be the no-hair theorem. If you look at the equation of motions, there's then at some point the quadrupole moment in there, and the quadrupole moment relates to the spin of the black hole in general relativity. So if you measure the spin, you can predict the quadrupole moment. If you then can measure it, you can have a check, and this is a first check on the no-hair theorem. So essentially what you need for that is radial velocities with 100 meter per second uncertainty. Currently we are at 7 kilometer per second. And then finally, let me just also report, since the EHT result came out. So in the infrared, such a star itself is a flaring source. Here you see 1 hour of L-band data, and you can see that this outburst occurs from time to time. One is not able to predict that. Here, adaptive optics data on the same scale, interferometric data, you can see these outbursts. And the speculation really is that this is an analog to solar flares happening on the accretion disk. And if you do simulations of these flares, you find that they actually astrometrically revolve. And that signature should be in the regime of the gravity astrometry, which is a few 10 microarc seconds. And you can see here our proposal from 2006, and here an observation in 2018. And if I overlay that now on the EHT image, you beautifully see that indeed we are seeing things revolve on the right scale. And in 2022, you see here 1 example of a flare which we've just observed, still working on that. Unfortunately, however, we know that such a star is not showing us its spin, but the angular momentum vector one sees in these flares is actually the one of the material feeding it. So you see the spin of the accretion disk, and that is determined by the inflow of stellar winds. So it's not the spin of the black hole, which we can measure in that way. And with that, I'd like to thank you for your attention. And thanks, of course, to the whole Gravity team. You see, it's a huge instrumental team behind this work. Thanks a lot.
Questions for Stefan? Do we have questions on Slack? Well, let me start then. This is a fabulous result, and you showed the power of angular resolution, the power of tracking the orbits over time. It looks like you've got enough light, but to go to the next step, which of the 3 is the most important? More resolution, more photons, or just more time to track the orbits?
Well, in the end, I think patience beats everything. Yeah. And that's also, it's actually very difficult. You might know this from NSF funding. If you need a continuous flow of time or money or anything, it's always hard to convince that after 6 years you need year number 7 and then again year number 8. But for these time series measurements, that's actually very hard. And ESO has this model of guaranteed observing time. I don't know if you implement this in Gemini. It's very powerful because that's where we essentially can say, okay, we sell our instrument to ESO and we have the next 10 years of data guaranteed. And that takes away a lot of stress. Without that, we wouldn't be building instruments, I have to say. And instrumentally, I think it's clear. So for the what we're actually doing is to equip all VLTs with laser guide star adaptive optics now, so that improves then the adaptive optics. Then you get more light into the interferometric fibers, and that hopefully brings us deeper in the interferometric images. And once you pick out a star which is close to such a star, it should be very easy to do spectroscopy on it, because if the star is physically close, it will be moving very fast, which means the Doppler shift will be plus 10,000 or minus 10,000. There will be no confusion issue,
yes,
because it will be moved away so quickly and it will change quickly. And the diameter of the telescope should, of course, allow us to go down to 22nd, 23rd magnitude. In addition, we might, so currently we're seeing O and B stars, and we can go down the main sequence. And as soon as we reach F or G stars, we have late type spectra, very rich spectra, which are much easier to do spectroscopy on than these B stars with the broad lines. So our limit is actually the line width of S2. It's not the instrument.
That does depend on having a normal IMF in the center of the galaxy.
Yeah, okay.
We'll find out.
We'll find out that, yes.
Any further questions for Stefan? Do we have time for one more? With the ELT, if I remember, the top of the mountain is pretty much filled by the telescope. Are there any interferometric options with ELT, or is there simply no room to build outriggers or some way to increase over the?
No, I don't think so. Also, budget-wise, of course, it's the ELT is such that it's self-contained. And the mountain itself, Amazonas, is 35-40 kilometers away from Paranal.
Yeah,
that's too far.
Yeah.
So I think it would be more realistic to build a fifth telescope on Paranal, a fifth big one. But still, I mean, each of these telescopes is $500 million or so. It's not so easy to find it when you want to build an ELT. So I think, but also ESO realizes, of course, that interferometry in some sense is the life insurance for Paranal, because that's worldwide so unique that you will not give up on that, even in the era of the ELTs.
Great. Well, thank you so much. Let's give another round of applause for Stefan. All right. So our next speaker is Julia Schwarwachter, who's going to talk about the next generation adaptive optics for Gemini, I believe, in fact, the Gemini North adaptive optics system. And I will give you the 5-minute warning.
Yes, yeah. Thank you. It's working. So thank you. I'm Julia Schwarwachter. I'm a scientist based at Gemini North, and I'm now talking in my role as project scientist for the GNL project. I'm actually filling in for Gaetano Sibo, who is the project PI. So GNL is the project to bring a new Gemini North adaptive optics facility to the telescope. And it's part of the GEMMA program, which we have heard already about earlier during this conference, which is the Gemini in the Era of Multi-Messenger Astronomy program funded by the NSF. And the major goal of this program is to provide or to strengthen Gemini's leadership role in high spatial resolution astronomy as well as time domain astronomy. So GNL is really the goal to have a high spatial resolution and wide field adaptive optics facility for near-infrared science at the Gemini North Telescope, which then will support multi-messenger astronomy and time domain science, as well as a wide range of science cases, and particularly in view of synergies with the James Webb Space Telescope and also Rubin Observatory's legacy survey of space and time. So GNL will replace the existing Gemini North adaptive optics system, which is aging, which is Altair. And it can also make use of course, the excellent side characteristics for adaptive optics that are available on Mauna Kea. It's particularly focused on being fully integrated into the Gemini Q operation scheme, which is of course important to have the system available on a basically nightly basis for especially time domain support. And while GNL will be a facility at the telescope, which is in principle available to any suitable backend instrument, it will also, it is particularly designed to support its first light instrument GEOMOS, which is a Canadian-built TNT Pathfinder instrument. And we will hear much more about GEOMOS in the following talk, which is given by the GEOMOS PI Sivanandam. But I will give a brief introduction to GEOMOS in a few more slides. And finally, also, I should mention that, the GNL project also will provide a path towards a future adaptive secondary mirror at the Gemini North Telescope, particularly through the laser guide star facility. And we will hear more about that project also in this session. I think the last talk of this session by Paul Hurst. So this is a very basic layout of the primary modes that are planned for GNL. GNL will use 4 laser guide stars. The first mode is a narrow field mode in which the laser guide stars are close together to provide a higher performance correction over a 20 by 20 arc-second field of view via laser tomography array. And GNL also plans to have a wide field mode in which the lasers are moved further apart to provide a more moderate correction over the full 2 arc-minute field of view that is available to the array system, and then using a ground layer adaptive optics mode. So I briefly mentioned GEOMOS, and this is just a very brief introductory slide, leaving more of the details to Zurish's talk after this. GEOMOS is an adaptive optics-fed multi-object integral field spectrograph, which will particularly make use of a multiplexing advantage by using up to 4 deployable IVU that can be placed within the 2 arc-minute field of view that's available through the array system. And the particular feature of GEOMOS is that it will use, in addition to the array correction provided by GNL, it will use a multi-object array mode for each individual IVU to enhance the spatial resolution for each individual IVU in this 4-arm mode. And I should also mention that GEOMOS also will host a near-infrared imager, which has an 85 by 85 arc-second field of view, basically filling the square within the 2 arc-minute field of view circle that's available to the instrument. So just to briefly describe how GNL will work in conjunction with GEOMOS, how the 2 modes will be fed into the GEOMOS options. So basically the GNL wide field mode will be used specifically for the GEOMOS spectroscopic mode, where the 4 deployable IVUs are used as deployable IVUs in the field. So then GEOMOS will in addition use the multi-object array correction for each IVU to enhance the compensation of the beam for each individual IVU. And also, of course, the wide field mode will also be available for the imager to obtain near-infrared images with a more moderate wide field mode correction provided by GNL. For the narrow field mode, GNL will directly feed GEOMOS. That's the plan, where the IVUs are basically tied together in the center of the field to form a kind of super IVU in the center. And this will directly benefit then from the laser tomography array correction over the smaller field provided by GNL. And we also think that this mode will be a primary driver also for using the imager with this higher stray correction provided by the narrow field mode, then in a somewhat smaller field of view at the 20 by 20 arc-second, but enabling, for example, interesting capabilities to follow up in the time domain science cases. So while GEOMOS is primarily, both in terms of imaging and spectroscopy, driving the design of GNL, I also wanted to briefly mention that GNL wavelength coverage will be between 0.03 micron to 2.5 micron. And this means that among the current instruments at the Gemini North Telescope, GMOS, the multipurpose optical instrument, would in principle also be available to be fed by GNO within the red band of the GMOS wavelength coverage. So GNO, when used together with GMOS, will cover a very wide range of science cases, which I think basically reflect the wide range of science we are seeing during this conference. So basically, they have been developed both by a science team on the GNO side, as well as by a GMOS science team. And they really cover science from solar system science, via galactic science, star formation, to extragalactic science and cosmology. And I'll just highlight a few of the science cases based on some of the key capabilities provided by the system. So one key capability is that it will be a very powerful capability for high spatial resolution follow-up of time domain events. And I'm very thankful for the very interesting talks we have seen earlier this morning, because I don't need to introduce anymore. I guess one of the science cases where we think this can be useful is to follow up kilonova, which we've heard a lot about this morning in very interesting talks, and especially also, of course, referring to this famous gravitational wave event 2017. And I'm just showing here again the follow-up from this worldwide campaign, which was obtained in part with Flamingos 2 at Gemini South under natural seeing. And the GNO mode, for example, would then enable to do such follow-up at a high spatial resolution, which may help to disentangle the transient source from the underlying galaxy light if there's a stronger contamination. And that would be very interesting also to discuss this with the experts from this morning's sessions to see where this mode could be really useful. And now going to the second key capability, which is actually that GNO operated together with GMOS will have very powerful tools for spectroscopic surveys, of course, particularly enabled through the multiplexing capabilities provided through GMOS. And we will hear more about these science cases in the next talk. And I'd also like to mention that GNO and GMOS will also be a very flexible capability both for solar system science, because GNO is planned to include a non-sidereal tracking mode, and also for other time domain and multi-epoch studies, just because it's fully integrated into the Q operation scheme with basically nightly availability. This will much facilitate to do multi-epoch studies with the AO system. I just briefly mentioned that these science cases also are very much in line with the recommendations of the Astro 2020 report, and actually GNO was mentioned here, as you can see in this item 3, as one thing that that has a strong case for continued support, which we very much acknowledge, of course, which was based on a white paper and RFI documentation that was submitted. So just to summarize, these are the performance requirements for the narrow and the wide field mode. You see the wide field mode at the top, which is the 85 by 85, basically field of view in terms of the imager in GMOS. And for this, we have full width have maximum requirements in the K, H, and J band. And the next two lines indicate the narrow field mode requirements now in strain ratio. And this is here distinguished between a mode which is the more likely case, where you have 60% sky coverage for the natural guide star selection. And we also show for comparison a mode in which we have bright on-axis guide star. And all of these numbers are actually at an average altitude for about 35, for a 25-degree zenith angle observations. And I'll switch a bit to the more technical overview of the system. I already mentioned that GNO will be using 4 laser guide stars. And these are created with 2 optical lasers, which are then each split in 2 and launched via their own launch telescopes. And the AO bench is then designed to have 4 laser guide star wavefront sensors, which can be adjusted depending on the constellation size for the 2 different modes. And also the AO bench will include a single DM, and the driver behind this was to have as little but as effective optics as possible. This is an overview of the architecture so that you can actually see something. I'm going to zoom into the top part here, where you can see the 4 laser guide stars launched via the 4 laser launch telescopes created by the 2 lasers. And now looking a bit more in the lower part of the diagram, you can see the RTC, which is being developed by HAA, and also the single DM, and the light path being split into the wavefront sensor path, which includes the natural guide star wavefront sensor as well as the laser guide star wavefront sensors, and of course into the science beam path, which is then providing the compensated beam into the science instrument. And this is just a model of how the laser guide star facility will look on the telescopes. You can see that the lasers are going to be site launched. So there will be site launched laser launch telescopes. And on the top right, you can see the so-called beacon, an optomechanical layout of the beacon, which is the system that's splitting the laser beam into two and also controlling the focus, polarization, and jitter of each laser beam. And this is just to show you that GNL is actually already happening in terms of hardware. So we have certain hardware already assembled and partly installed. These are two photos of the laser lab at the Hilo base facility. On the left, the blue boxes, you can see there are the laser heat exchanger. And on the right, you can see in the center, the silver box, which is the new laser on the table in the lab. And finally, also the LPC, which is the laser pointing camera, which will aid the acquisition of the laser guide stars onto the wavefront sensors, has already been installed on the telescope, as you can see in the picture here. And it actually recently had its first light, which is shown in this graph here. And I'll just conclude with a few conclusions on that GNL has made significant progress, especially with respect to the procurement of the aero bench, which is on the critical path of the project. And actually the contracts for the phase A, which is a competitive conceptual design phase, are in the process of being signed. And also the other work packages have been progressing well, and this includes the laser guide star facility, the system controller, as well as the RTC. And as I showed you in some of the pictures, parts of the hardware are actually already arriving, assembled, or installed. And I just finished the talk with the note that the current expected first light for GNL will be Q2 of fiscal year 28. Thank you.
Thank you. Questions for Julia? Questions on Slack? Questions from me? Okay. One of the things that we've heard throughout the week, and I thought we heard a lot of it today, was how useful it's been to have Gemini available at a particular time on rapid notice. What are the limitations on adaptive optics? We know there's the laser clearinghouse, but what are you thinking in terms of being able to use this for time domain? Because Gemma, of course, is all about multi-messenger. Can you talk a bit about that?
So we're currently exploring strategies to, for example, request the full sky within windows so that that you don't need to request specific targets in advance anymore. That's being explored to enable the more rapid response also for laser guide star aided observations. And particularly, of course, as we have heard throughout the conference, this will be especially a mode which will be very complementary to the James Webb Space Telescope because of its less ability to follow up rapidly on target of opportunity. So we hope this will enable some interesting science, for example, kilonova science, as we've heard this morning.
It used to be that it took a whole army of people to make the laser work and make adaptive optics work. What are your needs for operational staff? Is this going to be a routine kind of thing that you don't need any special troop of people?
So a special focus of the project is to make it as easy as use as possible. And for example, compared to GEMS, which has always been a bit more complicated to use with more operating staff than the normal operations, and also for some time with block schedules. The idea here is to have a really nightly availability of a laser facility and more or less a very simple approach that can be performed by the normal Gemini observing staff, which includes an operator or science operations specialist in the case and the observer. So we're currently operating like this actually with Altair and the laser in the north. There's no additional staff needed for this. So the plan is to have a similarly easy to use facility for GNO.
Any other questions? Zach, any questions from? All right. Okay, let's thank Julie again. Okay, as we heard, we're now going to hear what will go behind the GNAO system. So we're going to hear some Suresh Van Anandam from Toronto, who's going to talk about the Gemini infrared IFU system. Girmas. Take it away.
Thank you, Pat. Everyone can hear me well?
You want that?
Well, thank you very much for giving me this opportunity to talk here today. So I'm going to talk about the first light instrument behind GNAO, the Gemini infrared multi-object spectrograph. It's a mouthful, and we spent a lot of time figuring out how to pronounce it, and it's GERMAS, so it's easy to actually say it. It's a project that's largely being led by Canada with significant support from the National Research Council of Canada and, of course, the Gemini Observatory. And this is a community-led instrument that started off as a visitor instrument and then has now evolved, heading towards something that would one day be a facility instrument at the observatory. And of course, on this image, you might recognize one of the images from the James Webb Space Telescope. The goal of GERMAS is one of the main goals of GERMAS is to follow up a lot of James Webb targets and do more in-depth science. And very quickly, the instrument is being built by a consortium of Canadian universities and national lab, and of course, with support from the Gemini Observatory. It's a complex project with a lot of components, subsystems that all come together and have to work together. And so we're basically leveraging all of the expertise within the Canadian community, particularly the work that was done as a technical pathfinder for multi-object adaptive optics called the Raven project that was demonstrated on Subaru. Now, one of the things that has been happening over time is that GNAO and GERMAS are becoming more and more integrated, and you can probably tell by our talks that we're talking to each other and trying to look at the whole thing as a single program in a holistic fashion, particularly the science, the concept of operations, systems engineering, and of course software, because all of this has to work together really well to reach, to reach the performance at the focal plane at the end of the within the instrument. And so we're very thankful that the Gemini Observatory has been providing a lot of support, and we've been able to work very closely with the GNAO team. Now, you nicely summarized what GERMAS does, and in a real nutshell, it's basically a quad integral field spectrograph that sits behind the 2-arc-minute GNAO field. And it is able to image through that field at the same time. You get a little bit of occultation from the pickoffs if you do wish to do simultaneous imaging. And the diagram on the right shows you the GNAO field, and the imager field is the square inscribed within it. And of course, each IFU is doing additional corrections so that you get very high angular resolution observations within the small field of view. And of course, when we set out to do this project, while we started off with thinking about doing a galaxy survey and optimizing a high redshift galaxy survey and optimizing the performance of the instrument, we worked very hard to fill in all the gaps and find a broad range of science cases that range from the nearby universe to the most distant universe, and with a focus on what we can do that JWST can't do easily. And of course, GNAO has also developed on its own set of science cases, and there's considerable overlap between the two. And here is just a laundry list of science programs that we have fleshed out for the instrument in order to really understand what we want to build. And a lot of these programs that are shown over here are a combination of imaging and spectroscopy. So we've tried to really see holistically what are the capabilities that we would like to have. Now, when you design an instrument, you want to get a set of requirements. And if you have a laundry list of science programs, it's hard to converge on a set of requirements. So we looked for the most challenging science cases in order to what we call cardinal science cases, in order to figure out what the specific requirements of the instrument should be. And there are basically three specific science cases. One of the big ones, which I alluded to earlier, is doing a high redshift galaxy survey out to redshift 3 in depth in order to complement the local integral field galaxy surveys that are being done and fill in the gap of galaxy evolution from high redshift to low redshift. Now, some of this work has already been done, and I'll show you in a second. The goal here is to really amass a large sample in order to be able to look at all of the different axes of galaxy properties and how they impact their evolution. And one of the specific things you would do with an integral field spectrograph is measure the kinematics of the galaxy using line emission and AGN activity, et cetera, which is shown by the plot on the left. And you can start piecing together the dynamics and to some extent the stellar population of these galaxies. Now, the state of the art right now is the SINF survey. I'm not sure exactly how to pronounce it correctly. And they've spent a long time using the Symphony instrument on VLT to do AO and get high angular resolution observations of redshift 2 galaxies. Now, our hope is to push that by a factor of 10. And the way that's done is from the multiplexing and minimizing the overhead of observations, and also pushing the sensitivity of the spectrograph. And that's how we've approached the problem. Now, of course, ERIS has just come online from the earlier talk. So they're going to be pursuing their own guaranteed time program. So we're evaluating exactly what the goals of GERMOS will be in light of ERIS and James Webb now operational. But this is our nominal plan. The other reference science program that we want to target is something that's high angular resolution. The distant galaxy survey is moderate angular resolution. And this is to observe central regions of globular clusters and looking at the kinematics of the stars in these regions and trying to understand if there is any evidence for an intermediate mass black hole by looking at the kinematics of these stars. Now, a lot of this can be done with, say, MUSE in its narrow field AO mode, but there's a considerable number of globular clusters within the plane of the galaxy that are highly obscured that GERMOS would be ideal in targeting. So Yulia mentioned this, one of the other pieces, one of the other reference programs, particularly for the imaging mode, is looking at AO-assisted imaging of transients. And the goal here is not only sensitivity and image quality, it's also speed of being able to set up the instrument and GNAO. So we're working very closely with the GNAO team to understand the overheads and be able to target transients that will be found in droves in the near future. Now, so in the end, when we put all of this together, we basically have two instrument modes. One which will allow us to pick 4 objects from the GNAO field of view and do multi-object adaptive optics, and another where we can put all of the pickoffs right in the center so that there's a roughly contiguous field at the very center of the GNAO field and be able to do use the laser tomographic AO and do high angular resolution spectral imaging. And of course, the imager sits behind the pickoff. So if you wanted to, you can do simultaneous imaging. And that was normally the plan, but there are some complexities associated with that. With IR instruments, you have to nod, and the imager and the spectrographs have different integration times. So that's something that we're currently working through to understand. So just a little bit about multi-object adaptive optics. You might be wondering what the heck is that? And that's shown by the graphic on the left there, where you have GNAO that has its own wavefront sensors and the single deformable mirror. It'll be basically correcting the low-level turbulence. And what GearMOS will do is use the information measured by GNAO about the atmosphere and correct the remaining turbulence along that specific line of sight with our own deformable mirrors. So that ensures that each spectrograph will have an optimal correction. And we've done some simulations to show that there is fairly dramatic improvement in image quality doing it this way. I mean, that's the litmus test. You have to show that there's a significant gain. And we're actually working on putting a test bed on Sky right now, probably in the fall of this year. We'll be doing this type of adaptive optics on a 1 meter class telescope to validate our plan. So taking all of that in summary and figuring out what are the requirements, GearMOS essentially has 3 spatial modes and 2 spectral modes. So the spatial modes range from being able to cover, super seeing limited imaging all the way down to diffraction limited imaging in H-band. And the spectral modes cover RF 3000 to 8000 for being able to do more precise kinematic measurements. And when you change the spatial mode, you actually reduce the field of view because you have a fixed number of spaxels that are available to you, so you get smaller fields of view. And just for reference, the James Webb NearSpec IFU is 3 by 3 arc seconds, and it has a similar spatial resolution as our coarses mode. So we can pack fair bit more information in a single IFU versus what NearSpec can do. And we also get higher spectral resolution. So this, just towards the end of my talk, I just wanted to show you a little bit about the instrument architecture, and this kind of shows the flow of light traveling into the instrument, starting from GNAO and the various subsystems such as the pickoff arms and the spectrographs and the AO system. And we have our own calibration system too, both do metrology calibrations for the instrument as well as spectrophotometric calibration. One important aspect of how this instrument works is information needs to be transferred between the Gemini real-time computer and GearMOS. And that's one of the reasons why we have to work very closely with each other. So the instrument design is fairly advanced. This is just how it looks right now. Like any other Gemini instrument, has this nice T-shaped structure. And we successfully completed a preliminary design review 2 months ago. And so we're in the final design. And of course, we're also going to do some risk mitigation. And we're going to start building the cryostat next year so that we can retire some of the risks that are associated with the spectrograph. This is just a diagram of the pickoff system. You can see what it looks like on the top right. And the AO system is integrated with that. The deformable mirrors sit inside of this. And then the corrected beam goes into the spectrographs. And the pickoff system has 4 pickoffs that can access the full 2 arc minute field that we have available. And finally, this is how the IR spectrograph itself looks like. So it has 4 spectrographs. You can't see the one towards you and behind you. It's sitting in this blue square tube. You can see the one on the top and the bottom. And at the very center is the imager that's being led out of the National Research Council of Canada. And so there are really 5 instruments on this, within this cryostat, that have to work together to make GEARMOS a success. And of course, one of the important things that we had to do for the spectrograph risk mitigation is actually build the image slicer that was part of our project plan. And we built a prototype that looks almost exactly like what would go on GEARMOS. It's shown by the little figure below, just before our preliminary design review, to show that we have the capability in-house to do that. With that, I wanted to conclude my talk. So GEARMOS is going to be a powerhouse for doing AOFET integral field spectroscopy in the future, particularly targeting large extragalactic surveys. That's something that James Webb will have a lot of difficulty to do, but this would complement its capability quite well. And one of the things that it also does, and Julia mentioned earlier, is this is also a pathfinder, essentially a scientific pathfinder for a similar instrument for the 30-meter telescope that would go behind its adaptive optics system called Nefarious. So we're in critical design phase right now. Our expectation is we will deliver approximately almost a year before GNAO first light will happen, and that year would be spent integrating with the GNAO subsystems before first light. Thank you very much.
Thank you, Suresh. All right. Questions? Come on. All right. Please, Stefan.
It's made on a single point diamond turning machine. Obviously, it's not turning it, but it's cut off, carved out. That's right. So yeah, you guys probably use optical contacting to put that together. Yeah, we're just using an aluminum block and then we're carving out the slices. So we don't need that level of finish.
Yes, the micro roughness is not so bad in the infrared. Is that the?
That's right. Yeah.
Okay. Go ahead, please.
I have 2 very short questions. First, I was wondering if there were any limitations on the position of the IFUs within the field. And the second one, it was more about how it converses with you said the possibility of doing imaging simultaneously. So I was wondering how the filters and the ranges, how does that talk to each other with the IFU?
That's a good question. So the figure over there shows you like each pickoff has a certain arc that it can position itself. So it has approximately slightly under half of the field of view where it can position itself. Obviously, there's a collision avoidance that we will have to do also. So a given pickoff won't be able to access the entire field of view. We will have some software that figures out what's the optimal positioning. And at least for the galaxy surveys, we have way more sources than number of IFUs available. And for the imaging part, so the nominal plan is to use the imager for telemetry and track where the IFUs are over time and use it for acquisition for the long exposure observations. So there's been renewed discussions about maybe using the imager as a science instrument while those observations are going on because you're collecting photons. Now, the challenge there is the integration times are quite different. The IFUs will integrate for about 10 minutes and then nod. Imager will probably be 1 or 2 minutes. And if you want to get good image quality on your images, you have to find probably some way to nod the imager while keeping the IFUs in the same place as they were before. And we're very concerned about the gymnastics of doing that and whether it's worth doing that or not. especially with James Webb being able to do such great deep imaging. So that's why I kind of mentioned that it's under discussion. Whether and our PDR committee said, do you really want to do that? Because it sounds hard.
Zach, questions on Slack?
No.
No. Okay. Let's thank Suresh again for fascinating talk.
Thank you.
All right. So Zach and Jerry are going to drive the next one. Our next speaker is Paul Hurst from Gemini, who I believe is going to tell us about the feasibility of doing ground layer adaptive optics at Gemini, and I believe at Gemini North. So Jerry's going to get him set up. There he is. And Zach will put gold stars as needed, right, on the talk, which most people seem to ignore.
Yeah, 5 minutes, you're gonna get 5 stars.
All right, very good.
Awesome. Thanks, Zach. All right, I see my slides coming up there. I get a quick sound check. Can you guys hear me okay?
We can hear you right now.
Awesome. Thanks a lot. And yeah, it looks like I have the control. Okay, thanks everyone. Good afternoon. I'm Paul Hurst. I'm the technology development lead here at Gemini. I'm based at Gemini North in Hilo to tell you about the GLAO feasibility study that a fairly large group has been doing over the last several years. So ground layer adaptive optics, as Yulia told us about a couple of talks ago, only attempts to correct the ground layer turbulence. We neglect the higher altitude turbulence by averaging it out across multiple guide stars. And the idea here is that we get a very wide field correction. It's lower fidelity than regular AO, but it's a wider field. We want to do this with an adaptive secondary mirror. We want to use the laser guide star facility, again, that Yulia told us about, that as part of the Gemini North adaptive optics will give us 4 10-watt sodium side launched laser beams. For the natural guide star side of this, we anticipate using either the existing or upgraded P2 and OI wavefront sensors for tip tilt and slow focus. So adaptive secondary mirrors are kind of the key to this. The secondary mirror of the telescope becomes the deformable mirror for the AO system. There's essentially 2 vendors for these at the moment. There's Adoptica and TNO. These mirrors, they're both similar in the sense that they use a thin mirror shell. So a roughly 1 meter diameter, about between 1 and 3 millimeter thick sheet of glass, which is silvered in the normal manner and is the actual reflective surface of the mirror. Behind that, there are a bunch of actuators that push and pull on the back of that mirror surface in order to deform it. And that's where these 2 mirrors differ quite a lot. They use very different technology for those actuators. And both of those have different pros and cons. We haven't made any kind of selection yet. We're not at that stage, but there's pros and cons both ways there. So why would we want to do this? Why do we want to do GLAO with an ASM? So the baseline performance for GLAO in this kind of mode is a factor of 2 improvement in image quality. So you sort of, a regular quite good 0.6 arc second natural seeing becomes, really quite spectacular 0.3 arc seconds with GLAO. And this, of course, benefits both brute force angular resolution, but also point source sensitivity, especially in the infrared, where you can use, smaller apertures and get less sky background. Because we're not using an adaptive optics bench, the DM is the M2, and there's no throughput or emissivity penalty with this. There's no additional optics in the science beam of the telescope compared to the current operation mode in non-AO mode. And it doesn't take up an instrument port, and we can feed any instrument port on the telescope. So it really does become part of the telescope. You could envisage a future where using GLAO becomes, just like using tip tilt guiding right now. It's the default. And there's a caveat there in that we need the laser guide stars to do this. We can't propagate the lasers through cloud, so we need clear skies in order to do this. Many thanks to everyone who responded to the survey we did a year or 2 ago. And we did some science case reviews, and this shows a very strong support for a GLAO system on Gemini with a wide range of science users, which is hardly surprising. I mean, who doesn't want better seeing? So I'd like to tell you a bit about this feasibility study we've been doing and how we got to where we are. So we considered GLAO in the original concept for what became GEMMA and GNAO. And in the early stages of that, it became fairly apparent that there were some pretty big unknowns both in terms of how much it would cost to do this and can we even do it? Can we find a way to put this on the telescope? So we descoped it out of GEMMA and GNAO because of that. And the idea then is to carry out a feasibility study to basically answer those questions. Can we even do this and roughly how much would it cost? And that's what we've been doing the last couple of years. We're currently sort of also defining requirements and cost estimates for a conceptual design phase, which will be the next stage of making this ready to respond to a funding opportunity. So the challenge was, why is this so difficult? So the first question was, can we procure a suitable adaptive secondary mirror and mount it in place of the current M2 on the telescope? And we need to maintain the current tilt and focus and other functionality of the existing M2 system, which presents some challenges, but it appears to be doable. There are some other operational challenges with ASMs. In some ways, they're quite finicky devices. They are improving over time. But all these seem like they have solutions. It's all doable. The big, real unknown question was, where do we put the wavefront sensors? So we want to do this in such a way we can feed all the instrument ports and all the instruments on the telescope, which means we basically have to put them inside the acquisition and guiding unit. And the A&G is very, very space constrained. So there was a previous concept looked at GLAO on Gemini in the 2000s. And the idea that they explored was having a dichroic science fold. So you take the current fully silvered science fold, you make it dichroic, and you put the visible light wavefront sensors behind it, looking through the science fold, you reflect the infrared light off to the science instrument. And they determined that that was not viable because the current science fold has basically a steel lattice structure behind it, holding it flat. If it's also going to be transmissive, if it's dichroic, you obviously can't do that. So you can only support it around the edges. So you then have a pretty large optic that's only supported around the edges that you're tipping in all sorts of orientations as the telescope and the A&G position around the sky. And they basically found that it sags too much under gravity and you can't keep it sufficiently flat. So that doesn't work. So we looked for other ways to separate out the laser and science beam. So here's a little diagram of what I'm talking about with the acquisition and guiding unit. So the A&G lives in the center of the instrument cluster on the back of the telescope there. It's kind of the hidden central cube on the photo on the left there. And it's made of this stack of sort of concentric modules that fit inside each other. When you look at the sketch here, it looks like, there's bits of space available here and there. Maybe we can figure something out. On the right, this is a photograph of the actual module 3. The units you see there are the P2, the P2WFS, and the AO pickoff mirror mechanism. So you can see it really is pretty full. There's not a lot of space for adding extra stuff on here. So it is kind of tricky. So if we can't separate the light dichroically on wavelength, we have to separate it spatially. So the diagram I'm showing you here on the left, is a cross section through the center of the telescope. The unit at the bottom is the acquisition and guiding unit. Then there's the mirror cell. The blue lines represent the mirror in the middle. There's the M1 baffle above it. The purple line down the middle is the optical axis of the telescope. And then the green V shape is a science beam at the edge of the GMOS science field of view. And the yellow V shape is an LGS beam coming down from a laser guide star. You can see the LGS light comes to focus slightly behind the science focal plane. That's because the LGS light comes from the ionosphere at 90 kilometers rather than coming from infinity. And obviously, these two beams are 100% coincident at the secondary mirror. The secondary mirror defines the entrance pupil of the telescope. But they're obviously completely separate when them to focus at the various focal planes. So there's a point in between where these beams separate, where they no longer overlap. We've labeled that here as the beam separation point. So you can imagine it's pretty clear to see that if you make the LGS asterism larger, if you separate the LGS further from the optical axis on the sky, or if you make the science field of view smaller, so you either move the yellow lines out to the left or the green lines out to the right, then that beam separation point will kind of unzip up the telescope, which is what you want. You want the two beams to be further apart of the A and G in order to separate them physically. But there's some limits on what we can do here. If we make the LGS asterism too large, if we move the LGS too far off axis, then we get this vignetting on the M1 baffle. The M1 baffle is the big black tube that sticks up the middle of the telescope. And you can see in the diagram on the left here, the LGS beam will start to clip those baffle rings if we make this too big. So there's kind of two constraints there. And I want to explore each of those, or tell you how we explored each of those a little bit more. So the beam separation point, this graph simply shows the y-axis is the height of the separation point above the science focal plane, and the x-axis is the laser guide star radius, how far off axis the laser guide stars are. And then we've got several lines for different science fields of view. And then marked on with these dashed lines are the positions of various sort of strategic locations in the A and G. So simplistically, if you say, okay, well, we're going to separate the beams right down here at the ISS, that's basically very close to the focal plane, then that's great, because at the bottom of the graph here, you've got a huge science field of view and you've got no real constraints on your asterism size. But of course, to do that means that your laser wavefront sensors or your pickoff need to be at the science instrument focal plane. So we'd have to embed wavefront sensors in every science instrument, and the instruments are not really amenable to that. So that's not really doable. We want to put the wavefront sensors kind of up near the top of this plot. Thanks, I see the stars there. Where we can separate the beams in the A and G more. So that puts more constraints on the science field of view and the asterism size. So going over to the vignetting that I talked about, maybe the slides are stuck. Oh, there we go. Okay, awesome. What we're looking at here is a diagram of the pupil of the telescope and the illuminated area from each of the 4 laser guide stars. So the left-hand diagram shows this kind of critical point with the LGS asterism 6.8 arc minutes off axis. What happens with the vignetting that I showed earlier is that each of the laser guide star wavefront sensors ends up with a little crescent on the edge of the pupil, which is not illuminated on that wavefront sensor. If you make the asterism too big, these start to overlap. If you look at in the figure on the right, these are overlapped a lot, and these little divots in the 4 sort of diagonal corners, those areas of the pupil would only be sampled by 2 of the wavefront sensors. So that's going to impact the LGS performance quite a bit. So pushing on, we did some modeling to see how big an effect this is. We had this hypothesis that if we're in the case on the left where the crescents don't overlap, then most of the pupil is covered by all 4 wavefront sensors. These little crescents are only covered by 3. That's probably okay. So we did some modeling to verify that, and that turns out to be the case. So this is an AO simulation of the ground layer adaptive system we were looking at. It's not a very high fidelity simulation, so don't get too excited about the closed loop performance being really close to the diffraction limit at the longer wavelengths. There's undoubtedly issues that we didn't model that will separate that a little bit, but it does include that LGS vignetting effect. And you can see that we do get this factor of 2 image quality that is the nominal sort of GLAO performance. So that seems good. So putting those 2 things together, this red zone on the right here indicates where the LGS would be too vignetted and we can't go into there. The blue zone coming down at the bottom of the plot is where, we just don't know of any way to put the wavefront sensors, below the science fold, for example. But we don't want to go too high up. The further up this plot, we get a reduced science field of view. So this green ellipse, dashed ellipse, shows the kind of sweet spot where we're at that 6.8 arc minute LGS asterism radius, where we don't get too bad vignetting. We're proposing to pick off the light around about the P1 level, which seems like it's doable. And that gives us about a 6 arc minute diameter field of view for the LGS pickoff mirrors vignetting the science beam. So can we find a way to put LGS wavefront sensors at that place in the ANG? Well, it turns out we can. There happens to be some holes in the ANG shell that lead out to available space volumes in the mirror cell. So the concept we've come up with is to insert some deployable LGS pickoff mirrors into the beam. They'll go into the beam at the P1 WFS level, and they'll bounce the light kind of up and out into the mirror cell where we put the laser guide star wavefront sensors. Here's a 3D rendering of that. So you can see the green cone is the science beam, the yellow is an LGS beam. So these little pickoff arms are what we've, what we've added here. We bounce the LGS light off from the pickoff up to a full mirror and then out into this volume at the side of the A and G, where we can put the laser guide star wavefront sensors. There's kind of two possible configurations. You can either bounce the light across the telescope to the opposite hole, or you can actually bounce it up the same side and fold it out to the same side as shown here. So there's a couple of open questions. We're baselining on using P2 or OI for tip tilt. We don't really know if they're fast enough and sensitive enough. We haven't done simulations to know how fast we need to do the tip tilt, which tells us how bright the guide stars need to be. The LGS pickoff mirrors will vignette the P2 and OI patrol fields. So that further complicates this guiding issue. And the LGS asterism and thus the pickoff mirrors are fixed with respect to the telescope. So they will rotate on the sky as we observe. So the vignetting pattern will rotate and we'll have to switch guide stars as they come in and out of the vignetted regions. We are looking at investigating upgrading P2 and OI anyway, and we're really not sure yet, but it could be that these upgrades become prerequisites for GLAO. So finally, in summary, we found feasible solutions to the major challenges of implementing GLAO on Gemini. There's some compromises, but they don't seem to significantly affect their performance. The concept we have supports all instrument ports, doesn't take up an instrument port, and incurs no throughput or emissivity penalties. So it's very well integrated with the telescope. Conceptual design phase and beyond is currently not funded. In order to be ready to respond to a funding opportunity for that, we're working on basically capturing requirements and determining the cost and effort required for a conceptual design phase. Thank you.
Questions for Paul? Shall we?
Yeah, so LPT, of course, has a the Large Binocular Telescope has a one layer AOPS.
Can you speak closer to the mic?
Yeah, the Large Binocular Telescope has a ASM, right? So what we have been doing on LPT is the so-called enhanced seeing mode, which doesn't need laser, just a natural guide, just a regular guide star that seem to improve seeing by a factor of 2. So are you going to do that as well on this one?
So that's interesting that you get such good correction off that. We've bounced around. There's all sorts of ideas we could do with an ASM on Gemini. The P2 and OI wavefront sensors, the existing wavefront sensors, are 2x2 Sharp-Hartmans. So we can, in principle, measure astigmatism on those at full loop rate. And if we had an ASM, we could correct that, which I think is similar to what you're talking about. There would also be options for slightly higher order systems. So the older P1s, I think the P1 at Gemini South is a 6x6. We swapped that for a 2x2 at Gemini North in order to support a different LGS plus P2 mode with Altair. But there are options for all sorts of intermediate modes with, slightly higher order wavefront sensors driving the ASM, or indeed just driving it from the existing wavefront sensors. So we haven't gone into a lot of detail on of those, but basically the system that we're proposing, there would be no reason why it could not support all sorts of these kind of hybrid modes. Yeah,
I think LPT is correcting like 11 orders.
Sure. Yeah.
With the intensity mode, and seem to be like the default way of using the infrared spectrograph right now.
Yeah, sure. So that of course requires a bit of a brighter guide star than something that's only going to correct a couple of modes. But the system will be very flexible with regards to those kinds of capabilities. If there's a wavefront sensor somewhere, we should be able to use that and feed the ASM.
Thanks.
Questions on Slack? Nope. It seemed like a lot of the challenge is not so much with the ASM, but packaging the laser and all the wavefront sensors. Did you consider side launch for the laser, or is the performance problems are just too great?
No, the plan is side launch for the laser. I think Julia showed a diagram of the telescope with the laser guide stars on it in her presentation. It would be the same laser guide stars for this GLAO system as for the GNAO system. The launch telescopes have been spec'd such that they were able to propagate the stars out to a larger asterism radius in order to support this potential GLAO project.
Okay, so it's the pickoff mirrors and the wavefront sensors crowding in the center. That seems to be your geometric problem.
Yeah, that's right. It's packaging it in the A and G. You know, telescopes that have these big Naismith platforms with big AO benches on are great for all this kind of stuff. We don't have that. We have a very, very constrained space volume. And other telescopes also, some telescopes are basically just giving up on this. Ooh, sorry. Okay, that was my 20-minute timer. Some telescopes are basically giving up on trying to do something clever like we have, and are just putting the wavefront sensors inside the science instruments to support GLAO, which is great if you've got space in the science instruments to do that and you want to build a set of wavefront sensors for every science instrument that you want to use with the system. What we'd much rather do is figure out a way to put the wavefront sensors in the A&G system so that we can just use it with any science instrument. You know, this would work with visitor instrument. There's no coupling back from the instrument to the AO system. It's very much the telescope just delivers you the corrected beam.
Yes, that certainly would be the desirable way to go.
Yeah.
All right, well, let's thank Paul again.
Thank you.
So I believe we're now in the flash poster session. So the authors, I think you know who you are. Come on up. And do we know the order in which they are queued in? They'll show up there. Okay. Don't be bashful. Handheld mic? All right.
Oh, that's okay. Okay. Is this on? Okay. Hi, my name is Raven Gassis. I'm a graduate student at the University of Cincinnati, working on a project testing predictions of lambda CDM using strong lensing galaxy clusters. Specifically, we are looking into the central galaxy paradigm, which is the consequence of the hierarchical formation of galaxy clusters as predicted by lambda CDM. In order to test this, we are using a strong lensing galaxy cluster sample, such that we are able to determine the lensing profiles of these galaxy clusters, which gives us an idea of the dark matter content in the clusters. In order to do this, we need spectroscopic determination of redshift of the lensed arcs, which were determined using a variety of spectrographs, specifically, or I guess obviously, GMOS being one of them. Yeah, and with that, we were able to get the total core lensing mass profile, and combining that with HST data, we determine the shape and centroids of the BCG and ICL, as well as the ICM gas using Chandra data. And these are preliminary results. We make measurements of the position angles, ellipticities, and centroids of our cluster sample. And already we see concentrations to small deviations, which is good because that suggests that there is consistency of orientation and centroiding across a large spatial scale for these galaxy clusters. We also see that the ellipticities are well correlated, though the BCG and the ICM components tend to be more circularized. The BCG due to stellar friction in the core, and the ICM gas due to hydrodynamical effects. And yeah, by examining these multi-component measurements, we're able to determine what physical effects may be occurring in these clusters. Yeah, thank you.
Hello, my name is Jeon Yu from Kasi. I'm actually just now graduating next month, so very fresh. Yeah, thank you very much. Actually, thanks to Gemini, I'm graduating because this work is in my thesis in very big portion. I'm working on intracluster light, ICL, which is a starlight from bound to galaxy cluster, but not individual galaxies. So ICL study is very important because it tells us the creation history of galaxy cluster. Yeah, so we observed the fossil cluster at redshift 0.47 using Gemini telescope, GMOS North, deep imaging, and MOS observation. We proposed this observation and got result and published the result last year in MNRAS. So yeah, thank you very much. And oh yeah, you can find this poster with the same header over there. So yeah, please tune.
The nod to go to the next slide.
Hi everyone, I am Jongwon Lee at Seoul National University, and I am interested in this kind of jellyfish-like galaxies, which are showing very spectacular starburst activity with long asymmetric tails under the effect of land pressure stripping in galaxy clusters. In particular, I am studying the jellyfish galaxies in massive galaxy clusters because massive galaxy clusters tend to show the much stronger and more extreme effect of land pressure stripping than low mass galaxy clusters. So I obtained these 5 jellyfish galaxies, GMOS IFU data of these 5 jellyfish galaxies in the massive galaxy clusters at intermediate redshift. And as a result of emission line analysis, and I found that there is a positive correlation between their star formation activity and their host cluster velocity dispersion. In other words, jellyfish galaxies tend to show stronger starburst in more massive galaxy cluster. So for the detailed information, please come to see my poster, and any comments and questions are welcome. Thank you very much.
Hello, my name is Alexander Navar. I am a PhD student at the University of Cincinnati. I am working on characterizing a set of high redshift Lyman alpha emitters using strong gravitational lensing. As you can see in the bottom here, that's overlapping a little bit. Oh well. As you can see in the bottom here, here are the 6 lensing clusters, and the images that I'm studying are outlined by the yellow boxes. Above that is GMOS spectra, confirming that these do all indeed emit Lyman alpha. From this, we submitted a Hubble proposal, which allowed us to get narrowband imaging that isolates the Lyman alpha. With that and wideband imaging from both Hubble and Spitzer, I was able to do photometry and SED fitting, inferring some properties like galaxy mass, age, and dust. In addition, I developed custom code to extract radial profiles of the emission in the different bands that I have. And with all of this data, I'm analyzing and characterizing the spatial Lyman alpha emission in these high redshift galaxies. And so if you'd like to know anything more about this, please come by my poster and have a word with me. I'd love to chat.
Hello everyone, I'm Carlos Escudero from the Astrophysics Institute of La Plata, Argentina, and the poster we are presenting is a project that we are carrying out with the fellow Natalia Guevara and Dr. Fabio Fai.
The audio a bit.
In this work, we analyze a dwarf galaxy located in a small group at a distance of 20 megaparsec. For this study, hello everyone, I'm Carlos Escudero from the Astrophysics Institute of La Plata, Argentina, and the poster we are presenting is a project that we are carrying on with the fellow Natalia Guevara and Dr.
Okay.
And the poster we are presenting is a project that we are carrying on with the fellow Natalia Guevara and
Yeah,
Dr.
we're
Javier
going to
Pfeiffer.
try to get
In this
the
work,
volume
we
up a little
analyze
better
a
so
dwarf
people can
galaxy
actually
located in a
hear
small
it.
group at a
And
distance of 20 megaparsec.
why don't we
For
try
this
to get
study,
that queued
we
up
use
for tomorrow
excellent
morning
photometric
during
and
the break?
spectroscopic data obtained with the GEMOS instrument at Gemini South,
Pat, did you want to
with the
say
aim
anything
of
else
analyzing
before
its star
we
formation history.
wrap up for the day?
I invite you to look at the poster in its online and face-to-face.
I want to overtalk Carlos here. Okay, so thanks everyone for quite an interesting session. We're going to have a coffee break and look at the posters. And then I believe Brian is going to conduct another GPP workshop after that. And then do not forget our special presentation on the magic of astrophotography and astronomy at Gemini here in this room at 7 p.m. from a world-renowned astrophotographer. So with that, let's thank all the speakers for today and then go enjoy the posters.
There's a what, like a 2 hour gap. Yeah. So I'm basically just going to wrap things up a little bit. I'm gonna go here fast and I'm gonna be back here.
Sound good?
That's everything. That volume is bad, but when I tested it over lunch, the volume is good, but I want to make sure, so I'm gonna totally make sure of all those things. I would.
Which one? The poster?
Oh, okay, so I guess I'll do that first and then. I'll find out. Yeah. Well, no, come out. Ahí.
Me cago en la puta, no le quitaste esto.
¿Qué tengo que quitar eso?
Puto pollo, se me cierran los ojos. Vamos a trabajar, Ricardo Salinas Trabol.
¿Y por qué tengo que quitarlo yo? ¿Ah?
Porque tú eres mi Trabol. Anda, desconéctame eso, por favor. Desconéctamelo porque que si no me tengo que levantar otra vez.
Hechizo. Transformador pirata. La serie.
Me lo están pidiendo.
Propiedad del gobierno de los Estados Unidos.
Estoy esperando a ver si te falla.
Ya vamos a estar un rato y vamos a mostrar lo que tienes. Y vamos a jugar. Mira, lo mismo que hace 2 años. Y basta, basta.
Sí, ¿no?
Sí, no, sí, está. Estoy anotando puramente. Oh, no.
Que después estos libretos son tan útiles.
No.
Que no dice cuánto es por ahí logrado.
Como shopping list.
No hablar de voy a dejar de hablar porque intentando hablar súper mal para que no me
Hablas igual. Igual. Travel.
But you didn't have 100% attendance before, so. So you should finish up the other 100% right here. You'll set up later, so.
Hi, everybody. If you're here for the GPP workshop, can you raise your hand? Do you want to come up? Yeah.
You don't have to, but you know, maybe social party up here.
Because there's a smaller group today, because this is a repeat, but it'd be good to come up.
이거 했던 거 같다. 근데 어떤 것도 하는 거야.
So this is the same one you did yesterday? Yes. I mean, I did it. Okay, thank you.
Is anyone online for the GPP workshop?
I have no laptop, so I just want to see.
Okay. Yeah, for people, I think we only have like 3 or 4 people. So I think we'll probably try to do it like sit around a laptop. Actually, no, we can just do this.
Let's do that.
We'll just do this.
People here.
This will be shorter than Tuesday because some of the slides are repeats from this afternoon. I'll go through it quickly and yeah, it's fine. Okay, let's get started. So, okay, good. Just kind of basic background, a little bit more than this afternoon. We've had the PIT and the OT, which are current applications for proposals and observation preparation. We've been using them for like 20 years, improving them slowly. But we realized a few years ago that we just can't add the usability and infrastructure changes that we need with the current code. It's hard to work with. So it's time to just start fresh. Already went through this. It's usability improvements. It's the capabilities that we need for other software like the scheduler and make the code a little more homogeneous and easier to maintain. I did mention sort of, we don't want to get rid of these heavy applications you have to download. So the GPP architecture is web applications connected to a database. And these are the different to the system. This is a diagram, all the different pieces. So you get a little look under the hood at how it's organized and how complicated it is. So these are the main applications that you will probably use. There will be a dashboard, which will show you like a list of your programs. So you can switch between them, copy your program to a new semester, that sort of thing. There's Explore, which is the main application that I would mainly go through today, which is for proposal preparation and observation preparation. It replaces the PIT and OT basically. There's Browse, which is a search capability. The OT has this browser window you can pop up. It's like that, so you can search through all the programs that you have access to find things. Chronicle is a logging tool. It'll be used to view the night logs and observing logs, so you can see the comments on your observations. And weather is the front end to a weather survey, which will have historical weather data and forecasts, so you can see what the conditions are like, your observations. And there's a whole bunch of internal stuff. There's a little bit of Observe, which is the thing that actually executes the observations at the telescope, commanding the instruments in the telescope. There's Resource, which will be a common telescope and instrument calendar. So we'll say when the instrument is on the telescope, when a certain grading is in GMOS, who is actually looking at night, so we can match it people's capabilities of what we need to do. Schedule is the interface onto the automatic scheduler for QCs, so you can do experiments with the scheduler, and then there's an admin window for managing users and programs. And then there's all these other pieces to it. There are services that are used by various things. And you've got a service for doing automatic guide style. That's an extension of the thing we have today. Integration time calculators, which are built in. A calibration server, which will tell the database what caloric styles to use for a given observation for automatic selection, that type of thing. The scheduler itself, which we're building. So those are the basic pieces. And the connections to outside services like Sinbad. So there's a lot of moving parts here, but it's still a lot better than what we have now because you're using these common databases, so it's very integrated. You don't have very, very separate pieces and require changes in 5 places just to put in one new filter. So we'll go a little bit about the layout of Explorer, which is in this main phase 1, phase 2 application. First, about the overall layout of all the applications are about the same, so have the same look and feel to make them easy to use. Get used to one, the others will be familiar. So up here, there'll be a little application switcher, like you see in Google. You click on that and you can switch between browse and explore and observe, that type of thing. The upper right will be for user identity for logging in, authenticating. Then on the left, there's usually a navigation bar with different tabs, just give you different views on the type of thing you're looking at. And based on what you select there, you get lists of items here, and then you select something there and you get the details on the right in these different panels. And then I suppose there'll be a button for creating a proposal. There's search up here, and usually there's some sort of action buttons for things you need to add or remove, or sort of in this area in the menu bar of these panels. So let's add some observations to explore. NGC 1055. So then now you click on that, and now you have all the details. You've got target information and constraints and instrument configuration and ITC output down there, for example. We have a few more observations. You can see a few different features. Here's a junior's observation, which needs associated tellurics. And right now you have to, we give you a template, but usually you have to fill in the 2 tellurics, one before, one after. If you then decide you want to change your junior's configuration, you got to manually go in and change the telluric observations that goes with them. And this is all integrated. The system will know these tellurics. It will find one that matches depending on where it's going to be scheduled. And if you change the junior's configuration, the configuration of the tellurics changes automatically. There are also some organizational features. We're going to have sort of logical groups and groups. So you can say observations have to be done right together in some sort of order. Or group gives options, like this one thing can be observed on GMOS or GMOS cell. I don't care which, you pick one, and then the other one will be turned off as soon as it gets observed. There's also an advanced configuration. Mentioned before, so the basic configuration you put in your science requirements, like wavelength and resolution and signal to noise, and the system will give you the list of available options. You pick one of those, and then at the advanced tab, you can sort of tweak the details of the observations. Is something like what the OT instrument component has now. Here's a bigger view of the same thing. So for GMOS, you could conceivably change your grading, change the binning if you're not happy with the defaults, update either wavelength or spatial dither patterns if the default doesn't quite suit you. And there's even going to be some exposure modes. The default is, you give a signal to noise and it determines the number of exposures and the exposure time. But if you need 10 300-second exposures to do some sort of time series, you can specify that. Okay, let's look at the targets view. I'll click on the targets tab there. Now everything is organized by target. So these two have the same target, and then you have the target details there. If you select one of these, so the whole group is selected and you edit something here, it's changing them for all of them. So it's like a bulk edit capability. This is where you do upload lists of targets. You don't have to type each one in or do a symbol search for each one. That's something a lot of people request, so they ask about that all the time. And otherwise it works very similarly. You select a group, do an edit, everything changes. Also, you can drag and drop things between these groups. Now the constraints view, again, variations on the theme. Now everything's organized by constraint set in terms of conditions, timing windows. An important thing is that GPP is moving away from these percentile bins we have now for the conditions, like the 70th best percentile, which people have a hard time, especially at the beginning of learning about Gemini. What does that mean in terms of what I'll actually get? So now we're going to get physical conditions on targets, like full width, half max, image quality. So again, you click on a group of these and change that, it edits everything. You do an upload list of timing windows again, so you don't have to just do lots of typing, and likewise drag and drop. And this is where also you would define those different in and or logical groups. And then there's the configurations view, again, organized by instrument configuration. You have sort of an advanced panel here again. Select a group, edit it changes it for everything, and do drag and drop. So all very similar look and feels. You can do a lot without having to log into the system. You want people just to go in and play with it and see if we have something useful for your science. But as soon as you want to put in a proposal and access something you've done before, you need to authenticate. And of course, our needs of this are you gain access to the programs, the proposals that you're entitled to, you have permission on. We want to avoid having to manage accounts and email addresses and affiliations, especially as you change jobs and move around. And we'd like to be able to track publications from each proposal program to publications, so we can look at effectiveness of each program. So the ORCID is the Open Researcher and Contributor ID is the thing that we're going to start using for authentication. It's really commonly used now. Most of you may have this already, since it's required for WRS. Journal publications, other journals support it. It's free, it's really easy to maintain, it's unique, and it sticks with you. And it keeps track of all the stuff about your profile and your email. You go into your profile in ORCID, change your email address or your affiliation, and then Gemini can just read that in without you having to do anything else. So if you log in, then you can actually create a proposal. So this is what the proposal view looks like. It should be pretty familiar, and then you can edit in the title. When we're investigators, and we can give each investigator like permissions on the proposal, so they can read it, maybe they can edit it, some people can submit it. So it helps with collaborative everything. Not many people could go into this and edit parts of it. Then there's usual abstract. You can do things down here like the essay sections will still be done in like LaTeX or Word. Right now, you upload the PDF, so there's the ability to attach the PDF. You can download this PDF summary, like you can do in the PIT, so you can see exactly what the TAP will read. You can do things like duplicating old proposals, so you can resubmit it a new semester. And then there's the submit proposal button when you're all ready. And the nice thing is that that's just a flag in the database now. It's not actually sending any physical file. Which means that if you realize you've done some typos, you need to update the figure, until the proposal deadline, you can just click that again and retract the proposal, make a change, and submit it back, and do it as many times as you want won't end up with duplicate proposals in a vacuum we have to sort through. Much easier for everybody. Okay, so now I will do the live demo, and then I'll let you talk a little more and then let you have at it. So this is what the Explore login page or start page looks like if you haven't been there before. Again, you can log in with your ORCID. If you click on that, it's the first time it takes you to the ORCID sign-in page where you put in your ID and your password. And the first time you see, you tell, yes, generally you can read my information, and that's basically you do that once. This is not my computer, so I'm not going to do that. I'm just going to go as guest for now. Now, this is the first time I've come to Explore. I have to pick a program. So I'm going to play with this one. So this looks like the basic layout in the mock-up I showed. So we've got the user information in the upper right, so I could log in there if I wanted to, and the tabs on the left. For the observations, then it shows the things that have been defined. I click on that, and here's all the target information, which comes from SEMDAD. There's the sky survey image. There's elevation plot to show visibilities. There's the constraint set, and then the instrument configuration selection. And then I can click on each of these panels just to hide them away so I can focus on certain things. Otherwise, it can be a lot of information. So I'm going to go ahead and create a new observation by clicking on this action button up here, plus observe. Now I need to add a target. So add a target. Now I just start typing. And it's going to do a SEMDAD search and match the target names that meet that string. So I got all these options. I'm going to click there. Downloading the information from SEMDAD. There's the sky survey image. I can zoom in or out with this Aladdin light widget. There you see M31, this target is one of the black goblet clusters in M31. There. Now, SEMDAD does not have the spatial profile and SCD for this object, so I can edit that. This is slightly resolved to arcsecond full width half max, and the SCD is more like G than O. So my target's done. Now I'm going to scroll down here to my insert configuration selection. And as I showed before, it's showing me all the matching instruments and components that match what I put in, but I haven't put anything yet. So I have 414 total matches. I'm going to start typing in my constraints. So I'm going to do calcium triplet observing 2500 resolving power and simultaneous noise of 100. Now you see this number is reduced to only 36 matching configurations meet these requirements. And now it's running the ITCs to get the total integration time done and sort by that. So I've got a couple of options there. Which one do I pick? This one's a little faster, but it's not much. One way I can decide on that is look at visibilities, the elevation plots. So I can actually make this window, if I get it right, a little bigger. It's a little tricky. Okay, I'm not going to worry about that. Anyway, this shows a lot of information. You can sort of mouse over it and shows you, information as you go along. I'm going to simplify this a bit by hiding the parallactic angle and the sky brightness calculation. So I'm getting the elevation as a function of time for this target for tonight. That's to be for Gemini North. I can change the date here if I want to, forward and backwards, or I can pick a date with this calendar GUI, calendar widget. So that's a single night. I can switch to a semester view as well. So that gives hours, the target is up each night or a semester, so it's calculating that. All right, let me go back to the night view. So that's fine. So now that's for GMOS North. And if I click on this GMOS South configuration, you see this is switched to Gemini South, and now you see the elevation is much lower. So as you expect, it's better in GMOS North. So I'll pick that. And I said, that's basically done. It was created under the hood, the sequence needed to meet the signal to noise. And if you're happy with the defaults, that is ready to be observed. No human phase 2 checking needed. And I can see that the actual sequence, if I go to this advanced configuration, remember, this is the start of that advanced configuration tab that I showed in the mockups. This is under active development, so it's not all the fields are there. But you see where the starting point for changing filters or binnings. But here's the view sequence button. So there's the sequence it created. The top part of the table is the acquisition sequence, which is now a completely separate observation. Now it's just included in this. So there's less observations you have to manage. And then here's the science sequence with science exposures and flats, the calibrations grouped together. And it's doing default wavelength data for this mode. And if you play around with it, changing constraints and so on, then you can actually see this sequence extend and contract. So let's go back to the basic view there. So again, there's some other things you might want to play with. There's always, constraints. For example, I want to try reduce, make the image quality constraint 1 arc second, so it's a little easier to schedule. Now you can see the ITC is updating the exposure time. Or I can change the cloud cover again. Now it's going to take about a little hour and a third. I can also change the constraints by going to the constraints view. So again, as I showed in the mockups, these are all organized by constraints. These are all, they have the same one. So if I click on that whole set and change the image quality to say 0.8, then let's change it for all of them. If I just edit one, say put this to 1.5 arc seconds. Now the constraints, that's different, so it pops that observation out and it's in its own category there. And if I want to make the constraints of this observation the same as these, I can just we'll do this there, drag it up in there. Now it's inherited the constraints from that. Then there's the targets view. Again, everything organized by target. This target is in 2 observations, one for GMOS North, one for GMOS South. Same thing, select all. I update the magnitude. And it's changed it for all of them. If I just change one of them, click on one, then I have the option of either editing just that one, or actually I can select and do all of them, which is the equivalent of selecting all. Just a little bit more, going back to the observations view in terms of some usability features to make this easy. Let's go down. So try to get this a little higher. Easier to see. Okay, one thing is we built in undo redo from the ground up, which you have to do to make it work right. It's one thing we absolutely could not do in the current OT. So if I start editing this, go back to 0.6 and 0.8. And I said I changed my mind. Instead of having to select it every time, I can just do undo, and it unrolls those changes. And I can go and go forward through the change list. The other thing is that we built the help directly into the tool. No need to go to additional web pages. If I want to know about this image quality, what does that mean? I click on the little information icon, the help pops out, and you can read about what that means, how you set it. Again, you don't have to go digging through layers of web pages anymore. So that's where Explorer is at the moment. Again, it is under active development. Every few weeks, if you come back to this, you may see some things that moved around, some new things may appear. So I'll go through a few more things and then you can add it. Just a little bit about the Observe application. This is an extension of our current web SecExec that the Gemini staff will know about, and also visiting observers will execute their observations using this. So again, the layout is pretty similar in terms of tabs. But this is also, not only is it for, you see the details of the sequence, like I showed in Explorer, with the individual controls for running and stopping and aborting, but it's a view on the automatic output of the automatic scheduler. So anytime you'll see this is the schedule.
Can I ask?
Sure.
Before you move,
Yeah.
Explorer is basically Pit. New Pit, phase 1, 2, or I'm still confused.
Yeah, the Explorer is the equivalent of Pit and OT together.
So the template, proposal template for fast turnaround, long large program, do we still need to download from the website? It's like we can choose within the Explorer. Okay.
The proposal section, you'll be able to pick, okay, I'm doing Q the next semester, I'm doing fast turnaround or long programs. So right now in the pit, you select which one. There'll be a similar type of selection there.
Yeah, okay. Because now Pit, we still need to download the different templates.
That's gone.
Oh, yeah, awesome.
This should support multiple proposals at the same time. It'll handle the FT with the regular calls.
Thank you. Another question is archive information, because now when we put the target, then it says, oh, there's the observation done in the archive, but it doesn't say what kind of previous observations. God,
That's a good point. This one can have something similar. Yeah, it should have some information about whether there's archive data on that already.
So it's okay. Yeah, because nowadays we need to go to archive and find the program ID of those the program that observe this particular target. So the new Explorer will show some kind of program information at least. Then we can go.
It's not much about that yet, so we can do whatever. But likely it would be probably similar to what we have now, and that you will do an archive query for that target, and maybe give you a link to go to the archive page. But we're not planning direct integration with the archive itself at this point.
Another question is a telluric star selection. So I guess I don't really know Genius much, but for Gemini South, well, iGreens, I don't know if iGreens will stay when we are ready with this, but iGreens and F2, I guess we can use the same telluric database, but are you gonna kind of expand the telluric star database? Because now we use a F2 telluric star database and the iGreens, we use different database.
The specifics on that we can discuss and just put in what's useful, what's best used, because we haven't really gotten there yet. That what I would envision is that we have of telluric stars in the calibration manager, and they'll do an instrument. Well, it's going to do a specific type of query, select a different type of telluric for it. But will be options for changing the type or putting in your own. But we should have, we work with instrument teams to decide what are reasonable defaults for a given instrument.
In the beginning, you show the architecture, and it says the instrument is just at the bottom. That's the communication between the instruments and this one is just API.
Yeah, that's just the control of the instrument via GIAPI or ethics. That's like what the SecExec does now.
So I wanted to, I'm just curious where the GRP is in that diagram.
It's that arrow that.
Okay.
That communication is via, depending on ethics or GRP. Just like the SecExec server does now.
Okay. That's all.
Yep. Good. So a little more on observed. So I was at, it's the view, the observer's view on the schedule. So instead of looking at right now we have static web pages with different plans, with different conditions that the QCs create. This is the replacement for that. For getting set of conditions, this is what the scheduler says is you should do for the rest of the night. But then if something changes, like this example as I wrap the TOO, is suddenly realize, oh, something new I should do right now. I'm going to suggest that, you should switch, you should stop doing this, and you should switch to this observation. And it's always giving you the option. This is an assistant to the observer. So the observer always has the control. They have the option of, doing the switch, or if they have more information and that they should continue, they can keep going. So then there are just some helper instructions for either stopping or aborting and switching. And then if they start that new observation, then within like a minute, the scheduler have updated the plan with the TO observation there and filled in the rest of the night. Similar thing for Chronicle. This is again the logging tool. So if on a given, you'll be able to see, this is like the next day you're seeing what happened the night before with all the weather loss and maybe some faults and how much time for each one and what the observers or, operators put in for things that happened during the night. So this will be able to see the logs for your program in all the comments, and it affects this does the automatic time accounting as well, so you see how much time you got used up, and QCs will be able to use this to do any adjustments. I already went through this afternoon on the timeline, so unless there are questions, we're just going to skip that. And you are here, you are doing the testing, so great. So guys, you can play with it if you'd like. I will keep this up later. I'll put these links here to, there's one page for a list of suggested activities and a little spreadsheet if you want to give us feedback, but a few things about this. There's the URL for Explore. So yeah, we're especially interested in bug reports, any comments about the usability and any feature suggestions. A few logistical things. I would suggest if you want to play with this, do you create a program for your own work? You can do this by going to the user menu, manage programs, and then clicking on plus program and just renaming it. The reason is that at the moment, we are using in-memory database on the, it's called Heroku, is the service that runs on Amazon. And everybody to reset these machines. And so two things about that. Everyone can see all the programs. There's no distinguishment between your username. So just so you're not overriding or conflicting with someone else, I suggest, create your own program. Again, this thing is temporary. Sometime during tonight, this will get reset and everything cleared out. Eventually, within a few months, we'll be connecting this to the real database, and then everything becomes persistent, and we'll be able to match up programs with users and isolate them from each other. So there's a suggested activities, but I'd suggest, go to these URLs so you can look for the activities. It's basically just do what I was doing, just create some observations, edit them, move them around. There's one activity, if you feel comfortable with it, is to just time yourself doing the set of steps that I suggest. You see how fast you can do it. That helps me because when we were doing requirements gathering, I had people do those tests with the current OT that can compare, the speed or ease with this versus the OT, and we can see if we're actually making an improvement. So have that in, and I'll just walk around and get feedback and help you out. Thank you.
Hey, so is that working? Yeah, maybe it's just me and I'm being dumb. And I'm not a power user or any user at all. But I can you explain the relationship between the program platform and the target observation manager? Is there common functionality? Do they talk to each other? Is there common code? What's the story between the two?
They're complementary. They can do some of the same things in the two. They talk to each other, but they don't share any code. They talk with the application program interface. So there's a protocol for how they talk with each other. So the Tom allows you, to run, you run one, say, on your computer, or you have one on the server for your group. It might be able to access a whole bunch of different facilities. So you can create a Gemini observation with it. You might not get all the automation of using Explorer, but you will be able to set up a GMOS observation with a target and send it to us, like I showed this afternoon, and it will send the information to GPP via these interfaces, and then under the hood, GPP is creating the observation and doing everything else.
So there's a flow from Tom to
Through GPP, right. It's just another way of interacting with it instead of just needing the GUI. And it will actually allow you to do the rendering with your iPhone, or it actually works pretty well on a tablet. You can do it with your iPhone, but right now the interaction is not really good. And we're not putting in the effort in to try to make it look nice on screen that small. Another thing to try is that if you, as you make your browser window wider or narrower, you'll see the thing reorganizing. It tries to do it so that it's somewhat reasonable, but I'd be interested in any feedback about what it's doing on that. There's a lot of work in there, and this is doing with more lab. I think the CSPC is working to try to put a uniform interface so that all the archives, but we don't have the effort like on more we could put a front end on it for the uniform interface that we can look at. We can with GPT, we can do lots of things like adding links to the archive. So you have a data set Chronicle, there could be a link there, you click it, and it's going to the archive link there. Doing maybe you can tweak this one. Because sometimes we want to actually Gemini yeah. Some of them. I think you can do like a cone search. You can give a coordinate and a radius and yeah, I think we're done.
Nice, thank you.
Yeah. Sure.